Number 10. Blyde River Canyon. Blyde River Canyon is the second largest canyon in Africa, after the Fish River Canyon, although it is much greener due to its lush subtropical foliage. Walking treks through the rich diversity of flora and fauna-filled canyon offer views of magnificent escarpments, waterfalls, and ancient geological phenomena. Visitors have the opportunity to encounter all 5 of South Africa's primates here, as well as hippos and crocodiles near the wetlands of Swandini Dam. Number 9. Cape Winelands. The fertile valleys of the Cape Winelands are surrounded by majestic mountains, sleepy villages, fruitful orchards, and some of the lushest scenery in South Africa. Visitors can follow the wine routes of the Cape to visit the vineyards of the country's finest winemakers, whose sherries, ports, brandies, and intriguing whites and reds are world famous for their delicate flavors and savorable palatability. Number 8. Addo Elephant National Park. Located in the Eastern Cape region of South Africa, the Addo Elephant National Park is one of the country's largest parks. The park is famous for its elephant population that has a special brownish skin color due to the red soil. Amongst the elephants, other animals like ostriches, antelopes, and warthogs can be seen. As part of the park's expansion, a group of lions and a group of spotted hyenas have been introduced to the park as of 2004. Number 7. Hermanus. Located on the southern coast of Africa near the Garden Route, Hermanus is famous for its shore-based whale watching. The sheltered, shallow waters attract southern right whales that migrate to the region each year to mate and breed. A 6-mile-long cliffside walk with built-in telescopes and benches offers visitors plenty of opportunities to view these social animals as they raise their flukes in the sea breezes. Whale-watching boat tours are available as well. Number 6. Durban. South Africa's second largest city, Durban, is located on the eastern coast. Durban's subtropical climate, scenic beaches, and close proximity to Johannesburg have made the coastal city a popular vacation destination for South Africans. The English colonial architecture that once dominated the city has been enlivened by a mix of Zulu murals, Islamic mosques, Hindu temples, and Christian churches. Number 5. Hluhluwe Umfolozi Game Reserve. As the only park under a formal conservation effort in KwaZulu-Natal where you can see the Big Five, lions, elephants, leopards, buffalo, and rhinoceros, the Hluhluwe Umfolozi Game Reserve offers visitors wildlife viewing opportunities second to none. Wildlife enthusiasts may enjoy the vast expanses of native plants and native animals during guided walks, self-guided drives, or opt for a thrilling viewing experience by boat along the Huhlui Dam. Number 4. Garden Route. The Garden Route is a scenic stretch of the southeastern coast of South Africa to the Storms River in the Eastern Cape. The name comes from the diverse vegetation encountered here and the numerous lagoons and lakes dotted along the coast. It includes some of the best places to visit in South Africa, including Knisa, Plettenberg Bay, and Nature's Valley. Number 3. Drakensberg. The Drakensberg is a mountainous region that forms the boundary between South Africa and the mountain kingdom of Lesotho and offers some of the country's most awe-inspiring landscapes. The name Drakensberg is derived from the Dutch, meaning Mountains of the Dragon, which truly captures something of the mountain's otherworldly atmosphere. Number 2. Kruger National Park. Covering a wide stretch of bush and savanna in the northern reaches of South Africa, Kruger National Park borders the countries of Mozambique and Zimbabwe. For its dense animal population and the variety of its flora and fauna, the park is considered the jewel of South Africa's extensive park system. Numerous well-kept tarred gravel roads have made the park a favorite choice for self-driving expeditions. Number 1. Cape Town. Located on the southwest tip of South Africa's Western Cape Province, Cape Town is the most popular tourist destination in all of Africa. The metropolis enjoys a mild Mediterranean climate, a well-developed infrastructure, and a spectacular natural setting. Cape Town's center is located in a relatively small area between Table Mountain and Table Bay. The city also serves as a home base for exploring nearby attractions, including the region's many diverse beaches, as well as the rolling hills and valleys of the winelands.
still colorblind. I'd be like hoping for a black and white. I gotta be my love while you gotta be mine. Feel it falling from the skies while you gotta be mine. My wave, my shock, my demon in the dark.
Hi, Slim. Are you good there?
Hello, hi, how are you?
Okay. So you're a co-host, so you can share when you need to.
Yes, I saw that.
Okay.
I'm all good to go whenever you are.
1 minute to lift off.
Thanks. Hello, George.
Hi, Salim. Good to see you.
Good to see you too.
And congratulations on all the work you're doing. It's fantastic.
No, it's a pleasure. Thank you.
It's 9 o'clock, South African time. Greetings to all. A warm South African welcome to all delegates and contributors to Gravitake 2021, International Conference on Gravitation, Theory and Experiment. The main aim of this meeting was to assemble scientists working on the mathematical aspects of gravitation, as well as those working on major experiments under one roof so that there could be a deeper understanding of the science on both sides. While we will miss the lively environment of a normal conference with its coffee breaks, opening cocktails, banquets, we are confident that the scientific aspect will not be lacking. The situation has come about because of the deadly COVID-19 disease that arrested the whole world for over a year. In this regard, we are delighted to have Professor Salim Abdul Karim, Pro-Vice Chancellor of the University of KwaZulu-Natal and a Professor of Medicine at Columbia University, to address us today. Prof. Abdul Karim is certainly one of the most recognizable faces in South Africa and many parts of the world, since he has been at the forefront of the fight against the pandemic in South Africa and globally, especially at the World Health Organization. Time does not allow us to dwell on his contributions to science. However, his illustrious academic achievements may be found on his wiki page, which we have circulated earlier. Allow me now to invite Prof. Abdul Karim to address us. Salim.
Thank you very much, Dr. Hansraj and Dr. Sunil Maharaj. It's indeed a pleasure and an honor for me to be here with you today at the opening session of the Gravitex 2021 conference. So I have to tell you that when Dr. Hansraj, Professor Hansraj, contacted me and said, would you give a welcome address? I thought, what on earth do I know about gravity, except that it keeps me on terra firma? So I said, well, the one thing I can talk about is about COVID. And so I thought I would share a few insights into COVID with you. But very briefly, I would just like to say that as we deal with the COVID pandemic, we are having to adapt in many aspects of our lives. And I am so pleased that you are going ahead with this conference, because we simply cannot stop our lives, our existence, and our daily routines because of this pandemic. We have to adapt in a way that mitigates its risk and try and maximize the opportunities as they present. So I'm indeed honored to be with you here this morning and to wish you amazing deliberations in your conference. I will just briefly touch on the COVID-19 epidemic as it affects South Africa, and I thought I would just share with you a few insights very quickly. So this is what the epidemic looks like in South Africa. We had our first case on the 5th of March. We had a rapidly growing epidemic initially, but early actions with the lockdown slowed the spread of the virus. And then we reached our first wave. We went into our second wave, and now we are recovering from our third wave. And if you want to look at it slightly differently, the green line is our first wave, and you can see that we had a relatively mild first wave compared to quite a harsh second wave and an even harsher third wave. So the waves seem to be getting progressively worse as we go along. And if we look at this particular wave, the third wave, in one particular province, Gauteng, it was really, really severe, reaching a high of 76 cases per 100,000 populations, more than double what it was in that province in the first two waves. And you can see in admissions, these red bars represent admissions. You can see how the hospitals were really under huge strain in the third wave in this province. Now we are in a situation where it's recovering in that province, but we now have it rising in two of our other provinces, in the Western Cape, where we are close to peak, and in KwaZulu-Natal, where we are rising rapidly. But I thought that it's, in South Africa, we seem to forget sometimes that it's impacting the whole world. We're so caught up in our own daily challenges. But as we look at the epidemic and as the world goes through its third wave, driven by the Delta variant, we are getting some understanding of the impact of variants. So I just chose 3 countries to give you an example. So this is India, Brazil, and South Africa. If you look at each of these countries, this is their first waves. You can see India had a very mild first wave. In fact, after the first wave, politicians in India were already claiming they had conquered this disease. If you look at Brazil, they've had a horrible first wave, and a first wave that they never really recovered from even. And in South Africa, we had quite a severe first wave, but relatively mild to what was to come. But in each of these countries, what has been a key indicator or key event that has changed the trajectories is a variant. In India, we had the Delta variant, and we saw the horrible images on our television screens about how India struggled to cope with the burden of the Delta variant. In Brazil, they had the Gamma variant, and the Gamma variant led from already a parlous situation to an even worse second wave. In South Africa, we had the Beta variant, and the Beta variant rose and gave us quite a harsh second wave. And now we have a Delta variant driven third wave, which is even worse than what we saw with the Beta variant. So it seems that the future of the pandemic is now being defined by each of the variants. We're now dealing with new variations of the virus with multiple mutations that is able to spread faster, in some cases even cause more severe disease. And importantly, they are learning and adapting to our immune systems. And so they are able to escape some of our immune responses. And so what lies in store for us? Well, I thought I would just share with you some analyses I did for the Elections Commission when they asked me to provide some estimations about what can we expect next so that they can figure out what to do with our elections. And if you look at our first wave, the first wave lasted about 74 days, and the interwave period lasted about 94 days. And the same, it's actually amazing that the first and second waves were very similar, 74 and 75 days. And the interwave periods are also pretty similar, 94 and 99 days. The third wave seems to be slightly longer. We are now, I think, on day 82 or 83. So I've estimated more likely we'll see about a 103-day wave in the third wave. And if we go with another 99-day interwave period, we can expect our fourth wave in December. And we simply have to expect that we will have a fourth wave in all likelihood, and that it'll be driven by a new variant, because that seems to be the global trend. And for those countries that have chosen to go the route of depending purely on vaccination, we've seen the price that comes with that, as you're seeing now, with the third wave really taking its toll in the US. The US is now in excess of 100,000 cases per day, and they've dropped their mask mandates. So you can imagine the challenges that that's going to provide. In a country like ours, I think in most of the world, we're likely to see a situation of repeated waves until the virus isn't able to mutate into any worse than it is. And because any mutations carry cost, fitness cost. And so I don't know when that's going to occur. It could occur in the next wave, so we may not have a fourth wave, or it could continue for the next 2 years. We don't know when that's going to happen, because we don't know what all the mutations are likely to be. But whatever it is, we can expect that we are likely to build on our vaccination programs and our public health measures. Because as we're seeing with the Delta variant can cause breakthrough infections. In fact, many of our vaccines are only about 50% effective against the Delta variant. Some are higher, like mRNA, but some of the others are quite low. So you're still getting breakthrough infections, but the very positive thing is that we are seeing very few deaths and hospitalizations among vaccinated people. So vaccines seem to protect against severe disease, but not against getting the infection at all. So thought I would leave you with a sense of, where things are, the sense of how important it is that we ensure that we build the mathematical capability to understand this pandemic, to help us better plan for what's in the future and for us to deal with it. And in all of your work, every one of us is being impacted by COVID-19. But we have to ensure that we continue our good work in whatever fields we are. And so I want to wish you well. I want to wish you good deliberations, and I look forward to hearing what came off this meeting from Professor Hansraj in due course. On that note, I welcome you once again and wish you well. Thank you.
Thank you very much, Professor Abdul Karim. Those were sobering statistics that you presented. Certainly, friends, when the pandemic hit, everybody was looking to our epidemiologists and other scientists. Nobody was looking for their friendly neighborhood astrophysicist. But nevertheless, it's good to note, though, that some of our colleagues at the UCT and other places have been dabbling in contributing to the COVID pandemic. Some of them have been doing some work on sampling of how to administer testing effectively and so on through hypercubes, and people like Bruce Bassett and others have been doing some good work there using machine learning and so on. So I think a combined effort from various sectors is very helpful. Thank you very much, Prof. Abdul Karim, for your contribution on this morning's program. We're going to now bridge over to our opening plenary section, and we'll call upon Professor Roy Martins. We have 1 or 2 spare minutes, but nevertheless, we are in good time. Professor Roy Martins, if you can say a few introductory words for our opening plenary session. Thank you. You are muted, Roy. Try it now.
Thank you, Sudan. for those watching me struggle like that, I was not able to unmute myself. But thanks, Sudan. It's a pleasure to introduce to you, colleagues, our first speaker of the conference, Professor George Ellis. George started his career as an undergraduate at UCT and then moved to Cambridge to do a PhD under Dennis Sciama, where his fellow student, slightly his junior, was Stephen Hawking, also being supervised by Dennis Sciama. And this was the beginning of an illustrious career of George's. In 1973, as one of the highlights, together with Stephen Hawking, he wrote what is a famous, probably the most famous book in gravity, The Large-Scale Structure of Space-Time. Sorry, I just got an automatic message there, recording in progress. And George is well known for a variety of aspects of gravitation and cosmology, but perhaps most for his contributions to a fundamental understanding of the foundations of cosmology as a science. He's a winner of numerous awards and prizes. From the point of view of those of us living and working in South Africa, we clearly recognize George as the founder of cosmology, the discipline of cosmology in South Africa. And without further ado, let me hand over to George, who will share with us some of his views on the history of general relativity in its golden age. Thank you, George.
Thank you very much, Roy, and thank you, Sudan. It's great to be here, and you've got a wonderful team of people here. Now I'm going to attempt to share a screen, and okay, there we go. And what I want to do is a slideshow from the beginning. Okay, so there is my screen, and I'm going to remove, there we go. So what I'm going to talk about is a brief history of the golden age of research on general relativity. And I'm going to ask immediately to apologize for any of you who I omit from this. I'm trying to cover a very broad theme, and I will probably have omitted some people. Please accept my apologies in advance. I've tried to put it in as generally as I could. And this stops. I'm not going into inflationary theory and so on. I regard that as being after the domain which I'm going to be talking about. So the first thing which made a difference in this work on in the golden age was the discovery of coordinate-free methods and the use of atlases. And this arose from the starting to use Lie groups to determine solutions with continuous symmetries. And a key set of references there was Eisenhardt's book, Continuous Group of Transformations, from which I learned a huge amount about how this worked. P.M. Cohen's book, Lie Groups, which talked carefully about the relation of groups to algebras, and in particular introduced the coordinate-free methods, and they were developed by Sigurd Helgason in his book, Differential Geometry and Symmetric Spaces. Now, the coordinate-free methods allowed one to be free from some of the problems arising with coordinates, and they regard vectors and tensors as operators, but most importantly, they introduced the idea of generalized bases. You did not have to use a coordinate basis in looking at solutions in general relativity. But the key central thing which will recur throughout here is the idea of an atlases, that in a solution of general relativity, there are coordinate domains. And a general solution involves different coordinate domains, like here there's a coordinate domain u alpha and another u beta. This relates to these coordinates, to these. There's an overlap domain, and there are transition functions across that. And so the key idea is that coordinate systems may only cover part of a space-time manifold, and that underlies a great deal of what happens in looking at the properties of solutions in general relativity. Now, the use of Lie groups to determine solution symmetries, continuous symmetry groups for space-time, key ideas is the surface of transitivity, that is the surface on which the group acts, and the difference between simply transitive and multiply transitive groups. It's simply transitive if the dimension of the group is the same as the dimension of the surface. It's multiply transitive if the dimension of the group is greater than the dimension of the surface. And in that case, there are isotropy groups which exist. Now, the thing which started this all going is a remarkable paper by Kurt Gödel, a famous logician. And Gödel spent time at the Institute of Advanced Studies in Princeton talking with Albert Einstein about general relativity. And that had a remarkable effect on general relativity. Firstly, he produced the famous Gödel solution, a space-time homogeneous stationary space-time with closed time-like curves, which I will briefly mention later on. And this started a whole wave of people studying the causal structures of space-times. Now, the second thing which went on is Luigi Bianchi, way back 100 years before, studied the symmetries of three-dimensional Riemannian spaces with simply transitive groups. And Bianchi universes is now the name used in cosmology for expanding anisotropic universes. And again, Kurt Gödel was the person who first introduced this in a systematic way in an amazing paper he did about expanding universes, invariant under what we now call Bianchi 9, and he produced his shear-free theorem, which I will briefly mention later on. And Abe Taub was another person who took this up. So Kurt Gödel played a very significant role in the development in general relativity of what I would call the golden age. The Bianchi universes, Heckman and Schücking in Hamburg, played a key role then, giving a classification by a symmetric tensor and vector, which was incredibly much simpler than the way that Bianchi had done it. Bianchi had done it in a very, very complex way. Heckman and Schücking made it a very easy thing to do. Myself and Michael McCallum developed the orthogonal models and the idea of the difference between class A and class B. The mixed master behavior at early times was discovered by Misner on the one hand and Belinsky, Kalatnikov, and Lifshitz on the other, which has generated a lot of interest. There are orthogonal models like the ones I looked at with Malcolm McCallum, and tilted models, which I looked at with Andrew King, and Collins and Hawking looked at this, John Barrow, and some other people. And then an outcome of all of this was the use of dynamical systems to study the Bianchi models. And John Wainwright, Klaus Ugler, Barry Collins played a big role in that. And dynamical systems is a good way of looking at properties of whole families of models. Locally rotationally symmetric space-times involve multiply transitive groups and a one-dimensional rotational symmetry everywhere. Kontowski and Sachs started this, and I developed this in depth with John Stewart. Now, general bases can be used, but particularly useful are tetrads. And a tetrad is a basis where the scalar products, GAB, that is EA dot EB, are constants. And the rotation coefficients gamma ABC, which is EA, scalar product with the covariant derivative of B in the C direction, each have a clear geometrical meaning. And so you instead of using Christoffel symbols, these are the equivalent for tetrads. Now, there are two major forms of tetrad systems. First is null tetrads. In the Newman tetrad formalism, the vectors are null vectors, a real pair and a complex pair, and one has symbol psi and phi for the Weil tensor and Ricci tensor components. These can be re-expressed in two-spinor formalism, as Penrose and Rinder did. And this formalism is used extensively in gravitational radiation studies, using to derive exact solutions and properties such as the gravitational radiation peeling off theorems, where they define the News function. Bondi, Sachs, Newman, Penrose, Strykman, Robinson all developed this in depth, not using tetrad methods in all cases. And this was the foundation of the beginning of gravitational radiation studies. Orthonormal tetrads are really good from my viewpoint, because in an orthonormal tetrad, you get the physical magnitudes. In an ordinary coordinate system, just a standard coordinate system, when you look at the components of a tensor, it may look very large, but that doesn't mean the tensor is large, or it means that the coordinates are very small, so the tensor look large, roughly speaking. Heckman and Schucking introduced orthonormal tetrads, and I developed them in depth. And tetrads invariant under Lie groups were used to study Bianchi models by myself and Malcolm McCallum. And using orthonormal tetrads, I was able to prove a generic shear-free theorem for pressure-free matter with no symmetry assumptions. If the shear is zero, then either the vorticity vanishes or the expansion vanishes. And that's an absolutely general theorem in general relativity. It raises interesting issues about the Newtonian limit of general relativity. Instead of tetrads, you can use dual one forms. With the exterior calculus, and Misner and Kerr were people who used that. Now, the Weil tensor is the trace-free part of the Riemann tensor, and it's what we can call the free gravitational field. The general formula is there. And Petrov gave a classification of the algebraic properties of the Weil tensor at any point into 3 types plus some subtypes. Type 1 is generic, the others are algebraically special, and this immediately enabled some important results to be derived, particularly the Goldberg-Sachs theorem. A vacuum metric is algebraically special if and only if it admits a geodesic and shear-free null congruence. The assumption of a specific Petrov type can be put into the Newman-Penrose or equivalent equations, and then one can look for exact solutions. And perhaps the most important case of that was the Kerr solution. The Kerr solution is a Petrov type D stationary and axisymmetric asymptotically flat vacuum solution with 2 parameters, the mass m and the rotation a. It reduces to Schwarzschild when a is 0. It's a rotating black hole and the endpoint of life of a rotating collapsed star. And Roy Kerr found this solution by putting in the assumption of Petrov type D, stationary axisymmetric, and then he found the solution in that way. Then there is the use of covariant methods for fluids and gravitational radiation. This started with some pioneering work by J.L. Singh in Dublin, Heckman and Schucking, then the wonderful Hamburg group of Ehlers, Kunt, Sachs, and Trumper, Felix Pirani in London, in Cambridge, Hawking, myself, Kip Thorne, and then later on I developed this with Van Els, Martens, and others, many others. What was important in this, and which the Hamburg group pointed out, is the importance of the tensor symmetries, whether a tensor is symmetric, skew symmetric, trace-free on the indices. This is absolutely fundamental, and it hadn't been realized very clearly. In very early times, the importance of those symmetries was not known, and I attribute the importance of its work in general relativity to the Hamburg group. In the covariant formulation, Singh derived the geodesic deviation equation for geodesic connecting vector, which applies whether it's a null geodesics, time-like geodesics, or space-like geodesics. And this is one of the very important equations in general relativity. One of the things it does is it results in the reciprocity theorem, which Etherington derived. A first integral of the geodesic deviation equation relates up and down area distances. And that is fundamental in cosmology. It relates the luminosity distance to the area distance. And it's a result of us observing on null geodesics. Now, there's a remarkable result of this reciprocity theorem, and that is that black body radiation spectrum is preserved in general relativity. If you set off black body radiation from a surface like the last scattering surface in cosmology, it is received as black body radiation later on. That's an exact result. And it's a remarkable link between general relativity, quantum mechanics, and statistical mechanics, because they are all involved in that result. It's crucial to cosmic background radiation observations because the cosmic background is observed as is emitted as black body to a high approximation, and we observe it as black body to a very accurate approximation. What that means is we can test the reciprocity theorem by seeing how good a black body spectrum, our observed black body spectrum, is. And so the black body spectrum accuracy is a key test of gravitational theories, because if we were to discover that there were distortions of the black body spectrum that were not attributable to astrophysical effects, it would mean that radiation is not moving on null geodesics, and that would have a very important effect on our views of gravitational theories, which would mean there was something wrong with general relativity as the theory of gravity. Now, using the geodesic deviation equation, one can do a covariance analysis of gravitational wave effects, and you can prove they're not just a coordinate effect. And Felix Pirani was the key person in this. When Einstein discovered gravitational radiation using a linear polar approximation method, there always was a problem. Are you observing fluctuations of the geometry or just of the coordinate system? And using the geodesic deviation equation, Pirani makes it convincing that it was in fact real effect. The spin 2 nature of gravitational waves come from using the geodesic deviation equation. You split up the Weyl tensor into trace-free symmetric tensors, and you get the electric and magnetic parts of the Weyl tensor. And this equation, or its generalization to non-geodesics, underlies gravitational wave detectors. Weber was the early pioneer in this. Richard Feynman played an interesting role, and Kep Thorne, of course, played a crucial role in making this all real. So it was Trumper and then Hawking who did this. The Ricci tensor is given by the Einstein gravitational equations. The matter determines the Ricci tensor. The Weyl tensor is the part of the curvature tensor which is not determined locally by the matter distribution. It cannot be entirely arbitrary because you have the Bianchi identities, which can be rewritten as the divergence of the Weyl tensor as a current term, and the current term is given from the Ricci tensor, and you can rewrite that in terms of the matter tensor. And that equation is analogous to Maxwell's equations in electrodynamics, where that's the electromagnetic field tensor and J is the source term. Thus, in a sense, one could regard the Bianchi identities as field equations for the Weyl tensor. And that is what, in fact, has been done here. These are the field equations for the Weyl tensor. Now, one of the triumphs of the covariant method is the Ray-Chowdhury-Ehlers equation. Ray-Chowdhury was amazing. He came out of the blue and developed this equation without the acceleration term, and Jürgen Ehlers' contribution was to put in the acceleration term. And this is an equation for the rate of change of the expansion in terms of the shear, the rotation, the expansion again, the active gravitational density, which is rho plus 3p, divergence of the acceleration, and the cosmological constant. That is an exact equation for the way that time-like curves move together or away from each other in general relativity. It says that shear causes convergence, vorticity can make things move apart, expansion, of course, causes convergence, rho plus 3p causes things to move together, the active gravitational mass, rho plus 3p. The acceleration can go either way, and the cosmological constant, if it's positive, tends to make things diverge. And the basic singularity theorem is irrotational pressure-free matter runs into singularity at time t0 less than 1 over h0 ago if the density of gravity is greater than 0, lambda is 0, where h0 is 1 over 3rd h0. That's the basic singularity theorem. The Ray-Chowdhury equation also applies to null curves for a light cone. This is a similar equation without the acceleration, vorticity, and lambda terms, and it's one of the Newman-Penrose equations. It results stochastics in the past null cone if the null convergence energy condition is satisfied. And these caustics are important in terms of causal limits. Now, the key thing which was discovered was the maximal extension of the Schwarzschild solution, and this is a remarkable nonlinear effect of general relativity. So you've got the Schwarzschild solution, and there's an apparent coordinate singularity at the Schwarzschild radius. Now, Birkhoff's theorem says the Schwarzschild solution is the unique vacuum spherically symmetric solution, and I emphasize this as a local result. Asymptotically, flatness is a consequence. It's not, you don't need to use it to derive it. Schwarzschild is Petrov type D, it's static for R greater than 2m. Now, this is a coordinate singularity which is not obvious. This was discovered by Eddington Finkelstein in their time symmetric asymmetric partial extension and the Kruskal-Sakaris maximal extension, which removed the apparent singularities. And this is where this idea of coordinate singularities and atlases of coordinates comes in. And then Penrose introduced the conformal diagrams and conformal infinity. So here's the Eddington-Finkelstein form. There's the Schwarzschild radius. You've extended it across in one dimension by using null rays. Your incoming null geodesics fall through the event horizon, which is here. And the key point is that anything which falls in can't get out because the light cones tilt over. Once you're here, you inevitably form into singularity. And from the outside, you can't see into the inside. All you can see is the map is way, way back, but you cannot receive any information from the inside, which is why it's a black hole. So this coordinate extends across the event horizon by using one null coordinate, but it's time asymmetric. It shows that the interior is invisible from the exterior, and there's infinite redshift. If from the outside you fall something falling in, as you see later and later from here, you're going up this world line, you receive radiation from later and later in the history of this object, and the redshift diverges to infinity. The maximal extension here is the Kruger extension. It's time symmetric with past and future space-like singularities, and it's a truly remarkable thing. If you use double null coordinates and then bring infinity to where you can see it by conformal transformation, you have the original Schwarzschild exterior solution. That and that combined in the Eddington-Finkelstein, but you add to them two other Eddington-Finkelstein extensions until you've got two asymptotically flat regions, two regions here. As you cross the horizon, the constant time surfaces are these ones here. They change from being space-like to being time-like. The constant radial surfaces of constant area were time-like, they become space-like. So you transition from being static to being spatially homogeneous. So the symmetry changes. You've got a past singularity, a future singularity. You've got two asymptotically flat domains, and you have spatial surfaces which go through a wormhole, a minimal surface at r is 2m. All of these spatial surfaces, each of these ones are equivalent to each other because there's a symmetry group about the origin which switches them into each other. So there's the minimal two-sphere there. Spatial sections are non-traversable wormholes. They're all equivalent. And two interior spatially homogeneous time-varying LRS domains. The symmetry change as you cross the horizons. It's a truly remarkable effect of the nonlinear nature of the Einstein field equations. And this is a time symmetric and spatially inversion symmetric. So we have the idea of maximal extensions using conformal diagrams and conformal infinity, which was Penrose's contribution. Maximal extension Rice and Nerdstrom was given by Carter, maximal extension Kerr by Boyer and Lindquist and Carter. The further domains, they are not physically meaningful, as Tchaikovsky says. Integration of the geodesics and Kerr fully integral due to the killing tensor, which Brandon Carter found out. And there's a remarkable paper I would like to call your attention to if you haven't seen it, Bifurcate Killing Horizons. Here, there's a bifurcate killing horizon here. And there's a general properties of bifurcating killing horizons in a paper by Robert Boyer, Geodesic Killing Orbits and Bifurcate Killing Horizons. The infinite parameter rescaling associated with Hawking radiation, affine geodesic vector versus killing vector is a completely general property of bifurcated killing horizons. And this paper is a remarkable one written by Robert Boyer. It was actually, he died in Texas during the tower shooting in Texas, and Jürgen Ehlers rewrote this paper after his death. Now, transformational thing was the Gödel solution, which has rotation. It's spatially homogeneous, it's time homogeneous, and the light cones tilt over and over as you go out. This is one coordinate system. It's rotationally symmetric about this world line. The diagram is misleading because it's rotationally symmetric about every world line. As you go out from any world line, the light cones tilt over and over until they're horizontal and you get closed time-like lines. Not closed time-like geodesic, but closed time-like lines. This past light cone goes out, it reaches a maximum, and then it refocuses inward again. And as it were, the interior spills out. And from here, you can reach anywhere outside here. because the light cones have tilted over that way. It's space-time homogeneous, axisymmetric about every world line. Rotation causes light cones to tip over, causes caustics in the past and future light cones. Geodesic complete, hence singularity free. That's a maximal extension. There's no global space-like surfaces, so there's no cosmic time coordinate, and there's no simple coordinate diagram. The discovery of solutions with close time-like lines and no global time function, this Gödel paper, led to a huge outburst of studies of causality, studies of the domain of dependence, causal fusions past the boundaries. Stable causality is the idea of there's no time-like lines, closed time-like lines, even if you perturb it, and that's true if and only if there's existence of a time function. The Cauchy hypersurface is an achronal hypersurface, which is met once and only once by all causal endless curves. There were theorems about the existence of time-like geodesics within the domain of dependence, and conjugate points occur. Geodesics are maximal geodesics up to the conjugate points, but not beyond. These are the elements out of which the singularity theorems were constructed. Very, very important. As you go down the past light cone, the null-Ray-Choudhury equation says you get focusing and focusing length to caustics and to cusps. And this is a diagram which Charlie Misner and Roger Penrose emphasized. It's a very interesting diagram. If at the past light cone here, you look round continuously in all directions in the sky and come back where you started, whoops. What happens down here is you go along, you go round, you go through the fold, you go there, you go back, you go round there. And so you do this path down here, for instance, on the last scattering surface, when you move continuously in one direction up here. That's what leads to the different kinds of effects in the source plane related to the image plane. And so you get cusps and cold in the past light cone as a result of anisotropic focusing, Penrose, Misner, and Perlich. This underlies understanding of gravitational lensing of images, strong lensing, weak lensing, and microlensing, which is a major source of information on dark matter, mass profiles, and time delays give the Hubble constant. A lot of work has been done, and it will be described by Nick Kaiser in the next talk. Now, horizons in cosmology, and there's a lot of misunderstanding about this. Wolfgang Rinde wrote a wonderful paper about this, which clarified this. Now, here we have a conformal diagram of a solution with a positive cosmological constant. It's got a future space like infinity. The start of the universe is down here in this diagram. The last scattering surface is here. Here and now is where we are at this moment. This is our past world line. Our event horizon is this past light cone here. We are here and now. Now, the particle horizon from here go down to the initial singularity, and that vertical blue line is the particle horizon. Here's the particle horizon on this side. You cannot have any causal influence reaching us today from outside the particle horizon. So here and now, this region outside the particle horizon is causally inaccessible to us. The visual horizon has much less talked about, but here's the last scattering surface. Take our past light cone, it hits the visual surface here. And this is the world lines of the furthest most matter with which we can see. And that is what we see as the cosmic background radiation two-sphere. All those images from Planck, WMAP and so on, those are images of this two-sphere where our past light cone intersects the last scattering surface. So this is matter which can influence us, but we can't see. This is the further matter we can see. That's the visual horizon. So I must emphasize the event horizon relates to future infinity. It has no effect whatever on us today. And I think some of the literature nowadays is very misleading about that. You get the idea that the event horizon is important for cosmology. The event horizon has no effect. It's going to happen in the very, very far future, infinitely far in the future. It has zero causal effect on us nowadays. In particular, it does not relate to the creation of inflationary perturbations, because the event horizon singularity doesn't relate to any event horizon which occurs down in the past, way back in the inflationary era. The only one of these things which is changed by inflation is the particle horizon. The event horizon is unchanged by inflation, the visual horizon, but if inflation takes place, this surface here moves way, way back down. Oops, sorry. This surface here, the initial singularity moves way, way back down, and the event horizon, the particle horizon moves out. That's what inflation does. That's how it solves the horizon problem. But the event horizon isn't changed, and the visual horizon isn't changed by inflation. Now, an interesting question, given these limits on what we can see, is the universe spatially homogeneous? It is spherically symmetric about us, that's well established, but is it spatially homogeneous? We could be at the center of the universe, even though that may be something that we don't like to think about philosophically. Now, you can test that via source counts, but you run into a key problem of source evolution, and that actually makes it very difficult to prove that the universe is spatially homogeneous by looking at source evolution. A major theorem about this was the Ehlers, Guerin, and Sachs theorem. Isotropic collision-free radiation everywhere implies spatial homogeneity. So if you could prove that the cosmic background radiation was isotropic everywhere, that would prove spatial homogeneity. This is a stable result. There's an almost EGS theorem, which Sturger, Martins, and myself proved. And so even if there are fluctuations in the cosmic background radiation, this remains true, but it still depends on the Copernican assumption. We're assuming here that the cosmic background radiation is isotropic everywhere else. Now, some very interesting work has been done, a series of tests, direct tests by Martins, Clarkson, and others, by which we can actually prove that the universe is spatially homogeneous. And the key one is use of the kinematic Sunyaev-Zeldovic effect, which tests the interior of the pulsed light cone and in fact confirms spatial homogeneity. Many of you might think this isn't worth looking at, but spatial homogeneity is the foundation of cosmology, and it's very worth testing. Now, the singularity theorems. Is gravitational collapse singularity due to symmetry? In 1965, Penrose's use of topological methods to derive his singularity theorems via closed trap surfaces was a transformational thing for general relativity theory. It led to their extension to cosmology by Stephen Hawking. As Senavidia said, Penrose wanted to prove that deviations from spherical symmetry were not able to prevent the formation of singularities, which many people had suggested, particularly some of the Russians. So in Oppenheimer's Schneider collapse, you could prove there was a singularity, but within general relativity was this result just of the spherical symmetry. What Penrose introduced was the key role of inequalities, energy condition inequalities and trapped surfaces. And that's transformational because you change from equalities to inequalities means your results are very generic. Careful study of causal domains, which, as I said, had started already with the work of Gödel, but now Penrose's work led to a very, very detailed study of causal domains. Singularity was defined as geodesically incompleteness, and that was the strength of these theorems because they could be proved, but a problem with the theorems because they did not prove that the energy density diverged. They didn't prove that any scalar quantity diverged. Now, one can see the existence of trapped surfaces already in the Kruger diagram. A trapped surface is a sphere or compact surface on which both the ingoing and outgoing radiation two spheres have smaller area than the source two sphere. Now here, in the interior, these are surfaces of constant radius. Here's R is 2m, R is less than 2m, and here's R is 0, where the singularity occurs. So here is a closed trapped two surface because this has got a certain radius here, which lies between 0 and 0. As you go on the outgoing and ingoing, well, the null curve going to the left and the right, the radius you're coming to is to that surface, and R is less on that surface than on this level. So it's already visually immediately apparent that there are closed trapped surfaces in the Schwarzschild solution if you look at this Kruskal-Zakaros diagram. Here is the transformational diagram which Roger provided. You've got matter collapsing to form to a central core, You want to know if that's singular or not. You've got the Eddington-Finkelstein effect here. The outside observers can't see into the interior. And Roger said, okay, suppose there's a closed trapped surface, then the future of this point is limited to lie between here and here, and that leads to a singularity here. I'm not going to go into any of the details, but this was his basic singularity theorem, a transformational thing for general relativity. It centers on this idea of the closed trapped surface, which is an inequality, therefore the result is stable. It depends on the convergence conditions for null GD6, which are inequalities and therefore generic. And it depends on some global assumptions about causality. In this case, he wanted to be a Cauchy surface, but there have been many other ones in which those results are weakened. So this is a closed trapped surface to the future. So if the space-time contains a non-compact Cauchy surface, sigma closed future trapped surface, if the convergence condition holds for null vectors, then there are future incomplete null GD6. Given this, you've got the Schwarzschild solution and the Kerr solution as being plausibly the endpoint of gravitational collapse. And is that in fact true? So then there was study of his distance and uniqueness theorems, and Werner Israel published a remarkable theorem. The only static vacuum black holes are the Schwarzschild black holes, and hence are spherically symmetric. Unlike equilibrium matter objects, it was not possible to find a static black hole with a quadrupole moment, for example. Israel came out of the blue and produced this existence theorem, which was a stunning result. There was then a whole set of results of the uniqueness of the Kerr solution. Uniqueness of Kerr produced by Carter, Hawking, Robinson, and also a series of no-hair theorems for collapse to form a rotating black hole. Doroskevich, Zeldovich, Novikov, Price, and Wheeler, for example. Wheeler coined the phrase, the black hole has no hair. And part of this series of theorems were the area theorem and the black hole thermodynamic results, Hawking, Bekenstein, Bardeen, Carter, Israel, which is the basis for Hawking radiation results later on. Penrose discovered the ergosphere. In the case of the Kerr solution, there's a change of symmetry from spatially homogeneous from static to spatially homogeneous. And then there's the event horizon, and between them there's a domain which you can go into. You can sample the change symmetry and you can get out of again. And that resulted in the Penrose process. Objects can emerge from an ergosphere with more energy than they entered with. The extra energy is taken from the rotation energy of the black hole. Therefore, the rotation of the black hole slows down. And this process, the variation process, now is understood to be it's been transformed into the Blandford-Zanayak effect, which is considered a likely mechanism for enormous luminosity and relativistic jets of quasars and other active galactic nuclei. A very, very important result in astrophysics. Stephen Hawking said, well, let's do this in the past. Let's reverse it. Let's look at cosmology. Let's go backwards in time. And in fact, it was well known in cosmology that there was a surface of minimum angular diameter. If you follow the null cone back before that, you have closed trapped surfaces going backwards in time in cosmology. So backwards in time, you predict the existence of a singularity by running basically the same proofs backwards in time. And so Stephen proved a series of papers applying similar methods in the past direction of time. And he and I proved that the existence of the cosmic background radiation by itself was sufficient to cause this refocusing. Now, part of this huge development which was taking place was perturbation methods. And these have to be treated very carefully because of the nonlinear nature of the field equations. Systematic perturbation methods were developed firstly for the binary pulsar. The binary pulsar was observed and it was seen to be slowing down decay of the orbitational period. This was interpreted as the emission of gravitational waves, but there was a huge debate at that time about the perturbation methods used. The formula for emission of radiation was known for a very long time before, but people like Jürgen Ehlers were very, very worried for precisely this question. Were these were these variations in the coordinate system, roughly speaking, or was this really, was the gravitational radiation emission formula a genuine formula? This was resolved by an ongoing debate between a whole group of people at that time and confirmed the binary pulsar result, which of course led to the Nobel Prize for Hulse and Taylor, because this was the first confirmation of the existence of gravitational radiation. Perturbations in cosmology. There were two key pioneering papers. Lifshitz, the pioneering general relativity structure formation paper in 1946, I think it was. And then Sachs and Wolf, the pioneering cosmic background radiation anisotropy paper. It's an absolutely remarkable paper, this one. Ray Sachs is one of the geniuses of general relativity. He's played a key role in various ways, and this was one of them. Since then, there have been many, many structure formation studies, Peebles, Rees, Evstafio, Silk, many, many other people, which have led to our current understanding of the formation of structure in cosmology and its effect on the cosmic background radiation. But underlying this was the gauge issue, and the gauge issue is how to eliminate gauge modes. In cosmology, in cosmological perturbations, you've got your background model and the perturbed model. And the question is how they relate to each other. And what can very easily happen, and did happen in the early studies of these cosmological perturbations, people were producing gauge modes, which are basically just the coordinates were oscillating, and you had to somehow get rid of those gauge modes. And this was done in various ways by very, very careful studies of coordinate freedom, which Sachs and Wolf did. They did very careful studies of what the coordinate freedom did, and then deduced what the real modes were. But what one needed was to deal with the gauge issue in a more direct way. And Jim Bardeen wrote a key paper there in which he deduced a set of gauge covariant variables, which are very, very widely used nowadays to study perturbations in cosmology. Stephen Hawking used the 1+3 covariant processes to get covariant equations for gravitational perturbations, including the electric and magnetic part of the Weil tensor. He got this right, except his density variation, he didn't do that right. And this was corrected in later papers by myself, Bruni, Dunsby, and Tony Huang. And for the cosmic background radiation, a development of those methods, which I developed with Travis, Gebbie, Martins, and Sturger. And this then was developed by Lewis, Challoner, and Lazenby to give the CAM codes. And you can do all of this in a completely gauge invariant way, using gauge invariant and covariant variables. And I prefer those because they are so geometrically clear. Now, there was then quantum field theory on a curved space-time with the seeds of structure formation. The basic result, particles can be created by time-dependent gravitational fields or by time-independent gravitational fields with horizons. Starobinsky, Parker, Birrell and Davies, Fulling, and Bob Walt. And this is the basis for Hawking radiation, consistency with black hole thermodynamics, and it's the basis later on for the inflationary perturbations and structure formation in cosmology. Then there's numerical relativity, where we go beyond linearity. The evolution formalism for the GR field equation was set up by the ADM, Arnowit, Days, and Misner, using a lap function and a ship vector to relate quantities on successive surfaces of constant time. And the key application was the black hole binary emission of gravitational radiation using higher order perturbation theorem and the initial inspiraling phase and numerical code for the later phase. Very, very complex numerical codes based on generalization of the ADM formalism, but using Newman-Penrose formalism to interpret the results, creates templates to detect and parameterize black hole binary mergers with a gravitational wave emission. Finally, some outcomes and issues. This all laid the foundations for Hawking black hole results, inflationary universe models, gravitational lensing, and the wonderful developments in gravitational radiation detection. Key points. Black holes as a major part of astrophysics, powering quasars and creating jets, also emitting gravitational waves. Gravitational wave detection as an important part of astronomy. Gravitational lensing also, I should add in there. But the final ironic point, we don't know if the universe had a start because firstly of quantum fields, the equations which lead to inflation violate the energy conditions, and so they undermine one of the foundations of the singularity theorems. And in any case, quantum gravity takes over, and we don't know what the quantum gravity result is, what the quantum gravity theorem is. So we still don't know if the universe had a start, despite the Hawking theorems. And then conversely, of course, the same applies to gravitational collapse. It's not clear what happens at the endpoint of gravitational collapse either, for the same reasons. Standard cosmology has many issues to solve. Inter alia, we have a real problem if dark energy has W less than -1, because then there's a negative inertial mass density. And one of the key things in cosmology, which I think is a scandal, we don't know how quantum fluctuations at the beginning of inflation became classic. And decoherence does not solve this. This is one of the big problems, issues in inflationary theory. I'm going to make a provocative statement. I don't believe that any of ADS-CFT or ER equals EPR or traversable wormholes or Boltzmann brains refer to the real universe. I do not believe in the wave function of the universe, the Wheeler-DeWitt equation, or the Everett multiverse. And I'm probably treading on some toes here, but I'm just stating my own viewpoint. I suggest there are important lessons for quantum physics in the idea of local coordinates in an atlas. That key idea, I think that is central to the developments considered here. I think that this can apply in quantum physics. I believe considering local wave functions everywhere is the way to go in quantum physics. And that relates to some of these issues, like, for instance, the quantum information paradox, so-called. It's all related and affected by this result. So these are the results which I wanted to talk about.
Thank you very much, George. We already have 2 questions. I'll start off with Yunje Ma. Sudan, maybe Yunje is unable to unmute himself.
Hello?
Yes, I've just enacted that.
Am I audible? Hello?
Yes.
Yes, you are now. We can hear you now, Yunje.
Okay, great. Thank you. Thank you for giving this opportunity. Hello, George. Thank you for the very nice talk. And hi, hello. Yes, long time no see. And I'm very excited for it. But I want to just correct for 2 things, if I understand correctly. One is about event horizon. So what you said is event horizon has nothing to do with the current structure of space-time, or for the current physical consequence of space-time, which
in cosmology, yes.
Yes, but actually, so if you could, so actually, I think what event horizon is actually it defines a distance where above which, if a galaxy emits a light by now, that we will never receive it in the future. We will never receive it. That is due to due to dark energy. If there's no dark energy, then there's no event horizon. So I think the event horizon should not define at infinite future. It should define at present time, where it defines a scale above which we will never have any communication whatsoever in the future. So I think that should be, I mean, instead of having a big light cone, past light cone, defined top to kind of in the infinite future, I would suggest to having a horizontal line at current time in your space-time diagram that stretching horizontally to a distance where that defines the event horizon. So if I compute it, the event horizon by now is corresponding to a redshift 1.8. It means that a galaxy at a spatial distance 1.8 above that away from us, if they emit a light by now, we will never receive it in the infinite future. So that is my comments for the event horizon. If you
so you want to redefine the event horizon. You're introducing a non-standard definition of event horizon.
George, I think that is pretty much a standard definition. I mean, perhaps this is a bit more in detail. I can exchange the email with you later, but I think that is pretty much a standard definition of event horizon in cosmology, which is really about the horizon above which, if a galaxy emits light, we will never receive it in the future. Okay, so that is one thing. I can send you an email if you wish to illustrate what I mean. Yeah, would that be okay?
Well,
yeah.
Okay, I use the definition of particle horizon, which is given by Wolfgang Rindler in his very, very clear paper. For the event horizon, you have to have the past null cone is a causal horizon. If every event, a past light cone is a horizon for that event. So we know that.
Yes. So I don't completely disagree. I agree it is a past light cone, kind of light cone defined in the infinite future, but it should intersect it with our current 3D spatial slides.
Our current 3D spatial site is completely non-observable. It has zero relevance to observations. You cannot see what is happening on our current 3D. It has absolutely zero relevance to observations.
No. Yes, what I mean is not about observing it now,
Yeah.
but observing in the future. Okay, so we can discuss that a bit later. I see a few hands up, so
Yes, I think. Thanks very much for that interesting input, Junje, and I think we should move on.
May I just add in one sentence, Roy?
Junje?
May I just add in one other thing? Yeah.
Actually, let's come back to you at the end if we can. I see Martin has a.
Please send me an email with a paper about it. But my comment is that the surfaces of constant time in cosmology have nothing to do with anything which can be observed, and they have zero relation to us causally because they are spatially related to us, and so they have zero effect to us at the present time.
Yeah, I don't disagree, but it's about future observations. Okay, we can discuss that later. But I do have another comment, maybe after Martin. Yeah.
Martin, please go ahead.
First of all, I would like to thank you for a really beautiful and comprehensive discussion of this exciting period in the history of general relativity. I would like to ask you a little about coordinate-free methods and that kind of thing. So I guess if we look in the mathematical community, I mean, a lot of these ideas were developed in the late 19th century, the papers of Cartan and, the exterior derivative and Whitney and Whitehead with the notion of atlases and, a sort of formalization of a differential manifold. So, I mean, could you maybe explain how that sort of played out and what the relationship was between the sort of mathematical work and the, later application to GR?
Well, I try to indicate that it played a key role for me in terms of the symmetry groups. It was far easier to, for instance, in the Bianchi cosmologies, the easiest way to do it was to consider the commutators between the killing vectors and the tetrads, and the killing vectors and tetrads commuted with each other. To write that out is just far easier if you do it in a completely coordinate-free kind of way. It's the idea of atlases, yes, it was developed by that community, and in some sense, it was discovered by the relativity community, in effect, without formalizing it until much later, when it was formalized in, or for instance, the book I wrote with Stephen Hawking, and it was implied in Roger's work. But for instance, the Eddington-Finkelstein extension was using this idea of atlases. Yeah, I think in a sense, part of the idea of a generalized basis, it just made everything so clear. So at some level, it provided the background in which one could very, very clearly think, well, will I use a coordinate basis? Will I use a null tetrad basis? Will I use a orthonormal basis, and so on? And you could just think very clearly and see how it would make the difference if all of this took place. Incidentally, there was a wonderful book, Schoutens' book, Ricci Calculus, was one of the books which we referred to, which had a huge amount of information about the use of general bases, and it introduced an idea which Penrose talked about much later on, abstract indices. And Schouten wrote a lot about the idea of abstract indices, which was quite interesting.
Thank you, George. I think we have time for one more question, maybe two if we're lucky. And the next in line is Saikat Chakraborty. Your question, Saikat?
Yeah, hello. Can you hear me?
Yes.
Yes. Yes.
Yeah, I have already written my question in chat, if you can see. But again, let me restate it. So I wanted to ask whether it is possible to apply the dynamical system approach to find asymptotic states in astrophysical scenarios. For example, in a gravitationally collapsing cloud, because in cosmology usually we work with homogeneous models, and we get a set of evolution equations. But here, if we use even the covariant formalisms, we can get a separable set of a set of evolution equations, a set of propagation equations, and some number of mixed equations. So can we use the dynamical system approach to find the, end state of collapse or something like this?
Sorry, Roy, that was breaking up. Roy, tell me what I must answer.
What, sorry?
Sorry, I'm asking Roy, you were breaking up. I'm asking Roy to just...
So, George, if I understand correctly, the question is whether one can apply dynamical systems methods to inhomogeneous scenarios such as a collapsing matter cloud under gravitational instability.
Dynamical inhomogeneous scenarios, yes.
Yeah, yes, so the dynamical systems have been used for some inhomogeneous models. It's just that the most development has taken place in the case of the Bianchi models. And there's a book which I edited with about this with John Wainwright, which talks in great depth about this. And I think, I can't even remember now, I think there is one inhomogeneous model chapter in that.
Okay, so you can apply the dynamical system approach in that case.
Yeah. The dynamical systems are great because you see a whole family of solutions all in one go, and so it's very nice from that viewpoint.
Okay, yeah, actually I was trying something in that line, and thank you for the reference. So I'll take a look at that. Okay,
thanks for your question, Saikat. We have 2 minutes, so if there's one brief question, Rahul, you were next in line. If you could make it very brief, please. Rahul,
yeah, hi, Professor Ellis. Yeah, hello. Thank you for this wonderful talk. So my question is regarding the black hole horizon. So under what condition the black hole killing horizon can be different from the event horizon? And one of them, which of them is truly responsible for the Hawking radiation? Because generally we define surface gravity in terms of the killing vectors.
There's a huge literature on black holes, the relation between the event horizon, the parent horizon, ingoing and outgoing trapped surfaces. There's a large, very large, very interesting literature. I didn't mention that very much. A lot of that happened after the time that I'm talking about, and it's an ongoing debate, and it's related to the issue of the cosmic censorship, which I didn't say a great deal about, because again, a lot of that took place after this time that I'm thinking about. So, but there is a lot of literature on the relation between the trapped surfaces, the local definition. One of the problems with the original definition of a black hole was that it involved infinity. It involved the idea of whether information would precede infinity, and we rather would like to have addition which applies in astrophysics, and that means you don't need to talk about infinity. It should be local, and there's a whole literature about that. Ashtekar is one of the people who's written a lot about that.
Right. Well, thank you very much, George, for the talk and for engaging with the interesting questions. Unfortunately, due to time, we have to move on. It's a great pleasure to introduce our next speaker, Nick Kaiser, who also is a PhD graduate of Cambridge and whose supervisor, Martin Rees, was a student of Dennis Sciama, as was George. So there's an interesting connection there to Dennis Sciama. Nick Kaiser is very well known in the cosmology community for being one of the, if not the founder of the science of galaxy surveys, not just in terms of clustering, but in terms of lensing as well, which is the topic of his talk. And like George, he's the winner of numerous prizes and awards. It's a great pleasure to have you, Nick. And we'd be pleased to hear your views on the history of gravitational lensing and cosmology.
Okay, can you hear me?
Yes, perfectly.
Good. Now I'm trying to share my my keynote thing, and I don't see it. Just bear with me 1 second. What's happening?
Do you have a share screen?
Yeah, it's offering me. Now I see it. Now I see it. Perfect. It was hiding. All right. So let's see. I want to go into. Unfortunately, the bar that I have for sharing screen is covering up. No, that should be it. You see my title slide?
Yes, that's perfect, Nick. Thanks.
Excellent. Okay. Thanks very much for the organizers for inviting me to this exciting meeting. Too bad we can't all be there in person. Maybe next time. So I'm going to talk about history of gravitational lensing in cosmology. So I think the first the sensible discussion of gravitational lensing in cosmology is this gentleman who probably worked on it when he was in confinement. And you know, in his books on optics, he starts with a set of 30 or so propositions that he calls queries. And the very first one is this one that I've highlighted here, which is, do not bodies act upon light at a distance and by their action bend its rays, and is not this action strongest at least distance? Another query he gives is the proposition that light is particles. Right? It's well known that he took the particle rather than the wave view. And combined with the knowledge 30 years old then that the light moves at the speed 3 × 10⁸ meters per second, he would have been able to calculate deflection of light, so on. Now, as a bit of an aside, you know, given that this history of lensing in cosmology, you might wonder why he didn't go further with this. So what I have in mind here is this statement by Milner McRae, who, after the development of FRW models, said all of this could have been done by Newton, right? And the question is, you know, why didn't he do it? And what they have in mind is that, you know, Newton could have analyzed a uniformly expanding dust sphere. He would have obtained Friedmann's equations. And the key thing is that the radius of the sphere wouldn't have entered into any of the locally measured quantities, right? So you could take R to it to infinity. And the reason he didn't is revealed in some correspondence with Bentley, where he, it's in this quote below, where he's saying, yes, locally, in an infinite universe, locally things will collapse. So it's amazingly prescient. He's doing gravitational instability, but he refuses to accept the idea that the overall background, as we call it now, would be dynamical. He's, what we'd say in astrophysics, that he's invoking Gene swindle, right? And he admitted to being, you know, not too happy about this, but it's a missed opportunity. Nonetheless, a little bit later in the 18th century, Mitchell and Laplace applied Newtonian theory, asking how big a star would be big enough would stop light escaping from it. That's not what we're talking about. But start of the 19th century, you've got Cavendish here and von Sollner, who applied Newtonian theory to calculate the bending of light by the sun. There's a bit of controversy here as to whether von Sollner actually got the relativistic factor 2. It has to do with the figure at the bottom right there, where there's some confusion as to, in the literature, as to what angle he was actually talking about. Is it? But I don't believe he got the relativistic factor 2, right? These guys predicted 0.84 arc seconds deflecting, and the calculations, you know, very simple. You just say, what would Newton have got for the deflection of a particle, a test particle moving at the speed of light past a mass with the mass of the sun? Now, as another aside, now we're in the 19th century, middle of the 19th century, you've got Maxwell, and, you know, Heaviside translated him for us to the form of the equations. And you might ask, well, why didn't Maxwell do gravity and this kind of thing? And Maxwell never really got started with gravity. And it's a shame, because electromagnetism, it's a field theory, it's causal, it's relativistic, it involves gauge, and so on. What tripped him up, he got the stress tensor for gravity. This is in the his Encyclopedia Britannica article. And it's the correct stress tensor. But then he worked it out, and he realized that sitting in his room, there was a momentum flux of 32,000 tons per square inch. And he said, I do not think space is strong enough to withstand such a stress. Because you've got to remember, his mindset was, you know, that he didn't really get rid of action at a distance. He believed in lots of little actions. He believed in the underworld with cogs and gears or some kind of mechanism that transferred momentum. And so this kind of momentum flux, he just threw up his hands in horror. But, you know, if you look at least in weak field gravity, you know, it would have been a relatively minor advance for him to develop a relativistic weak field gravity, but it didn't happen. We had to wait until the start of the 20th century and Einstein, and then there's a rapid sequence of events. Around about 1910, he's thinking about principle of equivalence, and he predicts 0.84 arc seconds for the bending of light by the sun. And there's controversies around this. And there were two experiments to try and measure this, both of which failed, which is good because they would have proved him wrong if they'd have succeeded. And in 1915, he publishes GR paper, more controversy, but now it's got this factor too, that the light bending by sun is twice as big. And we all celebrated a couple of years ago the centenary of Eddington's trip to measure this in Principe, and Einstein became world famous. So, you know, what actually happened in that brief period between 1910 and 1915 for him to get it right? So he starts off apparently stimulated by reading about a tiler falling off a building and thinking, well, yeah, as he's falling, he doesn't measure gravity. Gravity and acceleration are equivalent. And then, you know, he can modify the metric of special relativity to include a warping of time, right, as indicated there. And that allows you to explain a lot of phenomenology of gravitation, why things move on parabolic paths if you throw them, and it predicts the gravitational redshift. And from the gravitational redshift, he gets the light deflection. And the argument here is that as the light goes deeper in the potential, its frequency increases, so its wavelength shrinks, so you can figure out how much light is bent. You get Snell's law, right? You could also get this by thinking about an accelerated observer on the surface of the sun. What would they see for the deflection? Right? That's where he is in 1910. By 1915, I don't need to explain to you, this audience, that he's developed the field equations and so on, beautiful parallels with Newtonian gravity. And now if he does weak field gravity, he gets this, what we call the Newtonian limit or weak field metric, slowly moving sources, and so on, where now, as well as the warping of time, there's the second term is the warping of space that appears, and that changes the geodesic equation, now gives twice the deflection. Now, cosmologists use a sort of optical, an analogy that the universe is just like lumpy glass, right? That if you've got this weak field metric and you ask, well, how does light particles move, they're null particles, then this is their coordinate speed of light varies from place to place. And so you say that's like an inhomogeneous medium, or, you know, say radio waves in an inhomogeneous plasma or something like this. Maybe that's not a very good analogy, but anyway, you know, well known, we know how light behaves in glass and so on. And so from that, you get Snell's law. I always get called up called out in France for not referring to Descartes, who they attribute Snell's law of refraction to Descartes, but I always reply that in fact, it was Ibn Sal who did it in the year 984. Anyway, what you get is a law for how rays are deflected with the factor 2 in it. So twice what Newton would have obtained. There's a warning here, though, that, you know, this seems like a nice, simple analogy. We all like analogies, but at a very basic level, it's terrible, because in glass, the speed of light varies from place to place, but the frequency is fixed, right? If you're inside a swimming pool and you look at light from the outside, there's no red shift or blue shift. Whereas in gravity, it's the opposite. The frequency changes because of the gravitational redshift or blue shift, but everyone measures the same speed. So you have to be careful with this. So what are the observables that you can measure? The most fundamental one is the gravitational time delay. So here's Shapiro's formula. And you actually measure this along with the geometric delay in strong lensing with multiple images of quasars, and George mentioned this before. I want to mention the paper by Blanford and Narayan, which for, I think, a whole generation of us in lensing were stimulated by that particular paper. It's so beautiful. And if you haven't read it, I strongly recommend it, where everything starts from the time delay surface and you derive everything from that. The next thing you can get is the light deflection if you integrate Snell's law. And this is going to be very important in the last part of the talk, is the light obeys has a random walk, and so you've got to add in quadrature the effect of different deflectors along the path. And then this is sketched here. Well, then you can ask, well, given what we know about large-scale structure, what dominates the deflection? And it turns out to be supercluster scale structure, things as 30 megaparsec scale, give or take. And they produce deflection of about 10 to the minus 3 radians, so it's somewhat hard to observe. And then what is more directly observable is if you now take the derivative of the deflection, you get a 2x2 tensor, which describes things like the magnification of images and the distortion of their shapes. And this has got a very different dependence on scale. This is quite weak at large angular scales, at degree scales for sources at redshift 1, it's about 1%. But if you extrapolate down to smaller scales, it gets bigger and bigger. And it was George, again, who was really, held our feet to the fire and said, you should take this seriously. For all you know, this blows up in your face. And we'll come back to that later. So here's a non-complete list of some of the applications of lensing in cosmology. I'm just going to talk about a few of the ones that I've highlighted, but in bold-face there. So strong lenses, first one was found when I was a student, and it was very exciting. And 2 images, there's actually 3 images, separation between there's a close pair, and the third one 6 arcsecond. And from that, you can do things like measure the mass of the galaxy. And as was pointed out by Revstal previously, because the background quasars varying with time, you can measure the light travel time distance. And that's on the order of the deflection angle squared divided by h0. So it's a path to the Hubble constant, though a somewhat uncertain one. What about the weak lensing was really started off by a fantastic paper that I'll mention at a few points going forward by Zeldovich in 63. And there's just a throwaway comment at the end where he has beautiful little sketches showing how galaxies will be distorted. Though for the most part, it was concentrating on how the flux densities of things will be affected. Rachel Webster thought about how the shapes of galaxies will get more and more distorted at higher redshift. That's not really weak lensing, which is simpler. It's a sort of linear probe. And it was in the mid-80s that really Tony Tyson and his group started presenting results on weak gravitational lensing. There was another weak lensing result, which was quasar-galaxy associations. So this was an exciting time. Very little was known about the large-scale structure of the mass around galaxies or on larger scales. And what was particularly exciting, that these 2 probes seemed to give contradictory results. So the, oops, I can no longer advance my slides. Roy, can you hear me?
Yes.
Ah, that's good. So we're still connected.
You're still connected. You can still see the slide, early days of cleansing.
Okay. This is annoying. The screen is completely frozen.
Try restarting the share.
Yeah, unfortunately, I can't see my cursor. I don't know what I can do. This thing is completely frozen up. Any suggestions? Control keys.
I have a backup copy of your slides. Maybe I can try sharing that, and you can just tell me where to advance it. Maybe
I'm going to try and rejoin the meeting.
Okay.
I see you're back with us, Nick. You are muted. Sudan, can you unmute Nick for him?
Okay, I'm unmuted. All right, let's try again. Something a bit nasty happened because
there we go.
Right, I think I'm not going to go to full screen because that was may have been causing the problems. So what are these early days? Quasar Galaxy Association, Claude Canizares and John Peacock wrote the first couple of papers on this that I knew about. What happens if you've got a quasar that you see through the halo of a galaxy? And naively you think, well, the galaxy's going to lens it, amplify it, make it brighter, so I'll see more of those things. The reason was that there were, quasars were thought to be cosmological distances, but there were some cases where they seemed to be associated with foreground galaxies. And the people who pointed that out were considered cranks in the community, but they were right. What they were seeing was this gravitational lensing effect. The theory here is that, yeah, lenses will make things brighter, but it's a little subtle what you actually see, because the way sources get made brighter is by magnification, then that dilutes the number of density of sources on the sky. So you see fewer faint sources and more bright sources. And then that was the prediction. People measured it, and they measured what seemed to be about a factor 3 larger than we believed to be realistic. And then the cosmic shear, CCD devices had been invented, and so people were starting to do relatively wide field astronomy, and it was Tony Tyson's group that pioneered this, and they in '83 they produced a couple of papers. One of them is illustrated at the top, which is measuring what we'd call cosmic shear, measuring the mean polarization of sources in a set of, I think, 30 or 40 different fields. And they got a null result, not too surprising, but bear in mind there was a great deal of uncertainty in what the large-scale structure was. The other thing they did was galaxy-galaxy lensing, which is the lower plot, where they got a null result too. But here, the dashed lines, actually the lower dashed line shows the prediction, a pretty realistic prediction. And so here, the lensing seems to be giving a lower mass than we thought was there. This all got sorted out. But the next thing was moving on to clusters of galaxies. About 5 years later, '89, Tony produced this paper where he made very deep images of the cluster Abell 1689, subtracted off the red foreground galaxies from the image and looked at the ellipticities of the background galaxies, and did a very sort of ad hoc modeling, which came up with this image at the bottom. And so this was, I can't overestimate, how exciting this was and what a huge impact it had. What was clear was that this was a signal coming from the bulk of the background galaxies being distorted. And big deal, you might say, we knew that was going to happen. But you could then extrapolate and say, well, what would I see on larger scales? This was an existence proof that proved there was high signal to noise to be had on large scale. The questions were numerous, though. What was this colorful image actually measuring? Surface density, projected potential? Who knew, right? And this null result for galaxy-galaxy lensing, that was revealing a problem with calibration. All of this had to be figured out, and was done so in the next few years. So I worked on some various parts of this, understanding what was being measured, inversion techniques, how you would make a properly calibrated mass map, how you would apply this to measure the power spectrum of density fluctuations. And as you know, this has produced lots more things. Here's a state-of-the-art example by a postdoc at LPNS, produced just recently from the Dark Energy Survey. And the next decade is going to be a golden age for this, with things like LSST, Euclid. Tony deserves all the credit for just having hammered away that we need dedicated instruments to do this properly. And a little bit later, we will have the SKA. So now I'm going to do a little intermission and make this a bit more interactive and have a little quiz. I hope this will work. I set this up with Sudan earlier. So far, I see the quiz, that's good. So far what I've told you is a bit disappointing for GR theorists. It takes you years to learn GR, and then for lensing, it seems you can get everything by using Newtonian theory and just adding a factor 2 for relativity. And I already pointed out some of the dangers of this, but let's just pose a little quiz here. So 1915, Einstein's prediction is twice Newtonian for the sun, and guess what? Eddington confirmed it. Well, what if you were to actually measure the bending of a horizontal light beam while sitting on the Earth? right? What would you measure? So the options are twice the Newtonian prediction, something else, or something that's, when I've tried this before, some people say, I don't like this question. It's ill posed or something. So go ahead. Hey, this is cool. We don't have that many. Oh, 14 people, good. This is anonymous, by the way, so don't worry. I'm not going to share the grades with anyone. We're up to 24. Last few seconds, anyone who's indecisive, make up your mind, because I'm going to close the poll in a few seconds. I think we're sort of converging. And this is very interesting. So we've got the highest ranked is the Newtonian prediction, and that's the right answer. That's the answer Einstein gave in 1910. But notice it's not trivial, right? You guys are experts on this. How do I get rid of the poll? It's not that many fewer thought the answer was the 1915 result. And interestingly, just want to get rid of that window. Sudan, can you get rid of it? So if we have time, we'll come back to that right at the end. Probably won't. Unfortunately, it's blocking my screen. We should have tested this.
Is it still there?
It's still there, unfortunately. Maybe I have to stop share and start share. I got rid of it. I'll start sharing again. Sorry about that. Interesting. So good. The majority, the highest ranked, but not an overall majority, got it right. There's another question I'd like you to think about, and this is this famous 63 Zeldovich paper, where I think he's the first to calculate or to draw these cone diagrams. So you think about an observer and a bundle of rays going back across the universe to a distant source, and ask how that bundle gets focused or defocused. At the bottom of these pictures he has at the end of how circular galaxies would get distorted. The left-hand plot at the bottom is cosmological distances and so on. But what everyone calls this paper is it's Zeldovich's empty beam calculation. He said, what if we looked at a source, but there wasn't any matter in the beam? And he convinces us that there would be no focusing because there's no matter in the beam. This raises an interesting sort of question. Here's a sort of an illustration of what he has in mind. And what I'll ask you later, if we have time, is this a case where this Newtonian ×2 works, right? If you were to imagine firing non-relativistic test particles up this evacuated tunnel, this is the empty beam in an otherwise homogeneous universe, would there be a gravitational field? Would it cause those test particles to diverge? And would light particles be the same, putting in V equals C and just cranking up it by a factor 2? So it's Geraint Lewis who posed this problem to me. this sort of strips it down to the minimum. But let's move on. Just think about that if you find the next few slides a bit boring. I want to talk about another historical story that started with that paper by Zeldovich. Right, so here's the Planck sky map, and from which we conclude that for any sensible H0, we live in a spatially flat universe. But in making that kind of cosmological parameter estimation, we're assuming that we're looking at a surface at a distance from us, which is given by the mean distance for the redshift at which we know the CMB was released. The other thing, pillar of cosmology, is the Hubble diagram for supernovae 1a, which again, in a similar way, assumes that there's no bias from lensing. So the question now is, well, is there a bias? I mean, so what we're talking about is things like angular diameter distances and the CMB, luminosity distances for supernovae. And I think most people would accept that these, with lensing, with structure and the associated lensing, these things become random functions of position on the sky. Things can be amplified or de-amplified. The question here is not that, it's whether there's a bias, right? Does the emergence of structure in the universe bias these distances, right? And Zeldovich, very quickly, Zeldovich was arguing, yes, if you look at things, see things along empty tubes, right? And the way he gets this, or one gets it, George introduced Ray Chowdhury's equation, comes very directly from the machinery, basic machinery of differential geometry, that you can measure what is in fact the enthalpy, this quantity here along the line of sight, skipping forward rather quickly. I don't have time to talk about some of the rather interesting issues cropping up here, but this seems to say, well, if there's no matter in the beam, then there won't be any focusing. And 64, Feynman gives a talk on this at Caltech, didn't write it up, but Jim Gunn, who was in the audience, did, and came to similar conclusions. Ron Kantowski, 69, Swiss cheese models. Charles Dyer developed this further, put in a cosmological constant, and everyone up to this point is singing the same song, that the emergent structure in the universe is going to make things look a bit fainter. And then there's an important paper by Weinberg where he pulls the rug out from under everyone's feet and claims that at least if the lenses are transparent, there won't be any effect. And his argument's very simple. He says, put a source at the origin of coordinates, think about observers on a shell who see that source with a given redshift. They've all got telescopes. Some of them see the source brighter, some of them see the source fainter, but conservation of photons, the photons have got across that surface. So on average, the flux density can't be biased. Okay, end of story, you might think. Weinberg's a smart guy. Not quite. Peter Schneider, working with Jürgen Ehlers and his student Stella Seitz, came up with a couple of theorems, one of which is very interesting, which is the focusing theorem using Ray Chowdhury's equation and showing that actually structure in the universe is going to make things look brighter. So what are they doing? We've got an equation here. Consider this a bundle of rays going back from your telescope across the universe. It's got some area A. Take the square root of that, call that D. D obeys this equation, right? R is the Ricci focusing. It's the matter in the beam. So you might think of it as being the mean matter with some fluctuating part. And if that's all there was and the fluctuating part averages to 0, you wouldn't get any bias. You'd be able to use the homogeneous universe. But there's this extra term, right? This looks like, well, I won't say what it looks like. So this term is the rate at which the ellipticity of the beam is changing squared. So it's a positive thing. And that's what gives you the bias they're talking about. And if you estimate roughly what it is, it's big, because it goes like the mean bias in the distance goes like the mean squared shear. And that is the thing that George taught us is potentially divergent at large scales. So following that, Kibble and Liu wrote an important article pointing out that Weinberg says flux densities are unbiased, but that's averaging over sources. They noticed that if you averaged over directions, and maybe with the CMB, that's what we talk about, you get something different. So Weinberg's saying the mean magnification mu is equal to 1. Kibble and Liu say that if you average over directions, you'll get something different. And what's going on, I've tried to illustrate here, is that imagine a situation with an observer surrounded by lensing stuff with some overdensities and underdensities. The fact that the underdensities cause the rays to diverge means that more of the sources will be seen through underdense regions. Right? There's a bias coming from that. And now that's all pretty old history, goes back to 63, we're up to 2005. The recent developments came from people responding to George's push to do nonlinear perturbation theory calculations and see if there are biases. This is hard, but it was nicely reviewed by our chair and his collaborators in this nice little letter. And they're claiming there's an effect. And in fact, this is perhaps the most interesting formula. This agrees with what you get from Schneider, Jürgen, Ehlers, and so on. So that's so the question now is there a flaw in Weinberg's argument? And George in 98 had come up with a sort of strong lensing argument for how this might break down. And he's already shown that picture. What Roy and his collaborators were doing was perturbation theory. And what they proposed is that Weinberg's argument is wrong because he draws a sphere, that a surface of constant redshift isn't a sphere. It's maybe qualitatively like a golf ball. And that kind of wrinkling can surely make the surface larger. So this is where John Peacock and I came in and tried to calculate this. And we posed the question this way. We said, imagine there's structure in some region and we look at these sources or the CMB at great distance. How will, say, the surface of constant redshift for sources be affected by this? And how will the area of that surface change? And we argue there's two effects because the light follows wiggly lines, so they don't, in a certain amount of cosmic time, say, they don't get as far. And the other one is that the surface is wrinkly and so has a larger area. So they have opposite sign. And now I will appeal to your intuition to argue that this is like calculating how much the area of that swimming pool is increased because of the waves. And it's not difficult to show that it goes like the angle, the tilt angle squared. It's a dimensionless thing. It can't be anything else. And the tilt angle in cosmology is 10 to the minus 3. So the tilt angle squared is 10 to the minus 6. So there is a bias, but it's extremely small. I'll skip over the details. The other point, though, and this is related to Kibble and Liu, is you can get much bigger effects if you average the wrong quantity. You have to be careful. To get an unbiased result, you have to average the right thing. And I have run out of time, so I'm going to why don't I pop up this other question? Let's have a bit of fun. We have about 1 minute, right? So here's the Zeldovich empty beam business, stripped down to its simplicity, right? So you got to ask yourself, is there a gravitational field there? So consider two things. I either fire P's along that tunnel and they may or may not diverge, or I can fire photons. So which, if either of the beams get defocused? This is a harder problem, so I can see your thinking. Only one. Come on. So if we were right, if the cosmologists who like to think that lensing is just Newton times 2, right, then presumably either there'd be no field and neither would be deflected, or there is a field and both will be deflected. We got 18. So we've run out of time. Okay. So people are at least not choosing something else, but we've got basically equal amounts here. And so the right answer here is B, that there is a gravitational field in such a tube. And you can see that most easily because the Laplacian of the potential has to be 0 there because there's no matter. But there is surely a radial variation of the potential, and that means there's got to be a transverse variation of the potential, and that causes deviation for non-relativistic particles. But the Ray-Choudhury's equation says all you care about is the matter in the beam, so the photons don't get. So I guess the people who opted for B, who got the right answer, no Ray-Choudhury's equation, well, so congratulations to you. And I better stop there. Sorry for going over a little.
Thank you, Nick, for a really interesting talk and 2 difficult puzzles. Any questions for Nick or comments? No questions? Just checking the chat.
We will have a tea break now, Roy, and we'll comment again at 11:15.
Okay, well, looks like everybody's dying for a tea. Great. Well, thanks again to Nick for a very interesting talk.
Bye.
So we'll adjourn for 15 minutes and then rejoin. In the meantime, you can enjoy some South Africa videos we'll play in the background.
South Africa has all of the features that travelers long for in a vacation destination. Fine weather, gorgeous scenery, great beaches, modern accommodations, and superb cuisine. The southern tip of Africa also offers an exotic array of once-in-a-lifetime adventures, from off-roading on a safari to diving with great white sharks. It's hard to name another holiday destination that offers as much variety. Here's a look at the best places to visit in South Africa. Number 10. Blyde River Canyon. Blyde River Canyon is the second largest canyon in Africa, after the Fish River Canyon, although it is much greener due to its lush subtropical foliage. Walking treks through the rich diversity of flora and fauna-filled canyon offer views of magnificent escarpments, waterfalls, and ancient geological phenomenon. Visitors have the opportunity to encounter all 5 of South Africa's primates here, as well as hippos and crocodiles near the wetlands of Swandini Dam. Number 9. Cape Winelands. The fertile valleys of the Cape Winelands are surrounded by majestic mountains, sleepy villages, fruitful orchards, and some of the lushest scenery in South Africa. Visitors can follow the wine routes of the Cape to visit the vineyards of the country's finest winemakers, whose sherries, ports, brandies, and intriguing whites and reds are world famous for their delicate flavors and savorable palatability. Number 8. Addo Elephant National Park. Located in the Eastern Cape region of South Africa, the Addo Elephant National Park is one of the country's largest parks. The park is famous for its elephant population that has a special brownish skin color due to the red soil. Amongst the elephants, other animals like ostriches, antelopes, and warthogs can be seen. As part of the park's expansion, a group of lions and a group of spotted hyenas have been introduced to the park as of 2004. Number 7. Hermanus. Located on the southern coast of Africa near the Garden Route, Hermanus is famous for its shore-based whale watching. The sheltered, shallow waters attract southern right whales that migrate to the region each year to mate and breed. A 6-mile-long cliffside walk with built-in telescopes and benches offers visitors plenty of opportunities to view these social animals as they raise their flukes in the sea breezes. Whale-watching boat tours are available as well. Number 6. Durban. South Africa's second-largest city, Durban, is located on the eastern coast. Durban's subtropical climate, scenic beaches, and close proximity to Johannesburg have made the coastal city a popular vacation destination for South Africans. The English colonial architecture that once dominated the city has been enlivened by a mix of Zulu murals, Islamic mosques, Hindu temples, and Christian churches. Number 5. Hluhluwe Umfolozi Game Reserve. As the only park under a formal conservation effort in KwaZulu-Natal, where you can see the Big Five, lions, elephants, leopards, buffalo, and rhinoceros, the Hluhluwe Umfolozi Game Reserve offers visitors wildlife viewing opportunities second to none. Wildlife enthusiasts may enjoy the vast expanses of native plants and native animals during guided walks, self-guided drives, or opt for a thrilling viewing experience by boat along the Hluhluwe Dam. Number 4. Garden Route. The Garden Route is a scenic stretch of the southeastern coast of South Africa. It extends from Mossel Bay in the Western Cape to the Storms River in the Eastern Cape. The name comes from the diverse vegetation encountered here and the numerous lagoons and lakes dotted along the coast. It includes some of the best places to visit in South Africa, including Knisa, Plettenberg Bay, and Nature's Valley. Number 3. Drakensberg. The Drakensberg is a mountainous region that forms the boundary between South Africa and the mountain kingdom of Lesotho and offers some of the country's most awe-inspiring landscapes. The name Drakensberg is derived from the Dutch, meaning Mountains of the Dragon, which truly captures something of the mountain's otherworldly atmosphere. Number 2, Kruger National Park. Covering a wide stretch of bush and savanna in the northern reaches of South Africa, Kruger National Park borders the countries of Mozambique and Zimbabwe. For its dense animal population and the variety of its flora and fauna, the park is considered the jewel of South Africa's extensive park system. Numerous well-kept tarred gravel roads have made the park a favorite choice for self-driving expeditions. Number
Hi, Martin.
Hi.
Nice seeing you. Look forward to seeing you in person shortly at some stage.
Yes, that'll be nice.
And I'm sure those leopards and other creatures that you saw on Sudan's collage there must have evoked some nice memories.
Yes. And they're waiting for me as well.
Yes. I'm really looking forward to seeing you here shortly.
Thanks a lot. I guess we should start now. So, okay. I have the pleasure to introduce Claudia Durban, who is now presently professor at Imperial College. So I might have the dates wrong, but I think we came together in, what would it be, 2003 to Ames in Muizenberg. So Claudia has been to South Africa. And so Claudia did her PhD at DAMTP at the University of Cambridge. And then she held a number of postdocs in Canada and faculty positions at Geneva, at Case Western Reserve University, and at Imperial College. And she's going to talk to us about cosmology under the gravitational rainbow. So welcome, Claudia.
Thank you very much. Thank you for this introduction. Yeah, it's been, it was a different reality, I guess, 18 years ago in Cape Town. I think we've seen each other since, but we spent quite a bit of time at that then. So let me try to share my screen and see if that goes. Can you see my screen here?
Not yet, but I think it's coming up. Yes, now it's visible.
And is it the presenter view or is it the full slide?
It's the presenter.
Okay.
So everything is good.
Thank you very much. I feel a little bit frustrated that we had to to close the video short, just when there was the first attraction coming up. So I apologize, you have to hear my talk rather than seeing the best attraction in South Africa, but hopefully I'll be quick and we can go back to more exciting things. But I'd like to start by thanking the organizers for this amazing conference. I apologize, it had to be soon and it's online. That's the nature of it, but it's very nice to be there, at least virtually. So I'd like to thank Sudan and Martin and all of the other organizers. And if the title of my talk is a little bit abstract, hopefully you'll get where I'm trying to head at towards the middle of this talk. But starting with a little bit of motivation, it's been, of course, a huge success for the cosmological paradigm. It's always lagging a little bit. Yes, with a multitude of various observations at different scales that all seem to be converging towards standard model for cosmology. But at the core of all of this success, there's, of course, the way we can see things, whether the glass is half full or half empty. And we may wonder if we're opening a whole plethora of new puzzles for cosmology and for physics in general. So there's in the core of all of this success, there's also a list of open questions that have emerged, and that's always how physics makes progress, a list of various questions from the very beginning of the universe to the late time of the universe and potential tensions that may or may not subsist in the future. So I'm not going to go through all of them in turn, but just as an example for the question of what dark energy is or what is at the source of the late time acceleration of the universe, I just thought it would be nice to illustrate the type of creativity that has been going on in the field in the past 20 years or so since observation of the late time acceleration of the universe. So this was in 2008, so already quite a few years ago. There was a list of potential models that Andrew Tolley, who will be giving a talk right after me, and myself provided. Provided the type of models that had come up since then in the literature. So I'm not going to go through all of them in detail, but then a few years ago, I thought it'd be nice to just illustrate what new models have come up in the literature since then. And what you'll see is that it's really been a huge explosion of various models that have been proposed in the past, even in the past 5 years or so. And this is not at all expected to be an exhaustive list of models. It's highly biased, but it's just suggestive in the type of creativity and imagination that people come up in trying to understand or address just the question of what dark energy is and how we can reconcile it with the cosmological constant problem. And there's a whole similar story going on for inflation at an even much higher level, or dark matter, and any open questions that might have come up in the cosmological paradigm that we're living today. So in parallel of trying to come up with solutions that are just within the standard model of particle physics and of cosmology, people have come up with models of modified gravity, and I've been asked to review a little bit of those. So I'm afraid I'm not going to make too much justice of that. But if you're trying to understand how you can modify gravity at all, there's various different type of assumptions that underlying behind general relativity that can be broken, whether it is the one related to Lorentz invariance. You can break Lorentz invariance, or you can restore, you can keep it. And if you keep Lorentz invariance, you can think of gravity as a spin 2 particle. It can be massless or massive. And if it is massless, then in order to modify gravity, typically you add additional degrees of freedom in which gravity is non-minimally coupled with the rest of the standard model or the rest of the matter field that be existing in the universe. So again, this is not at all exhaustive, but it's a type of classifications that can be used, and that is to address dark energy or any other question that you may have. Now, in all of those models, apart from maybe from the minimum massive gravity that breaks Lorentz invariance and some other Lorentz invariance breaking model, but in anything which is Lorentz invariant, you will introduce new additional degrees of freedom, no matter what you do. And in order to explain why we haven't yet observed those new degrees of freedom, you need to invoke some type of mechanisms. So the simplest one would be to say that this degree of freedom, which I symbolically designate as phi, which may have some background, phi b, and is living in a universe with a local density rho b. So one way to invoke that those degrees of freedom haven't been detectable yet is to say that they're weakly coupled to matter. So the coupling to matter is either zero just from the outset, or there's some mechanism that sets it to zero about some particular relevant cosmological background, for instance. So that's probably the most straightforward way to screen, or it's not really a screening, but you simply decouple this degree of freedom to the rest of the matter field that we may be observing. Now, in the past 15 years or so, maybe even more, I think probably 20 years, the chameleon mechanism has come up as one of a very powerful way to screen this the degrees of freedom that may be coming in, for instance, in NFOVAR, or in any other modifications of gravity. And effectively, what the chameleon mechanism does through non-standard coupling with matter is to give the scalar field in this context, but it can be applied to other things, is to give the field a large mass in dense environments of the universe. And then there's another whole class of models which are screened via another mechanism. So it's not directly through weak coupling, it's not directly through being very massive. The only other possibility is through its kinetic term. And as soon as you have a screening which relies in this case on a large kinetic term, which will mean that the scalar field or whatever field you're considering will effectively become weakly coupled to the rest of the matter field because it costs you too much energy to kind of excite it. This goes under the name of Weinstein mechanism. Sometimes the kinetic screening and Weinstein mechanism are separated out, but I really consider them all under the same umbrella. It is really when a kinetic term becomes large. And there's a whole class of models that I'm not going to go through that satisfies this Weinstein mechanism. But Andrew Tolley later on will be mentioning about some particular models and how this Weinstein mechanism gets implemented relatively naturally in many of these modifications of gravity and what the residual observable may be. But now for the rest of this talk, what I like to do is more of a generic approach where I'm not going to focus on any specific model at all, but I'm just going to motivate the fact that we have all of these effective field theories that may be interesting for the phenomenology of dark energy or for any other phenomenology that we want to have. And we really need to set these different type of effective field theories apart. And so the best way forward, of course, is what we always do. And what we should do is simply compare with the real world and let observations and experiments tell us where we are within this region of effective field theories, in this region of parameter space among all the models that we have come up with. And this has done a lot of beautiful work already, just in the terms of the dark energy models that I mentioned. There's one example of observations that have been very useful in the past few years in segregating between various types of models, which is that of the direct detection of gravitational waves from a neutron star merger with an optical counterpart. And as I'm sure you all know, this has allowed the community to put a constraint on the speed of gravitational waves at LIGO frequency to be exactly the same as that of light at huge frequencies, in one part in 10 to the minus 15 or 16. And so by itself, this one observation has allowed us to roll out many models of dark energy, which would otherwise have predicted a different speed for gravitational waves. There's a small caveat here, which is not particularly relevant for what I'm going to be talking about today, but it's worth keeping in mind, and it still goes under the umbrella of this gravitational wave, this gravitational rainbow framework that I'd like to be talking about, which is that in all of those models, particularly the new ones that have been people have come up with in the past 12 years or so, they really had to be considered as effective field theory with a finite region of validity. And there are effective field theory which are designed to explain dark energy, which is, of course, effective field theory at a very low energy scale. We want them to be valid at scale of the Hubble parameter today, or roughly 10 to the minus 33 electron volt or so. Of course, we like them to be valid a little bit beyond that, but there's quite a gap between the scale of dark energy and the observations at LIGO scales, which are of the order of 10 to the 100 hertz or so. So there's quite a large gap between the two. And it's quite possible that some of those models of dark energy, even though they would predict a speed of gravitational waves that depart from that of light, they do so at very low frequencies. And as you go to higher and higher frequencies, the model of those, some of those effective field theory are no longer valid. They need to be embedded within a high energy completion. And we would expect, and there's some explicit examples where we can see that happening for scalar field theories, that whatever was responsible for the spontaneous breaking of Lorentz invariance at low energy, which is what leads to a departure from the speed of gravitational waves to be 1 at low energy, will go back to being precisely Lorentz invariant at high energy. Just in the same way as when you shine light through glass, you have a deviation from the speed of light going through glass at low energy, but as you go to higher and higher energies, light at huge frequencies still shines through glass or through water at the same speed as you would do in the vacuum, because it remains completely unaffected by the medium in which it's going through. And so you would expect the same thing to happen for these type of dark energy models. And so it's not inconceivable that it could still predict a speed which is exactly liminal at sufficiently high frequencies once we have implemented them within a consistent high energy framework. But still, using observation to constrain some of these dark energy model is already making a lot of progress. And just to give you an example, this is just an illustrative example that I'll be using throughout this talk, just so you can see where I'm headed. It's not necessarily the most compelling model in the whole universe, but if you just consider a model of dark energy or modified gravity, which goes under the name of the quartic Handesky, which will have parameter CB, CM, and CT. So T, for instance, is the speed of gravitational waves. This has been constrained to be 1 at LIGO frequency, but it's possible that at the scale of dark energy, you can still have a departure of the speed of gravitational waves as compared to 1. So this model, it doesn't matter too much what it is, has some free parameters, and you can use current observations, current cosmological observations from CMB, BAO, redshift space distortion, and everything to constrain where you're more likely to be in the region of parameter space. So this is relying purely on observations alone. Now, in addition to those observations, which I think should really be the core of all the constraints that we're imposing on ourselves, because this is really just comparing with the real world, this is really what we have. But complementary to that, you can also ask yourself some more theoretical constraints, which I would argue you can use to complement your observational and experimental constraints. So there's many different types of theoretical constraints that will go under this umbrella, but really it's asking ourselves how healthy the model that we're considering, particularly as a low energy effective field theory, will be. And particularly, you can ask yourself whether it's stable, whether it makes sense as itself, whether the degrees of freedom that you're using makes sense. And a question that is often quite hard to ask, but is really essential, is to wonder whether the model we're using is really valid in the regime of validity that we want to use it for. And so there's a lot of question about strong coupling or related questions, which are quite subtle to answer. But if you can't answer them, then you don't even know that you can use the effective field theory that you've written down to describe the phenomenology that you want to for that particular process. So to give you some example of how theoretical constraints can be used in complementary to observational constraints, if we go back to the Handesky model that I mentioned before, whether you like it or not, it doesn't matter too much, it's really just for illustrative purposes. In addition to these observational constraints, you can put this type of theoretical constraints, which are based on stability, which are based on some level of luminality as well, which we typically think are related to causality. And so this is to give you some example of how you can go from just the pure cosmological constraints, observation constraints, to the more theoretical constraints if you put them as a prior. So how you can reduce your regional parameter space where you would expect it to be. So what you can see in here is that the main constraint is actually coming from the speed of gravitational waves. You want them to be subliminal. And in many, as I mentioned, in many of those effective field theories, because you spontaneously break Lorentz invariance from the cosmology at low energy, you can have a deviation from the speed of gravitational wave to be 1. Now, the question I'm going to like to ask, I'm not going to put a poll in like Nick did, but I can ask ourselves the question, and this is typically done in cosmological effective field theories. Should we constrain a model so that the speed is always subnuminal, so that whatever we have as a phenomenology, this delta C, even if it's not observable, in principle should really be constrained to be subluminal so that we don't have subliminalities. So I'm not going to put a poll there, but you can try to answer that question for yourself. And if you were to ask me this question a few years ago, I would say the same answer to answer is yes, absolutely. You should constrain the speed of gravitational waves, the models, so that the speed of gravitational waves is subliminal, because it's well known that subliminality is related to a causality. Even the tiniest amount of subliminality could be led to a macroscopic propagation outside the light cone, which would then be in tension with causality. So typically, this is where we are, and say that the sane thing to do is really to impose that the speed of gravitational is subliminal, and the speed of anyone, for that matter, to be subliminal. But now, what I'd like to convince you to do, and that will be through a different type of considerations, is that if you think of it a little bit more carefully, the connection between the presence of subliminality and the tension with causality is a little bit more subtle than what we naively anticipate, particularly in the presence of gravity. And so in the presence of gravity, it's not obvious that subliminality is always related to a causality. And to understand that, it's a little bit easier actually to go back into a yet different type of constraints, which are also theoretical, but it's slightly different than the constraints that I mentioned before, in how we can segregate between our various types of effective field theories. So before I mentioned about theoretical constraints, and those I really were thinking of constraints which were simply implementable within the low energy effective field theory, with no indication of how this low energy effective field theory will connect with an ultimate completion at high energy. But in addition to having a low energy effective field theory that may be describing whatever phenomenology that you want to, you may also ask yourself how this effective field theory came to be, what is its origin. And so you may have a model at low energy, but you like to see what is its fundamental completion at high energy. So I'm not going to give you the fundamental completion of quantum gravity and everything that, that comes to be. I'm sorry about that. But we can still impose some constraints on ourselves at low energy so as to ask that the model that we're having may in principle be compatible within a high energy completion. And when I say these words, this may sound very familiar in the sense of that's what typically the swampland conjecture is doing. And so just to give you a perspective on how the considerations that I'll be talking about connect with the swampland or don't connect with the swampland, they're really complementary to them. So they're complementary arguments that are based on scattering amplitudes applicable at low and high energy, as compared to the swampland, which is a little bit more conjectural. So I'm putting a question mark here because I don't know exactly how those constraints live in slightly different space. So I don't quite know how to put it in that, classify it into that level of assumptions. But it's slightly different and yet complementary. So the constraints that I'll be talking about go under the name of positivity bounds, and they assume the notion that the model we have at low energy, no matter what it is, should be able to have a high energy completion, which is unitary in the sense that the probability sums up to 1. Locality, I'll mention a little bit more what I mean by this notion of locality. Poincare invariance, so not only I want Lorentz invariance, but I also want particularly time translation invariance and causality. So these are the assumptions that I'm going to impose on myself. You may be unhappy about some of those assumptions, but in the grand scheme of things, these are relatively non-controversial assumptions. Now, you can put more assumptions if you want to, particularly weak coupling, and you can go to higher and higher level of assumptions, all the way up to having an explicit realization of high energy, for instance, from string theory, if you wanted to. Or you can remove some of those assumptions, particularly when you want to implement them within a cosmological setup. But I'll start with this level of assumptions there. Another surprise is that we may have some models at low energy, which may seem to be completely consistent within themselves to fit all the possible experimental and cosmological and observational constraints that we are observing, and be theoretically viable at low energy, completely stable, for instance, maybe completely subluminal. It seems completely perfect at low energy. And yet for some of those models, we know that they will never ever be able to enjoy a high energy completion, no matter what this high energy completion is. So it can be string theory, it can be bubblegum theory, whatever you want at high energy. We know that those some of those models will never be able to be implemented within a consistent high energy theory, no matter what the field content is at high energy. I'm putting no constraints at high energy aside from the requirement of unitarity, locality, Lorentz invariance, Poincare invariance, and causality. So a priori, it seems to be kind of surprising that there should be such a strong connection between our high energy completion and the low energy effective field theory, because there should be a decoupling of scale between what's going on at high energy and what's going on at low energy. But the reason that why we can put some constraints actually at low energy from the requirement of what's going on at high energy is because of the notion of causality that manifests itself in terms of analyticity. I'll mention about that in a second. And this notion of analyticity is precisely what makes the connection between high energy and low energy. So I'll be a little bit clearer in that. So let's imagine you have a low energy effective field theory, no matter what it is. You can compute some scattering amplitude at low energy. I'll just be computing some 2 to 2 scattering amplitude. That's really just what you think it is at low energy. And I'll look at the complex energy square plane. Now, at low energy, I can compute this amplitude using this effective field theory, but my effective field theory will have a finite region of validity. So far, we have no theory for instance, for the standard model of particle physics or for general relativity, in that sense, that is embeddable all the way up to high energy. So we typically work within low energy effective field theory. You really need to go to string theory or alternatives to string theory to have some high energy completion. So let me imagine I'm working with a low energy effective field theory with a finite region of validity. I can compute the amplitude in that region. Outside this region, I can no longer use this low energy effective field theory to compute the amplitude, but the amplitude still exists. And there's still a meaningful amplitude which exists there. I simply can't use my low energy effective field theory to compute it. I need to implement new layers of physics, maybe new degrees of freedom that comes in, that have to be integrated back in, put it back in order for me to compute this amplitude explicitly. And there may be an infinite number of layers of physics that go up all the way up to ultimate high energy completion of everything. And I definitely cannot use my low energy effective field theory to compute the amplitude there. But it seems reasonable to assume that no matter what the amplitude is up to infinite high energy, it will remain local, Lorentz invariance, unitary, and also causal. A notion of causality manifests itself in this complex energy square plane as a notion of analyticity. Analyticity of the amplitude, which means we can make an analytic continuation between what's going on at infinite energy and what's going on at very low energy. So it's the notion of causality that really embeds the connection, the communication between what's going on at high energy and the requirement of, for instance, locality and unitarity at high energy to those at low energy. And I will put some constraints that have to be satisfied by our low energy effective field theories within the region of validity where we can compute them. So I'm not going to go through the details of those, But what we can see is that if we ask for ourselves for unitarity, Lorentz invariance, causality, and locality, and the notion of locality in here is the requirement that the amplitude doesn't grow up fast enough so that it satisfies the Froissart bound, and so that I can really go back into real space and ask ourselves some questions in real space. That's really what he means by that. So those conditions really imposes some condition on the imaginary part of the amplitude. One of them that we know very well is that the cross-section has to be positive. This is one of those realizations. And that within the low energy effective field theory is encoded within some statements about what the amplitude has to satisfy. So for instance, the second derivative of the amplitude with respect to the energy square has to be positive. And that is typically related to this condition of subliminality at low energy. And that seems to make sense because in at least non-gravitational effective field theories, we're familiar with the statement that subliminality is related to causality, or that causality should require subliminality. And there's an infinite number of other constraints that we can impose on ourselves at low energy. So this is just an illustration of how we can implement those constraints for physics beyond the standard model. I'm not going to go through that right now for sake of time. But if you go back into the model of the Quartic-Hondesky that I mentioned before with the 3 parameters, just for simplicity, then you can implement these observational constraints with the positivity priors. And this is to illustrate how powerful these positivity constraints are in further constraining the region of parameter space, complementary to observational constraints. So you can see that from this, for instance, region, yellow region here, imposing those positivity constraints tell you that you would have to be in this region. Now, this is just illustrative. It really has to be taken with a big spoon of salt, because there's quite a lot of assumptions that have been made in us being able to apply those positivity priors, which are not so easily satisfiable in the cosmological framework. So it's really just to see how complementary in principle you could the constraints from observations and from those positive priors would be. The reason why you have to take that with a pinch of salt is because as soon as you're dealing with gravitational effective field theories, and particularly with cosmological ones, there's a lot of things going on which have to be taken into account and that are not necessarily under control at the current time. So in a non-gravitational effective field theory, I made a connection between those assumptions that you had at high energy and those notion of positivity bounds, and then a notion of subliminality, for instance, which seems to be naturally connected with the requirement of causality. Now, as soon as you're dealing with a gravitational effective field theory, as you want to do in the cosmological setup, then already the connection between causality and analyticity is a little bit more murky. Also, you may not want to impose the same level of locality at high energy. I'm still going to do it, but there's some open questions about those requirements in the first place. Hopefully, no one will object about the requirement of causality, but maybe that of locality you may do. But even assuming that those assumptions remain present, so I'm going to be as conservative as I can, even if you have those assumptions at high energy, deriving some positivity bounds from those assumptions is more subtle, and deriving the notion of subliminality speed at low energy from the positivity bounds or from the notion of causality is more subtle. There's an infinite number of reasons of why it's much more subtle, and I'm not going to go through this infinite number of reasons right now. There's a few reasons of why it is more subtle. The first one, related to the notion of subliminality, for instance, is just the fact that as soon as you have gravity, then you have frame artifacts, and this notion of speed is not invariant under the frame transformations, what the notion of causality is. So this is a completely trivial frame artifact that we can deal with because I have a finite time. I'll say this is something too easy for us to discuss about today. It can be very easily taken into account, but this just tells you that simply stating that the speed has to be subliminal in relation with causality makes no sense when you're dealing with a gravitational theory. You need to specify which frame you want to be working with. Now, a much more difficult problem to address is the fact that if you're interested in cosmology in particular, or whatever else you're interested in, the cosmological background will spontaneously break Poincare invariance. And so you really need to understand how the notion of the breaking of the symmetry will be implemented within the new positivity bounds, which were used assuming Poincare invariance. So this, for now, is going to be too hard a problem for me to solve, and I'm going to talk about it right now, but there's been some progress made by various members of the community. I think there's still a way to go into understanding precisely how to implement these constraints in a background that spontaneously breaks Poincare invariance. Now, a third type of subtlety that emerges as soon as you including gravity, and I have to say none of those are related to the fact that we don't have an ultimate quantum theory of gravity at high energy, or we don't have an agreement of what the quantum theory at high energy is. All of those are just artifacts at low energy already. But the third reason why it's becoming more subtle is because of the presence of a gravitational exchange, an exchange which is mediated by a massless spin 2 particle that arises as soon as you're dealing with gravity. And as soon as you're dealing with gravity, as soon as you add gravity in the game, you may not be interested in gravity per se, so you may be interested in scattering fermions, for instance, for physics in the standard model, or physics beyond the standard model, or you may be interested in scattering of your inflaton scalar field or your dark energy scalar field. It doesn't matter too much, but just the fact that ultimately it is a gravitational theory means that you can't prevent gravity to come along and play with you and to have a process that includes a gravitational exchange. Now, this gravitational exchange, because it's mediated by a massless particle, will have a pole at 0 mass, because it's a massless particle. So when T is the momentum transfer is 0, you have a pole there. And that happens even if you had an exchange of a photon, that's okay. But as soon as you're dealing with gravity, because it's spin 2 particle, the residue of this pole grows like the energy to the 4, like s squared. And that means that as soon as you have gravity, this contribution does affect the second derivative of the amplitude at t0. And it spoils the direct applicability of the positivity bounds as soon as you have this pole. If you had a photon, this would just grow like S. So even though technically you have a pole at T0, that doesn't come into this type of bounds. But now analyticity technically is much more subtle to understand at T is equal to 0. What it implies in practice is that as soon as you have a gravitational theory where those type of bounds are present, instead of us being able to impose a positivity bounds, which was just this coefficient being positive, in all the examples that we can think of explicitly, for instance, a model of particle physics minimally coupled to gravity, for instance, QED, minimally coupled to gravity, we see explicitly that this coefficient C is not positive. It's actually negative by an amount which is suppressed by the Planck scale, of course, so that when you decouple gravity, you send the Planck scale to infinity, this goes to 0, but it is still negative technically. And the very presence of this negativity is actually crucial in understanding the connection between causality, or how causality implements itself at low energy. Because as I mentioned before, in non-gravitational effective field theory, it is through the notion of positivity bounds, through the requirement that this quantity here is positive, that the notion of causality really manifests itself under the statement of subliminality within the low energy effective field theory. And this is how it's been proven, for instance, for the speed of light at low energy when it goes through different type of media. Now, in gravitational effective field theory, because the equivalent of this quantity here does not need to be positive definite, it can be a little bit negative, not by much, but it could be in principle a little bit negative. This tells us that the notion of causality doesn't require, even putting aside any frame artifact, doesn't require the speed of gravitational waves to be strictly subliminal. A little bit of subliminality is actually allowed, so long as it's suppressed by the Planck scale and sufficiently suppressed by the Planck scale. So as soon as we get to that level, you may wonder, well, if that's the case, how would that be visible? How the notion of causality manifests itself within the low energy effective field theory? Because after all, as soon as you have the tiniest amount of subliminality, and it can be suppressed by 120 orders of magnitude, it doesn't matter. In principle, the smallest amount of subliminality at low energy still means that you can integrate it out till the end of the universe, till the end of time, and get macroscopic support outside the light cone, which itself would tell you that you're in violation with causality. So within the next 5 minutes or so, if I have the time that I have left, let me just try to argue on how this small amount of superluminality that manifests itself within gravitational low energy effective field theory, particularly cosmological ones, is still consistent with a notion of causality, or not in tension with causality. So let me emphasize once more, and once again, and this is within the realm of the gravitational rainbows, that the speed of gravitational waves, just like the speed of light, can vary as a function of frequency when it's implemented within a spontaneously breaking Lorentz invariant medium, like cosmology. And so at high energy, at infinite frequencies, the speed, the phase velocity, infinite frequency phase velocity is the front velocity, can remain luminal. So there's no tension about that. There's no discussion about the fact that the infinite frequency phase velocity is luminal. And this is really what the requirement of causality asks us, that the front velocity be luminal. But within the low energy effective field theory, what we probe is not the front velocity, is the low frequency phase or group velocity. And we'll have to understand how this low energy superluminal velocity can be consistent with causality. So if we take the example of a cosmological framework with an effective field theory that may include, for instance, higher derivative terms as an effective field theory, so those are okay as an effective field theory, you will have inevitably some operators that lead to a departure of the speed, of the luminal speed of gravitational waves, plus corrections at high energy. So those corrections at high energy are precisely the ones responsible for switching the low energy phase velocity from subluminal to or superluminal to being exactly luminal at a higher frequency. But at lower frequency, you have a departure from luminality, and a priori you can integrate this level of superluminality from the beginning of the universe all the way up to the end of time, so that even if you have a very small amount here, you'll have a large amount support outside the light cone. And then you can perform at infinity, you can perform a boost and then go back in time and stop this talk before it ever started. Now, the reason why this is consistent with causality is because we're dealing with a low energy effective field theory. And as a low energy effective field theory, it has a finite cutoff. To be conservative, the cutoff will be at least at the level of the Planck scale. In most cases, as I mentioned, it can be much, much lower, maybe even lower than LIGO scale. But to be conservative, it will always have to be smaller than the Planck scale. Now, in those models, this level of superluminality is not big, it's not even observable, but it's a proof of principle on whether or not it could be a priori superluminal. You have this level of superluminality. Now, if you wanted to integrate from the beginning of time or from a given time all the way up to infinity, you need to make sure that you remain within the regime of validity of your low energy effective field theory throughout this time. And remaining within the regime of validity of this effective field theory tells you that there's maximum frequency that you can use for the modes that you can use which depends on how early in time you want to go. Or in other words, if you want to start at a given time ti, because the curvature at that time is larger, it means that you need to use lower frequency modes to send it. Otherwise, for too high frequency modes, you will go beyond the regime of validity of the UFT. Or in other words, the wavelength that you need to include or you can use to probe this support outside the light cone has to be larger than the Hubble parameter at the initial time in units of Planck scale. But when you use this requirement, which comes from the validity of the effective field theory into account, and you try to integrate out the distance outside the light cone that you can have, in principle, maximum distance that you can have from this level of superluminality, you end up seeing that it will always end up being an amount which is smaller than the physical wavelength of the mode that you sent in. So in other words, yes, in principle, you can have a support outside the light cone, but it's not resolvable. It's always smaller than the physical wavelength of the mode that you use to probe this level of superluminality. And so using a particle approximation to make these measurements is no longer adequate. You can't do that. So there's never really any physical support outside the light cone, in the sense that it's never resolvable. And because it's never resolvable, there's no violation of causality. And this is the case in an example of cosmological setup, but you can do the same thing for other type of effective field theories. And you can do the same thing about, for instance, black hole or other type of configurations that would spontaneously break Lorentz invariance. Now, a priori, you may say, well, this statement by itself simply tells you that it's not resolvable, and so it's inconclusive. But it's actually better than that. The very fact that it's unresolvable tells you that the would-be secular effect, or the secular effects themselves, can never grow, and therefore you can never grow as to be dangerous. So they're always remaining under control. So this quantity here is always going to be much smaller than 1. This is exactly what the notion of unresolvability tells us. And if this is always much smaller than 1, those corrections here that comes in when you're trying to expand this exponential in terms of what the exponential would be using the standard flat space-time propagator, and then corrections from the fact that you are seeing some departure from luminality, the fact that you can do this perturbative approach without those secular effect growing up tells you that you can compute the retarded propagator perturbatively about the one which wouldn't include the EFT operator, so wouldn't account for this spontaneous breaking of Lorentz invariance. And perturbatively, if you start with a retarded propagator, which is 0 outside its light cone, perturbatively, you can never all of a sudden create a retarded propagator which will start having support outside its light cone, because all you're doing perturbatively is acting operators on something which is 0 outside the light cone. So by itself, the notion of unresolvability of the support outside the light cone is then directly related to that of causality. So I'll stop here. This is just to motivate the fact that we have to be a little careful when looking at constraints on low energy effective field theories, particularly in the cosmological setup. So there's been a plethora of gravitational effective field theories describing various time evolution of the universe, and I've seen there's going to be many talks about that throughout the rest of this conference. What I like to argue is that complementary to the huge success of observational constraints, which are becoming more and more precise, we can also invoke some level of theoretical constraints. There are some theoretical constraints which are directly embeddable within the low energy effective field theory without any priors with what happens at high energy. Now, the more priors you put on yourself from high energy, the more constraints you will have at low energy. But even just remaining relatively conservative on what's going on at high energy, so I'm not going to be very specific on a particular string theory compactification, for instance, just requiring that whatever happens at high energy, no matter the number of fields, it can be an infinite number of higher spin fields at high energy, no matter what happens there, it's going to need to be unitary, for instance, and causal, is related to positivity bounds. Now, those positivity bounds is typically what tells you that the speed at low energy has to be subliminal, but in the gravitational context, it's a little bit more subtle than that, and a small level of what you typically qualify as subliminality is allowed, and so that has to be taken into account when segregating between various types of effective field theory, particularly for the cosmological setup. Thank you.
Thanks a lot for a really nice talk. I think we have time for one quick question. So I see one in the talk from Nikodem Popolowski. Would you like to turn on your microphone and ask your question? Oh, I guess I can read it. What about Einstein-Cartan theory? This is the most natural modification and of the oldest of general relativity.
Yeah, so so you can go through various type of modifications, including what it is you like to consider as being let fixed when you vary your action. So I would say it's not in that classification that I made. It may not seem very obvious that there are some modification of modified gravity that people are considering, but they're still present within this classification. In any model of gravity, which really corresponds to using not quite the same variables, maybe not the metric or not all of the metric in terms of what you're going to vary or what you're going to consider as the dynamical degrees of freedom, will still ultimately be manifest within this classification. Because if you're going to maintain Lorentz invariance, then you can think of gravity as either a massive or massless spin-2 particle, but the notion of spin itself is present as soon as you maintain Lorentz invariance. So there are some description of gravity which is not manifest in this description, but those realization of gravity, you can always ultimately put them back into an expression of gravity which is in terms of a metric and then additional degrees of freedom. It may not be very pleasant in the way we're writing it like that, but it's still the case. And so then the job is to understand where those new degrees of freedom manifest themselves, or how it will end up being coupled to matter.
Okay, thanks a lot. Let me just point out that other people can post questions in the chat, and hopefully the speakers can answer them. So this is a way in which Zoom allows us to ask more questions. So thanks again, Claudia.
Thank you.
So our next speaker is Andrew Tully, and maybe, okay, yes.
You see me?
Yes, I can see you now. And I can see the screen. So Andrew Tully also did his PhD at DAMT, and has held postdocs at Perimeter in Princeton, and has been on the faculty at Case Western and is now at Imperial College. And he will tell us about massive gravity, Galileons, and scalar gravitational radiation. So thanks a lot, Andrew.
Okay, thank you, Martin. So yeah, I'm going to follow on a little bit some of the themes of Claudia's talk, although focus more on one particular sort of extension of GR, which is really massive gravity, although that's connected. It's really a family of many things, in fact, as I hope to get across. So when we tend to think about modifications of general relativity, we can categorize them basically into things that may change physics at high energies or physics at low energies. So nowadays we tend to refer to things that change physics at high energies as UV, ultraviolet modifications. And the sort of classic examples are string theory fits into this category because we know there's new physics at the string scale. Quantum theory of gravity assumes some new physics coming in at the Planck scale and so on. But there's also other alternatives, such as, or not alternatives, but extensions of that. For example, we sometimes imagine there's extra dimensions with possibly relatively large size for the extra dimensions. And so new physics will come in at the scale of the Kaluza-Klein modes of those extra dimensions, and that can end up modifying gravity because then gravity propagates in those extra dimensions. So all of those, though, fit into the notion of ultraviolet modifications, where we're changing things at high energy but not at low energy. And by and large, if you believe Lorentz invariance is fundamental, those types of modifications are well understood in the context of low energy effective field theories in terms of their implications for low energy physics, where we're just basically taking GR and adding higher curvature terms in an effective field theory expansion. Now, that's not the kind of models I want to think about today. I want to think about the opposite kind, which are much more exotic in some sense, which are infrared modifications. And these have been introduced. So this is modifications that change physics at low energies or large distances. And obviously the main motivation for these in the last 10, 15 years or so has been try and say something about why the universe is accelerating as much as it is, or not more. And related to that, the old and the new cosmological constant problems. And also, it's also just to sort of see, how could gravity be different? So it's now we've got all this wonderful data on gravitational waves. If all they're doing is just reproducing what general relativity tells us, we're not necessarily learning that much. So it's more interesting to know, can we put constraints on other theories that may differ slightly from general relativity? Now, the guiding principle in all this is a picture that Claudia took of Stephen Weinberg at a conference in Case Western, who was talking about this particular topic. And the guiding principle is what we know is that general relativity is the unique local theory describing local Lorentz invariant theory describing the interactions of a massless spin 2 particle. So that's a particular perspective on what general relativity is that de-emphasizes, if you like, the role of the equivalence principle in space-time curvature, and emphasizes the degrees of freedom as what really matters. So the inputs into that is if we assume, as Claudia mentioned, Lorentz invariance, locality, massless, and spin 2 will lead to general relativity. So in talking about departures from general relativity, we have to give up one of those assumptions. And some people give up Lorentz invariance, some people give up locality. For the purposes of today, I'm going to keep those two particular cherished things, but then what we may have to give up is the masslessness of the gravity, or just the assumption that all you have is a single spin 2. So for example, scalar tensor theories assume you have a spin 2 and spin 0, but you may have other spin 2s. You may have higher spins in some, for example, in string theory. That's effectively what you've got as an infinite tower of spin states. So I'm going to consider this particular possibility, where you give up the masslessness and the single spin 2. And that sort of leads me naturally into the class of theories, and I use that term strictly, it's really a class of theories, which go under the umbrella of massive gravity theories. Now, to talk about what they are, let me just remind you a little bit of field theory terminology. So in quantum field theory, one way to sort of probe a system with some action is to add an external source, as Schwinger introduced, and talk about the generating functional. And that's the generating functional is a nice way of encoding all the correlation functions of the system, but it's basically a way of probing the system by adding an external source, giving it a kick, seeing how it behaves. So for example, in just a free theory where the action is just quadratic, because like box minus m squared, the generating functional is also quadratic, and it just looks like an interaction between two sources with the Feynman propagator exchanged between them. So for example, if we write that in momenta space, we have two sources in momenta space, and they interact via the Feynman propagator. And so Feynman diagrammatically, we can think of that as a single boson being exchanged between two sources. Now, in an interacting theory, you don't just have a single Feynman propagator. What you get in the Lorentz invariant theory is essentially a distribution, called something called the Challen-Lehmann spectral representation, a distribution of Feynman propagators with different masses, and that's what you get in interacting theory. So I want to think about it that way. So let's apply that notion to gravity. What is the source in gravity? Well, the source in gravity is the stress energy. So what you get in general in gravity, the generating function, the equivalent of the generating function, is some interaction between two stress energies. If you like, you can think of them as two sources, like the moon and the earth, each one being described by some stress energy. And at leading order, that interaction is described by the exchange of gravitational modes. So in particle physics language, say the graviton, or we can think of it as virtual gravitational waves, is just a matter of terminology. Now, in general, that exchange, just like in any field theory, can have some kind of spectral distribution. So there may be within that spectrum a pole part, which is an isolated contribution, where you have a particle with a definite mass, which is a stable particle. Now, in general relativity, that's what you have. You have a stable massless particle describing the exchange of the force between two stress energies, and that particle we call the graviton, a massless spin 2 particle. But more generally, you could have a spectral distribution where you include massive states, which come ultimately from interactions in the system. It may be quantum mechanical interactions. You have a spectral distribution, and that can create something that also looks effectively massive. But if it's not a pole, then the state is an unstable resonance-like state. So that often then we call that particular situation a soft theory of massive gravity, where you don't have a definite mass, you have a distribution, as opposed to a hard mass where there is really a definite mass state. Now, historically, there was the soft massive theory of gravity was really developed first. And the explicit example is called the Dvali-Gabadadze-Parati model, which was a particular extra dimensional model. And the way it works is in that model, you have an extra dimension, fifth dimension, which is infinite. So all the normal Kaluza-Klein modes, which you get in an extra dimensional theory, which are themselves massive spin 2 modes, rather than having a discrete spectrum, as in the original Kaluza-Klein picture, they have a continuous spectrum. And you can engineer it by putting a particular kinetic term on a brane localized in this extra dimension, so that the distribution of those continuous of Kaluza-Klein modes essentially has a peak at some scale, such the theory effectively looks like a very soft massive gravity theory with, in fact, the resonance, the lifetime of the resonance is of order the inverse mass scale, but it nevertheless is still as effectively behaves like a massive gravity theory. This, by the way, is a completely covariant theory. It's diffeomorphism invariant in 5D. You can write down an action, which is local, etc., etc. And is the first explicit realization of this kind of paradigm. I'm going to talk a little bit more now about the hard massive case, which was a bit more difficult to construct. And here we can be a bit more guided by how we know, for example, masses get generated in the standard model, which is via symmetry breaking. So we know if we take a theory of a particular local symmetry and that symmetry gets broken, essentially what happens is that the bosons that carried associated the force carriers of the particular local symmetry become massive. Now there's a particular regime, which is a high energy regime in that particular description, where you can use something called the Goldstone equivalence theorem, where you can basically describe the physics of the breaking entirely in terms of the Goldstone modes, which are associated with the symmetry breaking. So let me remind you what that is. It's just a particular model. So think about the abelian Higgs model, where you have your Higgs field as a complex scalar field phi, and you have a U1 gauge field, just Maxwell field, if you can think about it. And so the Higgs field is charged. And so as we know, we're supposed to work with covariant derivatives like this. And the Higgs field being a complex field will shift like a phase under a gauge transformation. And as long as the vector potential shifts in the normal way, then the covariant derivative transforms as it should be. Now in the symmetry broken state, it's actually nice to split that up and split the VEV of the field up into, and look at the departures from the VEV. And I identified that that's really what is the Higgs boson, whereas the phase of the field is what you'd call the Goldstone or the Stuckelberg mode. It's the light degree of freedom that gets eaten up by the gauge transformation, and the Higgs boson is the remaining massive propagating particle. Now, there's many different ways to think about this system, but one way to think about it is to go into unitary gauge, which basically fixes the Goldstone mode pi and sets it equal to 0. And then the action for abelian Higgs model would not look gauge invariant anymore because we fixed the gauge. And the Higgs itself would be a massive particle. And if you're working in energies below the mass of the Higgs, you can integrate it out. And then what the action will look like is basically just the Procker action, which describes a massive spin 1 particle, plus interactions which are not manifestly gauge invariant. Now, you might say, why did I go through that procedure? Well, the reason I'm going through that procedure is that for gravity, we don't have an explicit, we don't know how to do the Higgs mechanism for gravity, but we do know how to construct the low energy effective theory for the Goldstone mode. And so I'm explaining this procedure in order to say how we're going to do that for gravity. So in the case of the abelian Higgs model, this is what we call the unitary gauge model that you obtain after integrating out the Higgs boson. And you can reverse that process by means of the Stuckelberg trick, which is I can now take this Lagrangian, which isn't manifestly gauge invariant, And if I now perform a general gauge transformation and promote the gauge parameter itself to a field, what I'm actually doing is really just reintroducing the Goldstone mode that I set to 0 and going to unitary gauge. But it has the virtue now that you recognize that A mu is really just itself a kind of effective covariant kinetic term for a scalar degree of freedom, which is the zero mode of the massive photon that you get in this theory. And by making this form of the Lagrangian is now manifestly gauge invariant. And so now the counting of degrees of freedom and how a massive photon emerges is very clear. F mu, the gauge invariant A mu, is the normal 2 degrees of freedom that you have in Maxwell's theory. And the additional degree of freedom that you have in a massive spin 1 particle, because 2s plus 1 is equal to 3, is explicit now in the helicity 0 mode. So this Stuckelberg trick that I've just performed, where you take your theory, you go in unitary gauge, and then you undo that gauge transformation and promote the gauge parameter to a field, is a nice way of making manifest the additional degrees of freedom you have in a massive theory in its broken state. And the resulting effective theory actually captures physics in a regime of theories, and in a particular regime, which is captured by what's called a decoupling limit. So specifically, when you're working in energies which are very high relative to the mass of the spin 1 particle, if you take a particular scaling limit where this coupling goes to 0 and the m goes to 0 at the same rate, what you see is that the effective interactions for the helicity 0 mode or the Goldstone mode, so this is often called the Goldstone effective field theory, take the form of what cosmologists will call a P of X type Lagrangian. So you have non-minimal kinetic terms. And that just arises in the low energy description of the abelian Higgs model. So the reason I've gone through that, as I say, is because in the case of massive gravity theories, we really only know the equivalent of this low energy effective theory description. In order to uncover it, we have to think about what is the symmetry breaking pattern in massive gravity theory. So if you take general relativity, we know the symmetry is diffeomorphism invariance. If you want to give a mass to the graviton, then basically what you're asking is, how do I break the symmetry? How to break the symmetry? Well, what I would like to do is construct a Lorentz invariant theory of massive gravity. And so I want to break the local symmetry in such a way, so I break diffeomorphism invariance, but in such a way that I still leave behind an overall global Lorentz symmetry, or more precisely global Poincare symmetry. So that precise mechanism of breaking is really what's happening is you take the full diffeomorphism group and you have an internal Poincare symmetry, and the symmetry gets broken down to the diagonal one. In the case of bigravity, this is just where if you have 2 metrics, both have a separate diffeomorphism symmetry a priori, but when you couple them together, that gets broken to the diagonal one, and that's how you generate a mass. So both pictures are just the same. So explicitly how this is achieved as follows. The analog of the VEV of the Higgs field in the spin 2 context, what the analog is itself a spin 2 object, and is essentially what we would call the reference metric. So you need some fixed reference metric around which you define your massive gravity theory. But this reference metric can, by means of the Stuckelberg trick, be written in a covariant diffeomorphism invariant way by simply saying the Stuckelberg trick says I'll do a gauge transformation, which in this case is a diffeomorphism, a general coordinate transformation, and I promote the gauge parameters to fields. So in this case, if I take a metric and I ask how does it transform under diffeomorphisms, it's just this. This is the new metric in the new transformed frame. And then I just take the coordinate transformations, which are here labeled by phi a, and I promote them to fields, and those are the Stuckelberg fields. And in this way, we can construct a theory, effective theory for massive spin 2 particles, which is completely diffeomorphism invariant by means of the Stuckelberg trick. Now, just as in the spin 1 case, making a spin 2 particle massive introduces new degrees of freedom. A massive spin 2 in 4 dimensions has 5 components, whereas a massive one only has 2. So we have 3 new degrees of freedom, and those 3 come in the form of an extra vector, which carries 2, and an extra scalar, which is the helicity 0 mode. And they're essentially naturally built into this field phi. as the vector is just the vector perturbations of that, and the scalar is the ones which the derivative of the scalar comes in that field. And this is explicitly the velocity zero mode of the massive spin 2 field. And indeed, you can make this more manifest by, if you take this tensor, which I'm constructing, let's just forget about the Listy 1 modes for simplicity and focus on the Listy 0. By its natural normalization scale for its interactions turns out to be the scale lambda 3, lambda, I call it lambda 3, which is lambda 3 cubed, which is related to the square of the graviton mass times the Planck scale. So if we forget the Listy 1 mode for a second, rather interestingly, a diffeomorphism is naturally a squared thing. Because it's a spin 2, because I have to transform two things, I naturally get the Listy 0 mode combination of two derivatives of pi in a squared form. So if I want to naturally isolate the interactions of the Listy 0 mode, the natural thing to do is actually take a square root. So I take this reference, this now Stuckelberg reference metric, multiplied by the inverse metric, and I take the square root of that combination. That square root combination is exactly proportional to just the double derivatives of the Listy 0 mode. And that plays a crucial role in these theories. In fact, this double derivative of the Listy 0 mode shows you that the Listy 0 mode in massive gravity theories is essentially going to be a Galilean theory. Why? Because if all the interactions enter with two derivatives acting on the scalar field, then there is a simple global accidental, it's really accidental, global symmetry that emerges, which is where if I take pi and I shift by a constant plus something proportional to x mu, v mu, x mu, the double derivative obviously is left invariant by that transformation, because if I do two derivatives on x, it goes to 0. So there is an emergent Galilean symmetry in massive gravity theories in which the Listy 0 mode is the object playing the role of the Galilean. And that's how you can see how to construct the consistent interactions in these theories, because we know for Galileons how to write down their, for example, the interactions of them that preserve second order equations of motion. In fact, the simplest way, just for pure Galilean, if you have a scalar field pi and you want to write down all those terms which respect the Galilean symmetry and lead to second order equation of motion, it turns out they're all naturally written down with using the two copies of the Levi-Civita symbol, where I take contractions of the Minkowski metric, double derivatives of the scalar, basically in pairs, AA, BB, CC, DD, and then I multiply overall by pi. And you can, if you work this out, all the contractions, this is just pi box pi, and this is pi d pi squared, the cubic Galilean term, and this is the quartic Galilean, and that's the quintic Galilean term. And there are also natural interactions of the Galilean with helicity, massless helicity 2, where you do the same construction. If you take two epsilons and you contract with two etas, a single h and two dd pi, these interactions are invariant under massless spin 2 gauge transformations for h and the Galilean symmetry for pi, and lead to second order equations of motion. And it's exactly these interactions that naturally emerge in the decoupling limit of massive gravity theories. And so it allows us to infer what the nonlinear Lagrangian has to be. You basically make use of precisely this double epsilon structure, which you get in a determinant. And you can see that all the, and also the fact that dd pi arises from the square root of g minus 1 times a reference metric, allows us to figure out what all the relevant mass terms are that lead to second order equations of motion. And as I say, that in the low energy limit of these theories, the dominant interactions are determined by the helicity 0 mode at a scale set by lambda 3 scale, which is m squared m Planck. And that really that determines most of the phenomenology of these theories. Now, in a general effective field theory, there's in fact no requirement that we should restrict only to operators that lead to second order equations of motion. There are other higher derivative operators that will naturally emerge when we do quantum corrections and so on. But we can very naturally write these down in this language. If the building an effective field theory for a massive spin 2, in which the cutoff scale is λ3, so the leading interaction scale is this λ3 scale, then we would naturally write down an infinite number of local operators with arbitrary numbers of derivatives and powers of curvature and so on, all naturally suppressed by this λ3 scale. And because those operators are generally higher derivative, they have less significant impact on the low energy physics, and the low energy physics is dominated by these particular leading terms, which is often called the ghost-free massive gravity terms, or the DOGT Lagrangian. Now, that particular story I've given you is just a particular example, but it's really a generic one. And a generic ion modification introduces new physics. If you want to change physics in the IR, by which I mean cosmological scales, we're introducing some new physics scale M, which typically we take to be of order the Hubble scale today. But in the process of doing that, there's always some intermediate scale between the scale M and the Planck scale, at which something else happens, some other non-trivial physics comes in. And in Lorentz invariant massive gravity theories, this is precisely this λ3 scale. The same story I've just said works for bigravity. If you like working with bigravity, where you have two metrics, and those metrics are interaction, the same symmetry breaking goes on. You have two copies of diffeomorphism symmetry, and they get broken down to the single diffeomorphism symmetry. So you have the same amount of breaking. So you also have to perform the Stuckelberg trick. The natural Lagrangian is basically built out of the same square root structure, just identically. And as I say, because you're breaking the same amount of symmetry, you're breaking one copy of diffeomorphisms overall, because you have two copies and you break down a single one. You also, in order to capture the additional degrees of freedom you have in a massive bigravity theory, it's also natural to perform this Stuckelberg trick. Although interestingly, it's not clear, because both metrics are dynamical, you have a choice of which one you want to do. You could either do it on the F metric in analogy with what we did before, or you could do it on the G metric. But either way, in the decoupling limit, bigravity also looks like a Galilean theory interacting with two massless gravitons. Because if the decoupling limit is defined by taking the graviton mass to 0, such that the helicity 2 modes effectively become massless, but you still have the helicity 0 mode of the massive spin 2 mode, which interacts via Galilean interactions. There are many extensions of this story. Basically, essentially all the Lorentz invariant massive, both soft and hard mass theories look like Galilean theories in a particular limit. In fact, this was recognized already in the DGP model. The Galilean was actually a discovery of the DGP model, which was a soft massive gravity theory. All this does is demonstrate with all the hard massive gravity theories, whether they're a single massive or multiple massive, multi-gravity, whatever you want, they all give rise to Galileans in a particular decoupling limit. I'll skip that. And that brings us to the observational. That was sort of a lightning cursory review of the theoretical construction of these models. But as I say, one of the key features is the emergence of these Galilean fields, these accidental Galilean symmetries, fields which are describing in these theories the helicity 0 mode of the massive graviton states. And they interact at a much lower scale than the Planck scale, this λ3 scale, and that's why they control most of the nonlinear phenomenology. So we may ask, what are the constraints on the graviton mass? And that comes from many different sources, many different implications of what giving a mass to the graviton would be. So one thing is, let's say if we give a graviton a mass, eventually you get Yukawa suppression for all the forces. The inverse square law essentially gets cut off exponentially. So some constraints come from that particular aspect. Some constraints, such as the ones from LIGO on the graviton mass, come from the modification of the dispersion relation. Obviously, having a mass for a graviton means that things don't travel exactly at the speed of light, and that has an effect on the overall squeezing of the LIGO waveform. And then the other constraints come from the fact that deep down you have additional degrees of freedom. So because we have these additional helicity 0 modes, they can propagate what we'd call fifth forces, additional forces beyond the normal GR ones. And they can also radiate. Because you have additional gravitational degrees of freedom, you can radiate into these additional scalar modes, just like you can in the scalar tensor theory. So I'm not talking about scalar tensor theories per se, I'm talking about theories of massive spin 2, but the end product is that they effectively behave like scalar tensor theories, which the scalar looks like the Galilean, and therefore we can have all these sort of observational constraints on the addition of those things. Traditionally, the strongest constraints on these classes of theories actually come from fifth force bounds, such as lunar laser ranging and so on, as was first noted for DGP and so on. But I'm actually going to talk mainly just for the rest of the time about the extrascalar gravitational radiation. So in order to understand how the physics of these models work, the key thing is to recognize the Weinstein screening mechanism. So Claudia already mentioned that most of these modified theories, they introduce new degrees of freedom, which we don't necessarily see. And so often we need a screening mechanism to explain why we haven't seen them. In these theories of massive gravity, we don't need to introduce a screening mechanism. One is built in. And it's called the Weinstein mechanism because the fact that it was built into massive theories was first recognized by Weinstein back in the 1970s, although how we explain that now is in slightly different language than what he did. And roughly the way this works is as follows. In general relativity, the scale at which the interactions of the Felicity 2 mode become nonlinear for a given source is essentially the Schwarzschild radius. That's intuitively obvious, right? If you put a source in a metric, the scale at which the coefficients of the metric become of order unity, depart from, become significant, is the Schwarzschild radius. That's when everything becomes clearly nonlinear. If you're well away from the Schwarzschild radius, then the metric is roughly Minkowski plus a small perturbation. So Schwarzschild radius sets the scale at which the Felicity 2 mode become nonlinear. It says the scale of the interactions of Felicity 2 modes. In these massive gravity theories, we have additional states, such as Felicity 0 modes. But their interactions are not set by the Planck scale. They are set by this new scale, lambda 3, which is energetically is much lower than the Planck scale, and therefore is a larger distance scale. And that means that the effective Schwarzschild radius for the Felicity 0 modes is something called the Weinstein radius, and it's a hugely much bigger scale. For this, sorry, I've written it in those pictures, it's actually this scale. It's a hugely much bigger scale. It's much bigger than the size. So for example, for the sun, taking the sort of standard choice of parameters, the Weinstein radius ends up being the size of parsec. So it's a gigantic scale. So it's a very different phenomenology because we normally think of, we don't need to worry about Schwarzschild scale physics where gravity spin 2 becomes nonlinear, but we are very much inside the region in which the Felicity 0 modes are nonlinear. So if you like, from the point of view of Felicity 0 modes, it's like we're inside the black hole in these kinds of theories, because although it's not quite like being in a black hole, but we are very much in the region where the interactions of Felicity 0 mode are nonlinear. And that has to be accounted for in all the phenomenological predictions. Now, the effect of being inside the Weinstein radius is essentially to suppress the contribution of the normal inverse square law in such that the fifth forces are screened, and so they get dropped out. And calculationally, if you just take two static sources and you ask how the static force behaves relative to that in the normal inverse square law force, it gets suppressed. Outside the Weinstein radius, it's approximately 1, but inside the Weinstein radius, it goes to 0 at a particular rate determined by the 3/2 power, at least in the case of cubic Galilean or DGP, the 3/2 power, and goes to 0. And this is the effect of the screening. The fifth forces becomes negligible as we go deep inside the Weinstein radius. And that's why it's so crucial the Weinstein radius is so big, because we are very deep inside the Weinstein radius of the sun. For example, we're at a very small distance relative to the parsec scale, which is the Weinstein radius for the sun. And therefore, the fifth forces due to these additional zero modes are essentially highly suppressed within our local neighborhood. However, we still have these additional polarizations that we can radiate into. And so we still have to check, and this is not less obvious, that we're not radiating into them so much that we can use, for example, the constraints from the Hulse-Taylor pulsar and other pulsars on the spinning down of the orbit, which we know to be beautifully fitting with general relativity. We have to check that we're not radiating into these additional scalar gravitational waves. And to do that, we need to basically, again, account for how the Weinstein mechanism works. So let's imagine now a binary system. Think about the Hulse-Taylor pulsar, if you want, as an example. So we have a pulsar here, a binary system which is orbiting around itself. The distance that has a particular length scale, the distance between the two objects, which is typically much larger than the Schwarzschild radius for the system. It also has a scale which is set by the rotation frequency. So as they rotate around, they do so at a given frequency. And typically they're non-relativistic, and therefore the scale, the length scale, which is the inverse frequency scale, is parametrically larger than that scale. But in turn, the Weinstein radius for a typical binary pulsar, such as the Hulse-Taylor pulsar, is also hugely much bigger than that scale. So in particular examples, the inverse frequency scale is of order 10 to the 9 kilometers, but the Weinstein radius is order 10 to the 15 kilometers. So because of that hierarchy of scales, we can actually do a reasonable job of trying to analytically compute the scalar gravitational radiation by taking into account the background Weinstein screening and looking at perturbations around that from the source. So the way we do that is, let's just approximate the system by, as we said, in all these massive gravity theories, they look like Galileons in a particular limit in which the Galilean couples to the trace of the stress energy. So as a toy model for that, let's think about the cubic Galileons. We have a scalar field pi with a cubic Galilean interaction coupling to the trace of the stress energy. And let's take the stress energy just to be our binary pulsar system. So it's just a sum of two delta functions along the orbits of the system. And what we'll do is we'll approximate that by an overall total mass located at the center of mass, and then the fluctuations around that. And the total mass, if you like, the total mass of the binary system is the one that creates the overall background Weinstein screening. So what we do is we take the profile of the pi field, the Galilean field, can be taken to be the background field induced by the total mass of the binary pulsar as a source, which accounts for the overall background screening, plus fluctuations around it, which will be time dependent because the source itself is time dependent and orbiting. So the radiation for the scalar modes will be built into this part. This is just a background. However, it's crucial to account for this, take into account the Weinstein screening. Now, this part you can solve for exactly, given a delta function source, and account for it. And the effective equation for the fluctuations is similar to what Claudia mentioned earlier. Essentially, you get an effective metric. The effective metric determining the propagation of the helicity zero mode, the Galilean field fluctuations, is different than the Minkowski metric, and it depends non-trivially on the background profile. But nevertheless, those fluctuations are coupled to the fluctuations in the stress energy. Now, analytically, you can then go through and compute the power radiated. I'll just skip over the details because it's not too crucial. You can compute the power radiated in that field. And as I'm running out of time, I'll just mention the way we do this. Fortunately, the WKB approximation works well across the Weinstein region. So there's a way we can solve it analytically by matching across the Weinstein region into the region deep inside and the region outside in order to infer the total power. What you get, at least by this analytic approximation, is that the power is dominated, the power in the scalar radiation is dominated by the quadrupole radiation, just like in general relativity. That was not obvious because we're talking about a scalar. Scalars can make monopoles and dipoles, but it nevertheless the case is the quadrupole that dominates. However, if you look at how much radiation in this Galilean field relative to GR, it turns out to be suppressed both by the Weinstein radius, and by it's enhanced by the velocity of the system, but suppressed by the Weinstein radius relative to the frequency scale. Now, that analytic approximation can actually be backed up by numerical simulations, which we've done. This is actually for a cubic Galilean system. So this is explicitly what you're looking at is the scalar gravitational radiation induced by a binary pulsar. And you see what that naturally gives is the quadrupole. That obviously looks like a quadrupole signature. That's the quadrupole radiation from that. And when we compute the power in that quadrupole radiation, the numerical for a cubic Galilean, the numerical power fits well with what we expected on our analytic grounds, which is that you get this same, if you remember, there was two factors here. So you get an overall, if you compute it as a function of frequency of the binary system, it goes like 1 over omega to the 5 halves. That's the analytic answer. Numerically, you get more or less exactly that. So it's sort of more or less consistent. So what this is showing, is that the Weinstein mechanism is successful in killing off, suppressing the radiation into the additional scalar gravitational waves in binary pulsar systems, at least for the cubic Galilean. We're currently working on the quartic Galilean, which is a bit more numerically challenged to see if a similar phenomena occurs. Okay, so that was my, I think I've hit my time limit. So that was my sort of line-in review of massive gravity type theories. And the key points is to say that in these, at least if we focus on Lorentz invariant theories of massive gravity, in this broad sense of both soft and hard, what happens is inevitably, if we want to modify gravity in the IR, which is at Hubble scale today, we introduce new physics at an intermediate scale between Hubble and the Planck scale. And in particular, in the Lorentz invariant models, this is usually this lambda 3 scale. A common feature of all these models is in a particular decoupling limit, where a particular range of energy scales, the physics is dominated by the interactions of helicity zero mode, and that helicity zero mode looks indistinguishable from a Galilean theory. You get this accidental Galilean symmetry emerging. Crucially, though, the full theory is not a covariant Galilean or a Horndeski type model. And that's important to stress. The covariantization of the Galilean is not necessarily the covariant Galilean. Massive gravity or DGP model are examples of covariant extensions of Galilean, which are not the same as the covariant Galilean. The Weinstein mechanism really controls most of the interesting phenomenology, and at present it's only relatively poorly understood. It's well understood in the static context, where we can clearly say that fifth forces get killed off in the Earth-Moon system. In the time-dependent ones, it's a bit more harder to calculate what's going on. So I shall leave it there because I think I've hit my time limit for any questions.
Okay, thank you very much for a really nice talk. Yeah, that was really interesting. So we have time for a question or two. Let's see, I don't see any questions on in the chat. So if you can raise your hand with reactions and then I can see you. Well,
there is one question in the chat I can see, which is what physics sets the Weinstein scale.
Oh, okay.
And there's a crude way to understand that, which is that, you know, if you take GR and you add a mass term, the mass term itself is you know, the curvature term, the Einstein-Hilbert term goes like is dimensions of mass squared, right? So it's inverse distance squared. So the scale at which the mass term becomes relevant is when the curvature is of order m squared, when r is order m squared. Now, if you estimate where that is for a point mass source, when is the curvature due to a source of order the graviton mass scale squared? That is basically what sets the Weinstein radius. So when the curvature is large, the Weinstein region is when the curvature is large relative to m squared, and m squared is irrelevant. And the opposite region is where it's the other way around.
I have a quick question. So you talked about two experiments, the lunar ranging and the binary pulsar. Are there any sort of future experiments that you could envisage that would get better constraints? Would one, for example, do better with an artificial satellite being tracked in the moon because it might be less complicated, no, tidal effects and stuff like that, or
that's possible. Yeah, I mean,
system background's too complicated.
Yeah, that's possible. I think if we make it too complicated, it's kind of hard to analytically say what's going on. But I think, both of those, it's important to stress both of those, the lunar laser ranging and the pulsars. If we take the typical scales, the effects that we're getting are sort of just below what we can observe at the moment, but they're not very far below. So even with the pulsars, we discover these things all the time. And if we happen to get ones with the frequency scales in the right regime and so on, it can already start putting constraints on particular models. We may just be lucky. I think what hasn't been fully explored as it should be, though, is the LIGO type constraints on these things. No, and I don't mean the ones from the dispersion relation. That's been explored. So just if you ask, how does this system modify a binary black hole merger? Well, the Weinstein still dominates that system because the black holes are very massive things and well inside the Weinstein radius. So most of the constraints on the graviton mass coming at the moment are from the constraints on the dispersion relation. And they're good, but they're not as good as some of the other constraints. But the real ones would be the real, I think, interesting ones that haven't been fully explored is just how, even though we're deep in the Weinstein region, so we expect that the binary black hole merger should still be dominated by GR. There's still going to be corrections to the horizon geometry and so on in these theories that could lead to, in the end, significant changes of the waveform. So that's I think the thing that's not been fully explored.
Okay, thanks a lot for this really nice talk. So this ends our session, and we're going to resume at 1:15 South African time after lunch. So have a nice lunch. Thank you.
For its dense animal population and the variety of its the boundary between South Africa and the mountain kingdom of Lesotho, and offers some of the country's most awe-inspiring landscapes. The name Drakensberg is derived from the Dutch, meaning Mountains of the Dragon, which truly captures something of the mountain's otherworldly atmosphere. Number 2, Kruger National Park. Covering a wide stretch of bush and savanna in the northern reaches of South Africa, Kruger National Park borders the countries of Mozambique and Zimbabwe. For its dense animal population and the variety of its flora and fauna, the park is considered the jewel of South Africa's extensive park system. Numerous well-kept tarred gravel roads have made the park a favorite choice for self-driving expeditions. Number 1. Cape Town. Located on the southwest tip of South Africa's Western Cape Province, Cape Town is the most popular tourist destination in all of Africa. The metropolis enjoys a mild Mediterranean climate, a well-developed infrastructure, and a spectacular natural setting. Cape Town's center is located in a relatively small area between Table Mountain and Table Bay. The city also serves as a home base for exploring nearby attractions, including the region's many diverse beaches, as well as the rolling hills and valleys of the winelands.
Standing on the world outside, caught up in a landslide, stuck still, colorblind. I'd be like hoping for a black and white. I gotta be my love for you. Gotta be mine. Feel it falling from the skies above you. Gotta be mine. My wave was shook, my demon in the dark. The blue tide's pulling me under. Are you my soul, my heart? Pull everything apart. Are you gonna be my love? Are you gonna be my love? Be like, are you gonna be my love? Are you gonna be my love? Be like, are you gonna be my love? Are you gonna be my love? Walking on the clouds unknown. I'd be like, I'd be like, I'd be like.
South Africa has all of the features that travelers long for in a vacation destination. Fine weather, gorgeous scenery, great beaches, modern accommodations, and superb cuisine. The southern tip of Africa also offers an exotic array of once-in-a-lifetime adventures, from off-roading on a safari to diving with great white sharks. It's hard to name another holiday destination that offers as much variety. Here's a look at the best places to visit in South Africa. Number 10. Blyde River Canyon. Blyde River Canyon is the second largest canyon in Africa, after the Fish River Canyon, although it is much greener due to its lush, subtropical foliage. Walking treks through the rich diversity of flora and fauna-filled canyon offer views of magnificent escarpments, waterfalls, and ancient geological phenomenon. Visitors have the opportunity to encounter all 5 of South Africa's primates here, as well as hippos and crocodiles near the wetlands of Swandini Dam. Number 9. Cape Winelands. The fertile valleys of the Cape Winelands are surrounded by majestic mountains, sleepy villages, fruitful orchards, and some of the lushest scenery in South Africa. Visitors can follow the wine routes of the Cape to visit the vineyards of the country's finest winemakers, whose sherries, ports, brandies, and intriguing whites and reds are world famous for their delicate flavors and savorable palatability. Number 8. Addo Elephant National Park. Located in the Eastern Cape region of South Africa, the Addo Elephant National Park is one of the country's largest parks. The park is famous for its elephant population that has a special brownish skin color due to the red soil. Amongst the elephants, other animals like ostriches, antelopes, and warthogs can be seen. As part of the park's expansion, a group of lions and a group of spotted hyenas have been introduced to the park as of 2004. Number 7. Hermanus. Located on the southern coast of Africa near the Garden Route, Hermanus is famous for its shore-based whale watching. The sheltered, shallow waters attract southern right whales that migrate to the region each year to mate and breed. A 6-mile-long cliffside walk with built-in telescopes and benches offers visitors plenty of opportunities to view these social animals as they raise their flukes in the sea breezes. Whale-watching boat tours are available as well. Number 6. Durban. South Africa's second-largest city, Durban, is located on the eastern coast. Durban's subtropical climate, scenic beaches, and close proximity to Johannesburg have made the coastal city a popular vacation destination for South Africans. The English colonial architecture that once dominated the city has been enlivened by a mix of Zulu murals, Islamic mosques, Hindu temples, and Christian churches. Number 5. Huhlui Umfolozi Game Reserve. As the only park under a formal conservation effort in KwaZulu-Natal where you can see the Big Five, lions, elephants, leopards, buffalo, and rhinoceros, the Huhlui Umfolozi Game Reserve offers visitors wildlife viewing opportunities second to none. Wildlife enthusiasts may enjoy the vast expanses of native plants and native animals during guided walks, self-guided drives, or opt for a thrilling viewing experience by boat along the Huhlui Dam. Number 4. Garden Route. The Garden Route is a scenic stretch of the southeastern coast of South Africa. It extends from Mossel Bay in the Western Cape to the Storms River in the Eastern Cape. The name comes from the diverse vegetation encountered here and the numerous lagoons and lakes dotted along the coast. It includes some of the best places to visit in South Africa, including Knisa, Plettenberg Bay, and Nature's Valley. Number 3. Drakensberg. The Drakensberg is a mountainous region that forms the boundary between South Africa and the mountain kingdom of Lesotho and offers some of the country's most awe-inspiring landscapes. The name Drakensberg is derived from the Dutch, meaning Mountains of the Dragon, which truly captures something of the mountain's otherworldly atmosphere. Number 2. Kruger National Park. Covering a wide stretch of bush and savanna in the northern reaches of South Africa, Kruger National Park borders the countries of Mozambique and Zimbabwe. For its dense animal population and the variety of its flora and fauna, the park is considered the jewel of South Africa's extensive park system. Numerous well-kept tarred gravel roads have made the park a favorite choice for self-driving expeditions. Number 1. Cape Town. Located on the southwest tip of South Africa's Western Cape Province, Cape Town is the most popular tourist destination in all of Africa. The metropolis enjoys a mild Mediterranean climate, a well-developed infrastructure, and a spectacular natural setting. Cape Town's center is located in a relatively small area between Table Mountain and Table Bay. The city also serves as a home base for exploring nearby attractions, including the region's many diverse beaches, as well as the rolling hills and valleys of the Winelands.
still colorblind. I'd be like hoping for a black and white. I gotta be my love for you. Gotta be mine. Feel it falling from the skies for you. Gotta be mine. My wave, my stroke, my demon in the dark. The blue tide is pulling me under. For you, my soul, my heart, pull everything apart. Are you gonna be my love? Are you gonna be my love? Be like, are you gonna be my love?
Hello.
Hi.
Hi.
Lovely to see you.
Lovely to see you also, right?
Yes, yeah.
Hello, Ramesh.
Hi, Sudan. It's a very strange way of meeting, but anyway.
Yes, sir.
Yeah, it's not bad.
Naresh, it does have certain advantages. It does have certain advantages of keeping people at arm's length. I mean,
I know who is speaking. Yes.
It's nice seeing you. It's nice seeing that you are. You're looking okay.
No, or rather, you are still surviving. Yes.
Yes. I was trying. I couldn't quite find the words to put it quite like that. I mean.
Yeah. I knew.
But you understand intent.
Of course, yes.
Yes. So we have another 2 minutes. So Naresh, you have 45 minutes. Well, 40 minutes really, and 43 minutes. We can leave a minute or two for question time. Then.
Oh, but maybe you just give me a 5 minutes warning on that.
Yes, I'll give you 5 minutes warning. I know you get very emotionally carried away with the presentation, and
no. This time probably I won't last that long. There's nothing much to say.
We send out a chat message saying 5 minutes remaining, but no one listens to us.
No one.
Sunil will get up and start to clear his throat, and you know it's time.
I'll wave my hands. I mean.
Yes.
We still have another minute, so let's give it some time, because some people will connect late, and.
Well, it's after lunch. You see, it's the people always get little sleepy. Yes.
Yeah, there's about 50 participants. You have a big fan following, Naresh. I mean.
No.
You can start on time.
You record.
Yeah, okay. It's not yet 1:15. Just give it another minute.
I have a backup of your PDF, so in case you get stuck, I can come in.
I know that's why I sent you.
Yeah.
Okay, it's 1:15. We should start. It's my pleasure to welcome the three speakers for this third session for the Gravitex conference. And all three.
Yes.
So welcome to this third session. In some way or the other, all three speakers have one common factor in addition to the research expertise. They all have some connection to researchers and research groups in South Africa. So the first speaker is going to be Professor Naresh Dadich. Professor Dadich is Emeritus Professor at IUCA. He's a long-standing researcher in general relativity, cosmology, modified gravity, and various applications. He was one of the founders of IUCA. IUCA, for those who don't know it, stands for the Inter-University Center for Astronomy and Astrophysics. It's a wonderful research institute, beautiful buildings, and it's one of the premier research institutes in India. He also served a term as a director of IUCA. And Naresh is now formally retired, so he's had time to grow a beard. He still remains active. There's time to remain active in research, and the papers and ideas still flow at a constant rate. And Naresh has had a very strong influence in the lives of many researchers, and he's motivated many young researchers to enter the subject. And he has strong research links with research groups around the world. And in the past, he would have been traveling a couple of times a year, and I'm sure this COVID has really affected that movement. So Naresh, I think you can go ahead and start your presentation.
Thank.
Share your screen.
I share screen, but what is happening? That's something. What
do I have
to? No, I'm clicking on the share screen, but
just give it a few seconds, maybe.
Yeah, yes. Let's also. Should I get out and start again?
Just wait a moment. Sudan, from your side, is there anything?
I can share the screen if you want. You just have to say.
No, but no. But then you have to do everything I had. Can I
restart?
Roll on the slides?
Yeah, restart.
Oh, restart. Okay, let me leave.
He's back.
He's back. Yeah. Okay. Oh.
It was working. We're seeing the wrong screen. We are seeing your Zoom screen.
So what do I do for that?
Close the share.
Oh, just a minute. You mean to close all others, right?
Now just close share. Stop share.
Oh, stop share, yes.
Go back to share.
Go back to share.
Your screen.
Yes.
And now you've got a number of screens that appear. They choose the one with your slide on it.
Oh, but which one is the most first? Oh yeah, here. No. Okay,
Yeah.
Again.
No, you back to the same one. You have to stop it and go do it again. I again log out and come back again. No. You don't have to log out. You now share screen. There will be multiple screens there. You have to choose the one that you want us to see. We don't want to see the Zoom one. We want to see the slides, book dial, compact sphere.
Yeah.
Click on that screen. Click on the book dial screen and then say share.
But I don't see the slide here. The screen.
Let me help you from this side then.
Okay.
You just say next slide.
Yes.
Okay.
I think, Sudan, you better do that. Otherwise, we're losing a lot of time.
Okay. Yeah, that's it. Okay. So first, greetings to all friends in UK in particular and all other friends around. I'm going to talk about the Bookdal compact sphere bound, gravitational field energy and escape velocity. Like as Sunil said, that I happen to have a very strong link with his department. As a matter of fact, this talk actually originated from a discussion I had with D2 some 4 or 5 years back. And I thought it is the right time to start with this. Okay, so the next slide. So compactness of an object like a star is an important issue in astrophysics. And stars, as we know, are the basic building blocks of the structure in the universe. Now the question is how compact could it be? Of course, we know that the most compact thing is a black hole. So then question is, how close could one go to a black hole? And the compactness is usually measured by the compactness ratio, m over r, mass over the radius. Now, this should naturally depend upon the fluid interior, its equation of motion, binding energy, other fluid properties. Next. Next slide, please. Now, you have a very common sense thing that how will we define a compact object? And that common sense idea is that the one which cannot be compressed any further. Now let's ask the question is, do we have any solution of the Einstein equation describing this incompressible fluid? And the usual normal answer is the famous uniform density Schwarzschild interior solution. So this is actually the limiting equation of state that it cannot be compressed. So can we not get the compactness limit simply by this interior solution? In our usual notation, It's the standard things. All these things are known to you. So you have a central pressure you would like to be finite. Density is constant. And the two parameters you have, this constant A and B. So A should be greater than equal to B, so as to the proper time d tau doesn't become negative of the coordinate time dt. And that determines A greater than equal to B actually translates into M over R less than equal to 4/9. And this is the Bugdal sphere limit, so Bugdal's compactness bound. So this is a very a common sense way of getting the Bugdal compactness limit. Next. Now, the story began in 1959 when Bugdal considered an isotropic perfect fluid interior with density and pressure being positive and density decreasing outward. And of course, the interior is matched to the Schwarzschild exterior at pressure 0 at the boundary. Under these very general conditions, he obtained the bound M by R less than equal to 4/9, or otherwise the R greater than equal to 9/4M, which is greater than 2M. So it is slightly larger than the Schwarzschild radius. This bound saturates, that is M over R equal to 4/9, when the central pressure tends to infinity. Now, this bound is also generalized to pure Lovelock theory. Now, what we mean by pure Lovelock, so first let us see that Lovelock is the most natural higher dimensional generalization of general relativity. It's like X is a homogeneous polynomial in Riemann tensor. And its most remarkable property is that though the Xn is polynomial in Riemann, yet the equation of motion, which you get by varying with respect to the metric, still remains second order. No other generalization retains this very important property, and you want second order because you don't want undesirable features like ghosts, etc. But here we were not saying pure Lovelock, but we are saying not Lovelock in general, because you have each order comes with a dimensional full coupling constant. By pure Lovelock, we mean that the Xn has only one nth order term. It has no sum over the lower orders. And why it has been singled out by two very general basic properties. One, that Einstein theory is kinematic in 3 dimensions. That is to say, the Riemann curvature is entirely given in terms of Ricci. So Ricci equal to 0 implies Riemann 0. You don't have a non-trivial vacuum solution in 3 dimensions. Or other way to say, the Weyl curvature is identically 0. The question is, can we universalize this property? And the answer is yes, the pure Lovelock does this, as the Einstein is n equal to linear order Lovelock, n equal to 1. So that is to say, the 3 dimension will be 2n plus 1. So by defining the Lovelock analog of the Riemann tensor, Lovelock-Riemann, we are able to show that there exists no non-trivial vacuum solution in all critical odd dimension d equal to 2n plus 1, where n is the degree of the Lovelock polynomial. So this only happens only for a pure Lovelock and no other. There is another very physical motivation for this, that any theory of gravity or any long-range field theory like Maxwell theory or gravity, there must exist bound orbits around a static object. And if you take this property, then you say that in Einstein theory, the bound orbits can exist only in 4 dimensions and none else. So if you want to go to higher dimension, and still if you want to have a bound orbits, then it again uniquely picks out pure Lovelock theory. So that's how we come to the pure Lovelock. Now, so that your the Bugdal limit M over R as 4/9, it now takes this form as in this equation 5, where M over R raised to n, because this is the potential is a nth order here, and n is as defined here, d minus 2n minus 1 over n, which is 1 for d, n equal to 1, d equal to 4. Let's go to next slide. So there have been some alternative derivations of the Bugdal limit. The same bound was also obtained for anisotropic fluid by considering that the strong energy condition is satisfied. Matching at the boundary is done by the radial pressure to be 0. And Anderson and these people obtains the same bound, and the bound separates for a thin cell where twice the transfer pressure equal to the metal density. When we should see the saturation always occurs either in the uniform density case, where the central pressure goes to infinity, or in this case, you have an infinitely thin cell. Next. No, there should be one before this, I guess. Next. Yeah, this is the one, yeah. Now you ask what happens when electric charge is introduced. So if that object is a charged object, then we all know that the charge introduces a repulsive part. So the effective gravitational mass becomes m minus q square by 2r. They're following the same kind of a Bugdal procedure, that metal density is decreasing outwards while the charge density is increasing outwards. And the interior is matched to the Rystrom-Nordstrom exterior at pressure 0. Now this was obtained, considered by Giuliani and Rothman in 2008. They considered a uniform density distribution enveloped by a thin charged shell, and they obtain this beautiful simple result, the equation 7, that m by r is less than or equal to 8 by 9, and then this thing on the down, and where alpha square is the square of charge to mass ratio. And as expected, it reduces to the Bugdal limit when charge is 0. One interesting thing comes about is the upper bound on the charge here is 9 by 8, which is greater than 1. And so a charged object in principle could be overcharged relative to a charged black hole, because the charged black hole's extremality is alpha square equal to 1. Here, charge can exceed mass. So now this we obtain. This has been obtained for a charged object, following actually the on similar lines as the Bugdal. Next. Alternatively, Anderson considers various, this has been done by various people, Anderson in particular, for various kind of distribution where the fluid distribution is not uniform, and it obtains the equation 8 as the compactness limit, which again reduces to the Bugdal limit for Q equal to 0. But it has a strange thing that when Q square equal to M square, this goes to M over R raised to 1. So in that limiting case, the boundary will become a null boundary, concise with the black hole horizon. Now, few things, a couple of points about this limit. One, you see that this is an involved expression. It's not M by R given in terms of the charge to mass ratio like alpha square the previous time. It's an involved equation you have. Secondly, this itself doesn't contain any extremal limit. It doesn't restrict charge. You can't say, now here we put the charge to mass ratio only to unity, because you can't go below that's where you touch the horizon. So what you want to say here the compactness in this, according to this, is extends all the way down to the horizon. And that's that. So that's now this again saturates for a thin cell where the twice transfer pressure equal to the matter density. And it has earlier been also considered this saturation is where rho m plus q square by r4, that is the matter density and the density due to the electric field are constant, copper stock and fluorides, and with that demanding that the pressure, central pressure goes to infinity. So the two limits are distinct and different. And here we are not concerned about the relative merits of these things. Rather, we would like to come to focus on a new prescription for the Bugdal sphere. Next. So now, again, you simply ask the question is that without referring to the interior, can we work out the compactness limit? Could exterior solution play a role in determining the compactness bound? And obvious, perhaps you will say that no, because it really depends on internal structure, equation of state, binding energy, etc. However, we do know one thing. The analog of binding energy is gravitational field energy. And because the two are defined similarly, the definition of the two is similar, the total energy minus the matter energy. The total energy contained inside some radius R, subtract the matter energy from this, that will give you the binding energy. The difference is this, the binding energy is evaluated in the inside of the star, where the gravitational field energy is outside. And at the boundary, two coincide, they two agree. So could one be construed as reflection of the other? So let's see what a question you have. We can, however, ask the simpler question. Let us try to first translate the Bugdal bound in terms of the gravitational field energy. Then you may say that we are on a much slippery ground of gravitational field energy. How do you evaluate gravitational field energy? Because the energy by itself in a general relativity is a very ambiguous quantity, and more so the gravitational field energy. However, there does exist one very reasonably good and very acceptable definition due to Brown and York. Brown-York quasi-local energy. And in particular, like you have a positive mass theorem, the positivity of the Brown-York energy has also been proved by Liu and Tao. Next. So what is the Brown-York construction? Consider a time-like cylindrical region bounded at two ends by two surfaces. The total energy contained inside this inside into this time-like three cylindrical region is given by the integral k minus k naught, where k is the extrinsic curvature, k naught is the extrinsic curvature of some reference space-time, say asymptotically flat, the Minkowski space-time at infinity. Q is the determinant of the two metric of the two-dimensional surface. The two-dimensional surface which is bounding. Now, if you evaluate for the Rystrom-Nordstrom metric for a charged object, this comes out, this equation 10, that energy contained inside a radius r is r minus square root of r square minus 2mr plus q square. Now let us try to expand it for a large R and see whether it gives us a reasonable accepted result. So this will be m minus q square over 2r minus m square over 2r. So what you have? So what the entire picture is in the Brown-York thing, that at infinity you have a mass which is infinitely dispersed, and that is, say, let us say it has a mass m. Under gravity, it collapses. As it collapses, it picks up gravitational energy. So then when you are considering the total energy inside some radius r, then that you have to subtract out the energy, the gravitational energy which is lying outside of the radius r. So what you would expect is At the Newtonian level, you will say the gravitational energy is minus m square over 2r. This has to be subtracted from m, so that's why it's in 11 you see it's m plus m square over 2r. Now the electric field energy is opposite. The q square by 2r is energy which is lying outside, because that q square by 2r, this is the positive. Electric field gives you the positive contribution. So electric field energy is q square by 2r, and which is subtracted. So at large r, it does give us an physically expected result, that m minus the electrostatic energy plus the contribution from the gravitational field energy. So now once we have this, so now since I have a total energy contained in this, now I can obtain the gravitational field energy will be the total energy contained inside the inside the radius r, subtract from it the matter energy, that is the non-gravitational energy. So E by minus E matter, so which is the E by is the first two terms, and the matter part is this. This is a non-gravitational energy, m minus q square by 2r. So this gives as a good measure of gravitational field energy for a static spherical object. Next. Now, so let's say, where does we first use this gravitational field energy? So let's consider can we define the black hole horizon in terms of the gravitational field energy? And it was long back I had proposed this, that the horizon is defined when the gravitational field energy is equal to the non-gravitational matter. There is the equipartition between gravitational and non-gravitational field energy defines the black hole and horizon. And let us verify this for the charged object. So so on the left-hand side, this is what we have computed earlier, that is your gravitational field energy. On the right is the matter energy. So you have this. Now, this equipartition, the two are equal only at the horizon. That defines the horizon r plus as m over 1 plus 1 square root of 1 minus alpha square. So this definition works very well. It is that the black hole horizon is defined by the equipartition of gravitational and non-gravitational. As earlier case, this also we have been able to generalize is to pure Lovelock gravity. Next. But how do we understand it? What does this equipartition physically mean? Why should we accept this? And for that, the physical reason is that the ordinary time-like particles feel the gravitational attraction grad phi, which is produced by the non-gravitational energy, it's matter energy. While the photons, on the other hand, they can feel no grad phi, they only feel the space curvature. And the space curvature is produced by the gravitational field energy, EGF. Now, at the horizon is approached, time-like particle tends to be null, or the ordinary particle tends to be a photon. So should there be their sources. So at the time like particles tends to be null, the source which produces the acceleration grad phi and the source which produces the curvature, they should also be equal. And that is why the non-gravitational and gravitational energy equipartition defines the black hole horizon. This is a very illuminating, insightful principle. And let us see whether can we, on similar thing, understand something of the Bugdal limit. Next. So we say, could we similarly also define Bugdal bound in terms of the gravitational field? And actually, this was the point which emerged when I had a chat with Ritu some 5 or 6 years back. So let's just ask this question. The gravitational field energy is some constant times the non-gravitational energy. What happens? And demand that what should be beta such that M over R is the Bugdal 4/9. And the answer comes out that the beta should be half. So what you say is that Bugdal bound or Bugdal sphere is defined by gravitational field energy being less than or equal to half of the non-gravitational energy. Now we said, let us universalize this, that this should always be the case to define the Bugdal bound. So make this as a general prescription. So again, let's verify it for the charged object. So this the gravitational field energy for the charged object is on the left, matter energy on the right, half of that, and that gives you M by R, the equation 17, which is the same what we obtained earlier by Giuliani and Rothman by following the Bugdal's procedure of matter density decreasing and charge density increasing. So fortunately, we get the same result. Now, this does not have to be. So there is something, this general principle is being followed so that it is and here, of course, this entire thing is all these calculations, computations are done by using the exterior solution, which is unique. So you have, anyway, so equipartition of gravitational and non-gravitational energy defines black hole horizon, while the former being less than or equal to half of the latter defines the Bugdal compact sphere. So that's that. Yet we don't, in this case, we do not really understand what, is there any physical reason for this factor being half? I don't. So let's, next. Again, you can go over to the pure lovelock, and this thing simply follows the same form. So this is the your Brown-York energy you have, where phi is m bar over n. M bar is the m minus q squared by 2r for the mass effective charge for the charged object. Yeah, and so what? So then again you demand the same thing, that let beta be the vector between the gravitational field energy and the matter energy. That gives you phi as equation 21, 2 beta over 1 plus beta square. Next.
You have 5 minutes, Naresh.
I have 5 minutes. Oh, damn it. So let's get over to this. Okay, let's quickly get. Now, so this gives you that the phi. So following the Bugdal limit, phi was determined as this, that the phi, the potential. If you, and here we obtained in terms from the gravitational field energy and non-gravitational as phi as this. And that determines beta. So beta gets determined this way where gamma is. So what really is happening is that, and again, you will say beta is half for when n equal to 1 or d equal to 4. And there is one very important thing is, or in all d equal to 3n plus 1, beta is half. Because in d equal to 3n plus 1, m phi is always m over r. Or that the gravitational potential always falls as 1 over r in d equal to 3n plus 1. Next. So another measure of the compactness, it could be the your escape velocity. So let's consider a particle at rest following from infinity. What velocity will it acquire? The proper velocity relative to a static observer, that turns out to be is equal to twice the potential, 2 phi. And this is your same as the twice gs Newtonian. And it is for this reason that the Newtonian thing also gives you the same r equal to 2 gm by c squared, the Schwarzschild radius. One has always been wondering that how does this, you get the same Schwarzschild radius from the Newtonian theory because of this, that in the radial fall, the Newtonian, the Einstein gravity plays no role because the gravitational field energy only curves the space. And the curvature of the space only you experience when you have a non-radial motion. That is actually, so the curvature gives of the space gives you the perihelion motion, perihelion shift, and otherwise it is duality. So Bugdal space is then always defined as this. So this is, you say, the in escape velocity. So given the n, and the d, and the Lovelock order of the polynomial, the v square is universal. That is, it is same for whether it is object is charged or uncharged. For n equal to 1, d equal to 4 and 5, v square is 8 by 9 and 3 by 4. So now you say for 4 it is 8 by 9, for 5 it is 3 by 4. So as d increases, that escape velocity is decreasing. On the other hand, your compact, so-called the compactness ratio m by r, that increases because it is 4 by 9 for 5 it is root 3 by 8, which is larger than 4 by 9. It is increasing. So now it is interesting question to say the compactness is determined by whom? The escape velocity or m by r. It stands to reason that more compact the object is, the escape velocity should be larger because the gravitational pull should become larger, so it should have this. So there is escape velocity which really should be a true measure of compactness rather than m over r. Of course, in all dimension d equal to 3n plus 1, 2 are the same because they both are determined by the go as m over r. Next. Yeah. So recalling this, so you, as a matter of fact, what you can say is in terms of the n, v square goes this, for a large n, v tends to 1, or the black hole becomes, the object turns into a black hole. So if the Lovelock order is increasing, of course, with the Lovelock order, the d has automatically increased because the dimension has always to be greater than or equal to 2n plus 2. So it becomes, so as n large, it becomes, the velocity becomes 1, turning to a black hole. Yeah, just 2 minutes, could you? Now the question is, so here, what we have here. So in general, this is what you will say, that the escape velocity is universal for a fixed d and n. And it turns out that m over r extremal, that is for q square by m square equal to 1 or whatever, or not for, no, the here the extremality is q square by m square is 9 by 8. Is twice of the Schwarzschild. Now this incidentally is very remarkable. That same result is for the black hole. The black hole extremal is greater than twice the Schwarzschild for the m over r for the black hole. So that's so this is always. Now the thing is this, that twice the gravitational field energy being equal to the non-gravitational energy, there has to be some underlying principle. This is what we don't really understand. And so, like, as I understand the equipartition thing, there was a very physical reason for this. But for here, I don't understand. One doesn't understand this. Of course, except that it all looks very nice, because whatever that this extremal limit thing have a for black hole, the same sort of a limit thing exists for the for the compact object. I think I should stop it. Thank you.
Paresh, thank you very much for the presentation. Sorry we had those logistic problems at the beginning, but you went valiantly on. Thank you for that. The time has passed, so can I suggest that we don't have any questions directly? We'll ask speakers to send questions to you on the chat group, if that's okay.
Fine with me.
It's fine with you. Okay. All right. So we then move on to our next speaker. Our next speaker is Professor Luis Herrera, who is Emeritus Professor at the Central University of Venezuela. He has association with several research groups and universities, and he has he's an established presence in the subject, working in areas of anisotropy, dissipative fluids, extended thermodynamics, relativistic astrophysics, polytropes, and things like that. He has generated many results over the years, and his work has had a substantial impact on researchers in many countries. I should point out to Professor Herrera that his work has also had an impact in South Africa, which is thousands of miles away from Venezuela, and several researchers are now entering the subject, and there are thriving groups on dissipative models. So over to you, Professor Herrera.
Okay. Do you hear me?
Yes.
Yeah. Okay.
You can share your screen.
Okay. 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 Thank you. Thank you very much. Well, I am going to talk about hyperbolic and symmetric cell-gravitating systems. And let me begin telling you how I came in contact with this kind of symmetry. It starts with the discussion I had.
Professor Herrera, we can't see your screen. Can you share your screen with us?
Okay, let me see what happened. Yeah, one moment. Okay, do you hear me?
Yes, we can hear you, but
okay.
there isn't a screen.
Let me. Okay. Okay, and you see my screen now?
Yes, please go ahead.
Okay, okay. Now, I was telling you that all these subjects start with a discussion I had with Lou Witten about the Schwarzschild solution, discussion we had a few years ago. And now the point is the following. As you all know, the only solution to the field, item field equation in vacuum, which is spherically symmetric and static, is the Schwarzschild solution. Now, by static, what you mean is that the metric admit a time-like Killing vector, let's call it C0, which is, furthermore, it is hypersurface orthogonal. We are talking about a static, non-stationary field. If you adapt your time coordinates to this Killing vector field, then the metric is independent on the time in that coordinate, and the cross term G0, 1, 2, 3 are 0. Now, spherical symmetry implied that the metric admit also 3 additional Killing vectors, which describe the invariance with respect to rotation. These 3 Killing vectors here. Okay. Now, when you write down the Schwarzschild solution adapt to these coordinates in polar coordinates, then you get something very well known, which is this one, where m is the only parameter of the solution, which is the total energy of the source. Now, written in this form, this line element, this metric is valid only for the region R larger than 2m. At R equal to m, we have here is 0, an apparent singularity, but since we know that the physically meaningful component of the Riemann tensor are regular at R equal to m, we know that this singularity can be removed by coordinate transformation. And in fact, very shortly after the Schwarzschild found his solution, Eddington already in 1924 proposed a coordinate transformation to remove the singularity and to extend the solution inside the horizon, inside for the region R smaller than 2m. After that, a lot of people have done work on that. I don't know, I need to recall that. But an important point here is that any transformation, no matter what, that allows you to extend the solution inside the horizon always produces a non-static field inside the horizon. This is a fact. You can extend the solution to the whole space-time, but always inside the horizon, the space-time won't be static. Or in the words of Rosen in 1917, any transformation that maintains the static form of this line element is unable to remove the singularity. Okay, so the space-time is necessary inside the horizon and non-static. This is easily to understood because R equal to m is a Killing horizon. Now, most people is satisfied with this situation, but Witten and myself, we were not satisfied with this. And our line of reasoning was the following. Any evolutionary process should lead eventually to equilibrium state. And at this equilibrium state, we expect to have a static solution. So what we want was a static solution everywhere, not only outside the horizon, but also inside the horizon. How to do that? How to do this? Obviously, you have to break the spherical symmetry because we know already that if you impose a spherical symmetry inside, the metric is necessarily non-static. So what we did was the following. We take the Schwarzschild line element, and then for R smaller than 2m, we propose the following line elements. This one. It is obtained via transformation of theta by I theta. This is an imaginary number. So this is a solution to the Einstein vacuum equation. It's very easy to see. It is static. It admits a time-like Killing vector, but of course it is not spherical symmetry. Okay, it is not spherical symmetry. As a matter of fact, this metric admits this Killing vector, these three Killing vectors, which are not the Killing vector of spherical symmetry. This symmetry is called hyperbolical symmetry. Now, at the moment we published with Witten the first paper on this subject, we were not aware of the fact that this kind of metric of symmetry has been treated in the literature before for several people. The first paper I have found is the Harrison in Physical Review D, and then there are many, probably more than the one I am indicating here. But none of these references deal with the specific model of black hole. They deal with the spherical hyperbolical symmetry in general, okay? So the general the model we proposed for the black hole was the picture is composed of two different metrics. Outside the horizon, you have the Schwarzschild solution. Inside the horizon, you have the solution I have just shown, which is hyperbolically symmetric. And so when you cross the horizon, there is a change in signature and in symmetry, spherical symmetry outside and hyperbolical symmetry inside. So that was our first proposal based on hyperbolical symmetry. Next, we want to study the motion of test particles in this spacetime. So we want to solve the geodesic equation for this spacetime and to check what kind of behavior they have. So you start with the Lagrangian, typically of this kind, where dot is the derivative with respect to the proper time. And then the Euler-Lagrangian equation are just the geodesic equation. Now let me summarize the result of this study. Well, one important conclusion is that in this case, any theta equal constant trajectory is unstable, except theta equals 0. All the other theta equal constant trajectory are unstable. This is at variance with the Schwarzschild case, of course. Next, any kind of geodesic in this spacetime must have necessarily R dot different from 0. So you may have purely radial geodesics, you may have geodesic in the R theta plane, or the general case. So let me first consider the radial case, geodesic moving along the radial coordinates. Then you have two constants of motion, which are E and L, the energy and the angular momentum. In this case, the canonical momentum P theta is not constant in general, okay? Then since I have already said that the only stable trajectory is theta equals 0, let's consider the radial geodesic along theta equals 0. And then you can integrate one of the radial geodesic equation for theta equals 0. And the first integral gives you this expression here. This is the energy, and this potential has a very simple form, 2 over y minus 1, where y is just dimensionless variable r over r. And the graphic of this potential is this one. So y equal 2 is the horizon. This is Schwarzschild. You don't need to look here. And this is our potential V. Obviously, the trajectory should satisfy E larger than V. So for this particular value of energy, particles only can move from this point to this point only. So particle may move from here, cross the horizon inward, but it will bounce here. And we shall see next what happens. But you can raise the energy as much as you want. The particle will never reach the center, never. So this is very different from the situation in Schwarzschild case, in the classical case, where any particle inside necessarily meet the center at some finite proper time. Here is the opposite. The test particle will never reach the center, never. The other important feature of test particle here is that in general, in this particular case, the particle may bounce at this point and may cross the horizon outward, which is forbidden, of course, in the classical, in the Schwarzschild case. So if you move the energy, for example, to this level here, then the particle may come from the infinite, cross the horizon inward, bounce somewhere here, and then get back to the infinity with any problem. So it can cross the horizon in both directions in this particular case. Next, it is interesting to consider the r theta motion, the motion in the r theta plane for any phi equal constant. In this case, the first integral of the radial geodesic may be written like this, where theta is 2m over r. So theta in principle change from infinity at the center to the horizon, which is 1. And k is a dimensionless canonical momentum. Prime here is derivative with respect to theta. So this is a kind of spatial equation. When you solve it, what you obtain is something like this. Now, the line from the length of the line from the origin to any point on the curve is theta, and the angle is formed with the horizon or horizontal axis is theta. So this is your horizon, and the center is at infinity. So you see that for different values of k, different values of the canonical momentum, the particle always remain inside the horizon, approaching the center but never reaching it. The center is at infinity. Higher the momentum, you get closer to the center, but you will never get the center. So this behavior suggests that there is the gravitation behavior as a repulsive force inside the horizon for this model. And this is in fact the case. And you can very easily check that by calculating the force acceleration of on a static observer inside the horizon. Remember that this is just the inertial acceleration which is necessary in order to maintain static the frame by canceling the gravitational acceleration exerted on the frame. Now, in the case of Schwarzschild solution, you get that the radial component, contravariant radial component of the force acceleration is positive, is pointing outward, which expresses the fact that the gravitation is attractive, is pushing the particle inward. So you have to push the particle outward in order to have a static observer. However, in our case, the radial component, the contravariant radial component of the force acceleration is negative. It's directed inward, implying that the gravitation is pushing the particle outward. So you have, as expected, a repulsive gravity instead of an attractive one. Now, once we have this behavior of test particle inside this space-time, we decide to study what is the general behavior of fluid, static fluid, which in principle could serve as sources for this kind of space-time. Now, the properties I am going to show you are independent of the adoption of this black hole model or not. You may not adopt this black hole model, and these are just the properties of any fluid which is endowed with hyperbolical symmetry. So we shall consider a fluid distribution, which is static in this case. It may or may not bounded from exterior with some hypersurface sigma E, and it will be bounded from interior, we shall see this, by some surface sigma I. This is so because we shall see that the fluid can never fill the central region. Now, the line element which admit the 3 Killing vectors satisfying the Killing equation for the hyperbolical metric is this one. This is a general metric which admit those 3 Killing vectors, which is endowed with hyperbolical symmetry. These two functions nu and lambda, because of the symmetry, only depend on the coordinate lowercase r here. So you may, since you have the line element, and if you provide the energy momentum tensor, you can write the field equation, the Einstein field equation. Now, the general form of the energy momentum tensor may be written like this. This is energy density, this is isotropic pressure, for velocity, and an isotropic tensor. Now, because of the symmetry, it can be shown that only two main stresses may be different. So the anisotropic tensor is described by the single scalar. So you may write in this form, which this is a unit space-like vector in the radial direction. Pi is the difference between the two different main stresses, which could be different. Now we define the mass function inside the fluid distribution as usual. No? You know that the parameter m, which appear in the Schwarzschild case, in the Schwarzschild metric or in our metric, may be written like this, where the R32 Riemannian component is calculated with the corresponding metric. Now, if you generalize this definition to any point on the fluid distribution in this way, but now this component of the Riemann tensor is calculated with the line element I have shown, you get this expression here. So this function is necessarily positive, of course, okay? And using the field equation with this expression, you obtain this expression for the mass function. So since it is positive defined, then necessarily must be negative. So one of the main features of all hyperbolically symmetric fluid is that the energy density is negative. Okay, the weak energy condition is violated. I should come back to this point later. Okay, this is necessary. The second important consequence is that if you evaluate the mass function close to the center, then it is very easy to see that m goes as r cubed approaching the center. And therefore, if you go to this expression here, you see that at some moment 1 plus e minus lambda will be 0, which is impossible. So there is a region, interior region, close to the center, where the fluid cannot be hyperbolically symmetric fluid. There should be another thing. For simplicity here, we shall assume that there is a cavity, vacuum cavity, inside which there is a Minkowski spacetime, surrounded this central region. You may assume another thing. You may assume another fluid with another symmetry. Well, in principle, so you may write m in this way. This is the absolute value of the energy density, and the integral is take values from some minimum value of r until the value you wish r, some lowercase r. Now, the generalized Tolpan-Oppenheimer Volkov equation, the hydrostatic equilibrium equation, look like this, which is very similar to the spherical case, except for the fact that you get here a minus and here you get a minus 2. Okay, and you have 2m minus r. Now, this is in general negative, and this is in general negative 2 because this absolute value is larger than PR. So this is positive as in the spherical symmetric case. So when you have a gradient, negative pressure gradient, this opposes gravitation. But now, since this term is negative, as we shall see now in a few minutes, then the inertial mass density will be negative. So a force pointing in some direction will produce motion in the opposite one because of the negative of the inertial mass density. We shall see this in a few minutes. But in general, the form of the Tolman-Oppenheimer equation is the same as in the spherical symmetric case. Now, in order to detect the repulsive character of the gravitation inside the fluid distribution, again, you calculate the force acceleration of the fluid, which is describe the inertial acceleration, which is necessary in order to maintain a static the frame by balancing the gravitational acceleration. And now you can see very easily that the radial component, contravariant radial component of the force acceleration is negative, implying that somehow the gravitational force is pushing the fluid element outward instead of inward. Well, we have found many such solutions, but we have no time to discuss them. And we also set up a general procedure to express any solution of this kind in terms of two generating functions, but we shall omit this discussion here. Now, the final point was how does this fluid look before reaching the equilibrium? How is the dynamics of this kind of fluids? This is the last problem. So again, the fluid distribution may be or not bounded from outside, but with this surface, and it necessarily will be bounded from inside by some sigma y surface. Now, the general form of incomoving coordinates of the line element admitting the hyperbolical symmetry is this one. It's this one, where A, B, and R are a positive function, and because of the symmetry function only of T and lowercase r. The energy momentum tensor, the general form is the same in form as in the static case, but it has now the dissipative term, where Q is a scalar describing the heat flux vector. It has only one meaningful component because of the symmetry. Okay. Again, the fluid may be anisotropic, but only two principal stresses may be different. Okay. And we may define, well, this is we are chosen co-moving coordinate, then V has only time-like components, and you may calculate the force acceleration, the expansion scalar, and the shear. The shear tensor is defined in terms of single scalar, which is given by this. Dot is derivative with respect to time-like coordinate. Now, the mass function in this case gives you this expression here. And now this term here is the so-called aerial velocity, okay? This is a change in proper time of r, and this should be less than 1. So the mass function is positive defined here, as in the static case, okay? If you use the field equation, then you get this expression for the mass function, and this expression for the, this expression too for the mass function in terms of the physical variables. Now, if you assume that R prime is positive to avoid shell crossing singularities, it's very easy to see that mu must be negative too in this case. And furthermore, you see that M approaches the center as R cubed. And then you see that at some moment, this will become negative because this is smaller than 1. And therefore, the center of the field distribution cannot be filled with this kind of fluid either, okay? You have to fill it with different things, or you assume that you have a cavity, vacuum cavity, and you have Minkowski inside it. Now, it is interesting to analyze the Euler equation, so the dynamic equation following from the conservation law. It takes this form or this one, which is much more interesting, this one here. Now, this is interesting, it has the Newtonian form. This is the proper time derivative of velocity, which is some kind of acceleration. This is the passive gravitational mass, which according to the equivalence principle is the inertial gravitational, the inertial mass density. And these are different force terms, okay? This is the gravitational term, and this is the gradient of pressure. This is the propel radial, this is the propel, the proper radial derivative. Now, suppose that you have negative pressure gradient. If you have a negative pressure gradient, it produces force pointing outward, no? in the direction of increasing R. This minus with this minus gives you plus. But since mu is negative, this term is negative too. And therefore, the pressure gradient, negative pressure gradient, produce a decreasing in the velocity u. So it compresses the fluid element in terms of expanding it. So it pushes the fluid element in the inverse direction that we have in the spherical symmetric case. And this is the spherical term. Now this is negative, and this is negative too. So if minus, this minus cancel the minus coming from here. So the gravitational term produces a positive time proper derivative of u. It pushes the fluid element outward, revealing the repulsive character of this gravitational force inside the hyperbolic symmetric fluid. Now, since we have dissipative fluid, we need some transport equation. So I have adopted here the Mueller-Rails-Stuber equation, which reads like that. This is the thermal relaxation time. This is the thermal conductivity. This is temperature. Okay. This equation in our case has only one independent component, which is this one. And when you put tau equals 0, you recover the Eckert-Landau equation. Now, there are two important differences and consequences from this equation here. The first one is when you look for the thermal equilibrium condition, Q equals 0. When you look for this condition, you get that this so-called Tolman condition, right? Ta prime equals 0, which amount to this equation. T prime is minus TAB. This is the Ford acceleration scalar. Now, since A is negative, this is positive. So the thermal equilibrium condition in this case implies that you have a positive gradient of temperature. This is at variance with the spherical symmetric case where you get negative gradient temperature gradients. The explanation is very simple. You have here a positive gradient of temperature implying an outward, an inward directed flux vector, heat vector, which is necessary to compensate the tendency of thermal energy to move outward because of the repulsive character of gravitational field. In the spherical symmetric case, you get a negative temperature gradient implying an outward directed heat flux vector to compensate the tendency of thermal energy to move to the center. So you see the difference between the two cases. And another important consequence comes when you couple this equation with the Euler equation. When you do that, you combine these two equations, you get this equation here. Now, it's very similar to what you obtain in the spherical symmetric case, but the physical meaning is quite different. Now, this is negative, because remember, this is negative in magnitudes larger than the pressure. So this term is negative, so the effect of the dissipation to the effective inertial mass is to increase the absolute value of the inertial mass density. So suppose you have a negative pressure gradient. The negative, which is this minus, is plus, and this gives you minus again. As we have saw, the positive pressure gradient push the fluid element inward. But now it does it weaker because the absolute value of the inertial mass density is greater. This is minus 2, and therefore the DTU is smaller. So this effect is smaller than in the non-dissipative case. In the spherical symmetric case, what you have is that this is positive, and therefore this term diminishes the total inertial mass density, and therefore the negative gradient of pressure push the fluid element inward stronger than in the non-dissipative case. In both cases, the effect of this term here is to enhance expansion, but it comes about from different terms in different ways. Okay. Well, we have found many solutions for this kind of fluids. I would like to show you just two of them. They were found under two conditions. One is the so-called quasi-homologous condition, implying that the velocity u is linear in the function r. This implies, because of the field equation, this condition here. And furthermore, we assume that so far that the so-called complexity factor, which is the trace-free part of the electric part of the Riemann tensor, vanishes. Okay, when you look for non-dissipative solution of this kind, you may obtain two different kinds of solutions satisfying this condition. One is a solution which is conformally flat, isotropic in pressure, non-dissipative, shear-free, and homogeneous in energy density. This is this solution here. But this solution is not geodesic. So it is a kind of Friedmann-Robertson-Walker for the hyperbolic symmetric case, but it's not geodesic. It's not geodesic. So you ask, well, what happens if I impose geodesic condition? If you impose a geodesic condition, then you get this solution. Geodesic, conformally flat, non-dissipative, shear-free, but the fluid is anisotropic and the energy density is inhomogeneous. So you have two solutions which need to be a reminiscence of the Friedmann-Robertson-Walker. One is geodesic, but is inhomogeneous and isotropic. The other is geodesic, but is inhomogeneous and isotropic. So in the spherical symmetric case, when you impose homologous condition, you get at once the Friedmann-Robertson-Walker condition. if the system is not dissipative. There is only one solution, which is the Freeman-Robertson-Walker. Here, if you impose a homologue condition, you may get at least two different non-dissipative solutions. This implies that somehow this kind of solution, this kind of space-time, provide a rich, a wealth of different kind of solutions, which maybe could be useful to describe different astrophysical or cosmological scenarios. So let me conclude with the general conclusion, with general properties. So the following features are the more remarkable of this kind of fluid. First, the energy density is necessarily negative. Now, I know that I am aware of the fact that from purely classical physical consideration, you expect energy density to be positive. But now there is a wealth of work of different people showing that if you expect quantum effect to be important, then you should expect energy density to be negative. So it's not a very strange scenario, okay? So this kind of solution may be useful for under very extreme conditions when classical quantum effects are expected to be important. The other important feature of this fluid is that they cannot never fill the central region. And this concords with the result we obtained shown in the geodesic, that notice particle with finite energy can reach the center. So the center is not reachable. And therefore, if you put a fluid, the fluid cannot fill the central region. This is due to the repulsive nature of the gravitational interaction within the field, within the fluid distribution. Now, we look for the Tolman condition for thermodynamic equilibrium, and what we found was the condition which is the opposite of the spherically symmetric case. Now you need a positive gradient of temperature instead of negative gradient of temperature. And furthermore, the modification produced by the effect of dissipative process on the inertial mass density point in the same direction to enhance the expansion, but in different way than in the spherically symmetric case. And then we obtain several solutions in the non-dissipative case, which may be considered as reminiscence of the Freeman-Robertson-Walker spacetime, but they are not exactly. In one case, the field is not geodesic, and in the other case, the field is geodesic, but is anisotropic in pressure and inhomogeneous in energy density. We have found also different solutions which are dissipative with the condition B equal 1, which seems to be very useful to describe situations where you have a cavity surrounding the center, but they are not very illuminated now, so I will not show here. So the conclusion here is that there seem to be a lot of different kind of cosmological astrophysical models endowed with this kind of symmetry, which in principle could be applied to different situations. Okay, we are right now expanding this study to the Lemaitre-Tolman-Bondi case. How to found a version of Lemaitre-Tolman-Bondi spacetime which admit hyperbolic symmetry, but we have not yet final results. Well, this is all. If you have any questions, thank you.
Thank you. Thank you very much, Professor Herrera, for a very nice talk. Can we invite questions? Please raise your hand, or you can send something through chat. Sudan, can you see anything from your side?
No, I'm not seeing any questions.
You're not seeing anything.
Okay.
So in the absence of questions, let's let's thank the speaker for a very clear and very thought-provoking talk. It's very interesting to see that one can interpret the matter, inside the event horizon in this very interesting way, and I'm sure it's going to generate quite a bit of interest. And can I invite participants, if they have questions in mind, to actually send those questions, and if they're shy to ask questions now, to send those questions directly to Professor Herrera directly. So Professor Herrera, thank you very much.
Thank you.
Professor Herrera, we have some time. Just one quick minute. Just want to mention something to you. Looking through your CV, papers, collaborators, there's lots of them, lots of papers, lots of collaborators. And I noticed that there was a very comprehensive review that you wrote with Professor Bill Bonner and on radiating stars in physics reports. And there was some other work done. Professor Bill Bonner from Queen Mary College, University of London. So I noticed that connection. I just wanted to point out to you that Professor Bonner had been a regular visitor of ours and had spent quite a bit of time with Professor Ellis in Cape Town, and then he also spent a couple of periods of visits with us at the University of Natal in Durban. It's just an observation.
Yes. Bill told to me about his interaction with South Africa. He spent 1 year or more in Cape Town, as far as I remember. Yes.
No, he did that. Okay, it was just an interesting connection. I thought I'd bring it to your interest, bring it to your attention. Okay, so with that, I was just hoping there might be something coming up. There hasn't been any penetrating questions, but I'm sure people will try to contact you later. So thank you again for your talk, Professor Herrera. And,
thank you very much.
And
Bye.
we look forward to interacting with you again in the future. So then we've got a couple of minutes, but I think we can go on to the next talk, if that's okay with you.
Yes, I think so. It's marginal. We are recording the talks as well, so it doesn't matter if somebody misses a couple of minutes at the beginning.
Okay. All right. So we then move on to our last talk for this session. And that talk is going to be given by Professor Salvatore Capozzolo. So then is Professor Capozzolo here? Okay. So
yeah, I'm here. Hello.
Welcome.
Herrera, if you can take down your screen. Prof. Herrera, if you can take down your share screen.
Not myself, Professor Herrera. I mean. Okay, yes. Thank you.
Yeah.
Your screen is still up.
Huh?
Your share screen. Are we still seeing his share screen?
Yeah. Now.
Hello.
Now it's okay. So I think we can see your screen, Salvatore. So it gives me great pleasure to welcome Professor Salvatore Capozzolo to this last talk in this session. Professor Salvatore, you are in a fortunate position because most speakers we tend to cut off because there's not enough time. In your case, you're getting a few extra minutes. So.
Okay, thank you so much.
So Salvatore, Professor Salvatore is a professor in astronomy and astrophysics at the University of Naples. And he has association with many different researchers and institutes, around the world. He has major research projects in general relativity, extended theories of gravity, And the main applications are in large-scale structures of the universe, gravitational lensing, galactic dynamics, and quantum phenomena linked to gravity. Highly published, and he has produced several books in the subject, and he's therefore a very strong and dominant presence in the field. And also, he has an interest in science development. He's been president of the Italian Gravity Society. He's been an editorial board of European Physical Journal C, etc. And like the two previous speakers, he also has links with South Africa. And yes. I believe that he's got strong contacts with the researchers at the University of Cape Town.
Exactly.
Thank you.
Specifically with Professor Dansby.
Dansby, yes.
Okay.
Over to you. We are in your hands.
Okay. Thank you so much. Thank you so much for for this kind invitation and to take part in this very, very nice conference, which is very enlightening. A lot of topics in gravity and cosmology. So in my talk, I would like to point out some important issues which could be connected with the fact that general relativity is not is a local theory. And then, according to this, what does it mean taking into account non-locality in cosmology, and in particular in some extended theory of gravity? And I would like just to convince you that if you take into account non-locality, this could give rise to very interesting phenomena, a part of several solutions in cosmology and in astrophysics. And then it could be a very, very natural way in order to address the problem of dark side of the universe, in particular, the problem of dark matter and of dark energy, due to the fact that non-locality gives for free some characteristic length, as for the first time has been noticed by Professor Deser and Woodard. And then, according to this, it would be a good way in order to try to get some interesting effective theories at a larger scale. Okay, so coming to my talk, the outline is this one. I would like just to discuss a little bit with you the meaning of locality and non-locality in physics, and then to specify what does it mean non-local theories of gravity, why it could be a very interesting approach in order to be developed in the realm of theories of gravity. In particular, I would like to focus on an approach, the Noether-symmetry approach, by which it is possible to find out and to select some theories with the sort of physical criterion. The physical criterion is the fact that some symmetries has to exist, and then conserved quantities should be taken into account. And then I would like to review the fact that taking into account some theories of gravity, in particular theories of gravity based on curvature, theory of gravity based on Gauss-Bonnet invariant, and then theories of gravity connected with the teleparallelism and then based on torsion, is it possible to construct some reliable cosmological models in which non-locality can be taken into account? Finally, I would like just to give you a sort of an overview of the possibility that if you take into account some astrophysical tests, it is possible to check if non-locality could be present at certain interesting scales, as for example, scales related with the galaxy or cluster of galaxy and so on. Okay, so let's come into the game and then consider what does it mean locality and non-locality. If you take into account locality, in some sense, in physics, you are dealing with the kinematics. In particular, when you are taking into account locality, you are dealing with the states. While, on the other hand, when you are considering non-locality, we are dealing with dynamics, and then you deal with interactions. And then any classical theory can be considered a local theory. For example, classical mechanics is a local theory due to the fact that any points of a tangent on a cotangent bundles can be exactly identified, for example. The same is for classical field theory. And then in such a case, you have a very straightforward approach to deal with tensor fields over manifolds. In particular, general relativity is related with this kind of approach. On the other hand, as soon as you are taking into account quantum theories, you run into non-locality. In particular, the Born interpretation of the psi function, and first of all, the Heisenberg uncertainty principle, put into the game the non-locality and the fact that you cannot give, as all of us knows very well, you cannot take into account the position and momenta under the same standard unless you have to face the problem of the uncertainty principle. Okay, so non-locality in physics can have a very, very prominent role. In particular, there are some fundamental interaction, as was pointed out for the first time by Heisenberg. For example, as soon as you are taking into account some one-loop effective action, in that case, you have to deal with non-locality. In particular, it is a very nice example of non-local Lagrangian is the so-called Euler-Heisenberg Lagrangian, in which you can see that non-locality comes out directly in connection with the electromagnetic field. And then this is a very, very interesting case of the fact that non-locality emerge a lot of time in physics. Another very interesting Lagrangian model in which non-locality is useful is the so-called Yukawa Lagrangian. Also, in this case, you can take into account an effective action, and you can deal with non-locality if you are capable of managing the operators which are running into the theory. In particular, in this case, this Klein-Gordon operator related with the Yukawa Lagrangian can give rise the non-locality, as you can immediately see in this example. Okay, but let us come more in detail on what does it mean local action and non-local action. In particular, local action means that there is a functional and you are taking into account only local fields. For example, you can have algebraic function of fields, or you can consider derivatives of these fields, and all of them are evaluated at some single point. So in some sense, physics is very, very well localized. So this is the standard paradigm for all fundamental field theory, both at classical and quantum level. On the other hand, when you are dealing with the non-local action, you have taken into account some functional, and in that case, you have non-local fields, at least one. So as soon as you have just one local field, you can deal with non-local non-locality. In particular, you have a function of fields, and they can be evaluated in more than one point, and then several times you face, for example, transcendental function of fields or their derivatives. So in particular, this is the standard which is requested in several effective field theory. So we can wonder if general relativity, which is a standard local theory, and quantum field theory, in some sense, can be related in order to encompass non-locality into their standard, and then try to see if this could be a good approach toward an effective theory of gravity that can be read as a sort of quantum gravity. In particular, we can deal with some shortcomings in general relativity could be addressed taking into account non-locality. And as you know, there are several shortcomings. For example, you have problems at infrared scales and a problem at ultraviolet scales. At a large scale, for example, you have that the acceleration, so the cosmic expansion. We have inflation, we have the galaxy rotation curve, and then we have to deal with the huge amount of dark matter. We have the fact that some stars escape the mass radius diagram for neutron stars. There are several neutron stars which are larger than they should be. And there are several problems related with the fine-tuning of cosmological parameters. In particular, as you know, there is this big problem with the H0 tension, sigma 8 tension, and so on. On the other hand, from the point of view of ultraviolet, you have the big issue of renormalizability. And then, according to this, general relativity cannot be quantized. General relativity cannot be, this means that general relativity cannot be treated under the same standard of the other interactions, which are in some sense renormalizable interaction. And furthermore, we have the big issue related with the fact that the theoretical and the experimental value of lambda is very different, and then the vacuum state of gravity is very difficult to be addressed. And furthermore, we have the problem of singularities for classical spacetime. So the final statement is that at the moment, at least as far as I know, there is no theory which is capable to address all these problems under the same standard. And then there are a plethora of theories which are extended theory of gravity, alternative theory of gravity. There are several issues related with the detection of dark energy and dark matter. And then we have several approaches in order to deal with this plethora of problems. So in particular, I would like just to point out the fact that at fundamental level, there are no final evidence for dark energy and dark matter, in a sense that they have no material counterpart, because at the moment, it seems that the three families of particle standard model and the fact that the Higgs boson is giving the mass dressing for all particles is a very strong result. And in some sense, dark energy and dark matter are a big puzzle due to the fact that they exist. And we have that at a large scale, at infrared scale, we have to deal with the fact that observations cannot be simply related with general relativity if you do not take into account some dark objects which are capable of addressing the phenomenology. So the issue is, the dark side issue could be in some sense solved taking into account non-locality. So non-locality, the fact that we have to introduce non-local terms into the standard action of general relativity, could be a way in order to address some of the problems that we mentioned before. And then, for example, all of us knows that there are several proposals. In particular, there are scalar tensor theories, there are higher order theories, there is the successful Starobinsky model that all of us knows very well, that is working extremely in a very good way to address the Planck data. There is the proposal by Kellogg-Stelle and several, and in particular, you can consider higher order scalar tensor theories, and then locally you can extend theories of gravity. I like to deal with the extended theory of gravity because all this theory has general relativity as a particular case. So in some sense, if you consider, for example, curvature-based theories, in some sense, in order to be in agreement with the phenomenology, in some sense, general relativity should be one of the possibility. And as you know, there are several good probe of the fact that the general relativity is working very well at a lot of scales. And then in any case, we have to deal with some post-Einsteinian issue, but the theory, the Einstein theory, should be retained in some way. Okay, let's go now more specifically into the problem of non-locality. What does it mean, extended theory of gravity which are non-local? If you want to give just a classification, you can consider, for example, two main families of non-local extended theory of gravity. In particular, you can take into account infinite derivative theories of gravity, IDG's theories, and the integral kernel theories of gravity. In particular, in this case, what you have to take into account is some non-local operator which is acting on the dynamical counterpart of your theory. And in particular, as I mentioned here, it could be the curvature scalar, the torsion scalar, or the Gauss-Bonnet scalar. So there are several proposals, and also in this case, you can have a very rich phenomenology by which you can take into account several approaches. In particular, what is the infinite derivative theories of gravity? Is a theory in which you have, this is a prototype of this theory, in which you have an operator, and this operator is depending on the distance. And the distance in this case is defined by this object, x minus epsilon. In this case, as soon as you are considering a Fourier transform, and you consider a reparameterization of the theory, you can deal with this kind of theories under the standard of the Fourier transform, and then, as you can see, as you can imagine immediately, you have some characteristic length emerging from this standard. In particular, there are very nice theories that has been widely discussed in literature. In particular, there is this very nice. There is a very nice paper by Bisbas, Gerwig, and Koivisto and Mazumdar, in which they discuss singularity-free and ghost-free theories of gravity, constructing infinite derivative theories of gravity, taking into account all the curvature invariants that you can construct, considering the Ricci scalar, the Ricci tensor, and the Riemann tensor. As you see here, immediately you get some characteristic masses, and then you get some characteristic length as soon as you are defining the coupling for this kind of theories. And it is very, very crucial how you can choose the function defining the non-locality. In particular, it can be a transcendental or an analytic function. It is nice to see that the box operator that you are going to consider here, being strictly related with the mass and with the length, give for free this scale that could be interesting for the purposes that I mentioned before. Okay, so in particular, just to coming more into the details, and I put here some important results in this respect, you can get the so-called super renormalizable and unitary theories. In particular, you can have a non-local extension of the Starobinsky model, and then in some sense, it is quite easy to get solutions which are in good agreement with the data that already has been confronted with the theories. In particular, these super normalizable and unitary theories admit regular black hole solutions, and they have the maximal UV complexion, in particular for this non-local extension of the Starobinsky model, by which you can consider the possibility that some natural scales emerge, for example, at ultraviolet scales. From a very preliminary point of view, the first attempt to include non-local terms into cosmology has been proposed by Deser and Woodard, which for the first time taking into account non-local cosmology. What is their approach? Their approach is simply the fact that they added a non-local term into the standard Hilbert-Einstein action, and they noticed that this non-local term gives rise to a retarded Green function. And this retarded Green function can be recast in terms of standard cosmological parameters, in particular with the scale factor. And according to this, you can recover characteristic length and characteristic scales of energy, which are strictly related with the non-local term. And then they claim, their preliminary claim is that taking into account this approach, which is motivated by quantum field theory and by the fact that non-locality could have a very important role into the dynamics, let us try to see if, for example, issues like dark energy could be addressed according to this. Okay, so now let's come to our proposal, which I'm developing with some of my collaborators. In particular, let us try to see if the former Desert and Woodard approach is working in the various proposals which go under the standard of the so-called, the so-called gravity trinity. The gravity trinity means that you can recast the standard general relativity in various ways, for example, taking into account teleparallel equivalent gravity or taking into account non-metricity. So let us try to see if it is possible to find out a criterion by which you can find out cosmological solutions where the non-local terms, non-local contribution can have can give rise to some nice dynamics. In particular, let us take into account this kernel gravity that I mentioned before. We know the motivation, and the purpose are try to reconstruct cosmography and dark energy. Why cosmography? Cosmography could be very interesting because without searching a priori a given model, by cosmography it is possible to find out some selection criterion based on observation, on which by a sort of inverse scattering procedure you can reconstruct the phenomenology. And then let us try to see if there are some non-local models which can be directly related with cosmography. Furthermore, let us try to see if it is possible, for example, find out some black hole solutions, because due to the very good observation, I have in mind, for example, the Event Horizon Telescope and the other observations which are on the market, by which it is possible to select some data which could be compared with the non-local gravity measurement. So what we are going to propose is a possible method. The possible method is based on the fact that let us try to see if the existence of some Noether symmetry, in particular the existence of some conserved quantity, could be a good criterion in order to select reliable Lagrangians which are connected with non-local gravity. Okay, and this is the procedure that we followed. In particular, let us remind briefly what does it mean, this Noether symmetry approach. We consider, for example, the so-called Noether point symmetries. We have a one parameter group of point transformation, and according to this one parameter group of point transformation, we can take into account an infinitesimal group generator, which is the so-called Noether vector. And then we can take into account also the first prolongation of the infinitesimal generator. In particular, as all of you knows, the Noether theorem states that if and only if exists a function g, t, q, where q are the configuration and t is a free parameter, in particular time, such that this relation hold, then the one parameter group point transformation generated by the x, by the generator, by the vector x, is a one parameter group of Noether point symmetries for the dynamical system described by the Lagrangian. And then associated with this, we have an integral of motion. So our guess is, if you are capable of selecting theories according with this procedure, and if we are capable of selecting integral of motions which have some physical meaning, in this case, this could be nothing more than a proposal to select some reliable non-local theories. However, this is nothing else but a proposal. But, you know, if you are in the dark, let us try to switch on a little light. And in this case, this could be some reliable criterion. So the recipe, what is the recipe? Consider a point like Lagrangian, in particular a cosmological Lagrangian, by which it is possible to find out the Friedmann equations, considering coming from the Euler-Lagrange equation of this Lagrangian. Write an ansatz for the x vector or for its prolongation, and derive the Noether point symmetry, and then let us try to obtain the form of the Noether symmetry in relation with the entries of the theory that we are taking into account. So the system, as we will see in a moment, contains some unknown function. And this unknown function can be nothing else but our functions which are related with our non-local gravity. And then related with the existence of a symmetry, in other words, it is possible to see if the symmetries are capable of selecting a physically motivated Lagrangian. And as we will see in a moment, this is true because some interesting Lagrangians come out according with this approach. So let us start with the curvature-based theory. In particular, let us consider a generic function of R and a generic function of the box -1 R operator. And this is the generalization, the standard generalization of F over gravity. As you know, F over gravity is a theory, for example, giving rise to very interesting models. In particular, let us try to see if it is possible to discuss the non-local counterpart of F over gravity under this standard. Then, what is the procedure? The procedure is that let us take into account a cosmological Lagrangian. We can formally localize the Lagrangian as soon as you are defining this auxiliary field, which is this box phi. And then, as you can see, you can reduce formally your theory to a scalar tensor theory, nothing more. But you have to take care of the fact that you have this Lagrangian constraint, which is inside the theory and which gives rise to the fact that according to this, you have to define your operator. However, you have the standard constraints, which are the definition of the Ricci scalar. In this toy model, we are using a flat Friedmann-Robertson-Walker theory, but it is easily extensible to any Friedmann-Robertson-Walker theory. And then at the end of the day, if you work out this formal localization, you can get this kind of Lagrangian. So take care of the fact that this kind of Lagrangian is a point-like Lagrangian by which you have to take care of the Friedmann equation that can come out. In particular, in this case, you are considering a sort of mini superspace approach in which you have A, R, phi, and epsilon. Epsilon is nothing else but a Lagrange multiplier, which can be dealt under the standard of a new scalar field, by which you can recover your former Lagrangian at the beginning of this kind of this calculation. So let's go on with some details. If you are interested, I can give you some references. And immediately what you can generate a nether vector, and you can generate the Lagrangian related with this. And after all this, after some algebra, you get the form of the symmetry generators, which is related with the existence of some symmetry. The interesting point is that at the end of this procedure, you get two arbitrary functions. And as we will see in a moment, these two arbitrary functions are interesting from the physical point of view, because as we will see, this can be reduced to the, for example, to the non-local Starobinsky model, while this can be reduced to the super renormalizability. It is important to point out, for example, in the case of the super renormalizability case, that while Modesto, Mazumdar, and the other authors put this kind of terms, the super renormalization terms by hand, in this case, it is strictly related with the existence of a nether symmetry. So in this case, it can be considered a sort of criterion. Then you can consider the selection of the model. In the first case, what you get, as you see, it is the first function, as soon as the n is equal to 1, is equal to 2, gives rise immediately to the non-local extension of the Starobinsky model. So it is very important to state this point, because the non-local extension of the Starobinsky models comes directly from the request of the nether symmetry. So the Starobinsky model, this is true also for the local Starobinsky model. So the Starobinsky model is related with the existence of some Noether symmetry. So is the Noether symmetry which in some sense states that it is not just a phenomenological model in which you had R squared or R squared log and so on, but it comes from the existence of some Noether symmetry. You can work out the model, you can consider the Euler-Lagrange equation derived from the Lagrangian that we proposed before. You can get solutions, and these are some particular cases of solution. These are exact solution, some particular exact solution, but there are several of these solutions that can be worked out. And as soon as you remember that your auxiliary field is defined in this way, you can see that the non-local theory, the non-local term can be strictly related with the definition of the Noether symmetry. It is interesting that, for example, standard accelerated expansion are immediately related according to this kind of procedure. In the first case, immediately you can recover also, for example, the case discussed by Deser and Woodard, because according to the value of this n that you can consider into your dynamics, you can get, for example, the fact that you get a general relativity minimally coupled with a scalar field, but we know that the scalar field has a non-local meaning. In particular, we get in this case also, for example, solutions which are radiation solutions and so on. In the second case, also in the second case, we have some interesting situation, because after all the proceeding, the procedure, please remember the fact that this is a sort of super renormalizable theory according to the previous reference that I mentioned before. And in this case, you get a class of models which can be given by the fact that your n give rise to a huge amount of possibility. And as you can see here, also in this case, you get a de Sitter behavior. So what I want to point out is the fact that dark energy can be easily related with this approach, because all these kind of theories give rise to accelerated expansions. Okay, so we can extend the approach to some more sophisticated cases related with the extended gravity, and in particular you can take into account the so-called Gauss-Bonnet gravity. Gauss-Bonnet gravity is very interesting from several points of view, because the Gauss-Bonnet term is a topological surface term. It reduces dynamics. You can get ghost-free theories according to the Gauss-Bonnet proposal. And in particular, it is interesting to see that from a cosmological point of view, you can derive the fact that, but just in cosmology, we have to develop this also in other more physical cases, you can see that the square root of G, which is not zero into the dynamics, because there is the square root, while if you take G linear into the action, it is trivial and it goes to zero. You can recover, in some sense, the dynamics related with the standard general relativity. In particular, you can recover, in some way, the Hilbert-Einstein action. Then you can work out this, and it is interesting to see that the form of this Hg can be strictly related with this statement that I gave. And also in this case, you can apply the same procedure. You can produce a formal localization of your theory, and then the formal localization gives rise to an auxiliary field. Also in this case, the auxiliary field can be related with the Lagrange multiplier. This is the Lagrange multiplier for the case of Gauss-Bonnet terms in cosmology. There are several literature on this. And then you can get the standard point-like Lagrangian, and you can reduce this kind of Lagrangian, giving rise to our mini superspace approach. Also, in this case, you have to take care of some auxiliary scalar field, which are related with the Lagrange multiplier. Okay, so also in this case, the same procedure, you search for, the recipe is always the same. You search for the nether generator. You get, according to this nether generator, the form of the Lagrangian, which is related with the existence of nether symmetry. And then you can find out several interesting cases. In particular, in this case, we found out these three proposals in which also in this case, you get a sort of Lagrangian in which you have further terms with respect to the standard GR. Please consider the fact that inserting this term into the standard Hilbert-Einstein action he has no contribution. So in this case, you need just this and this contribution. Then this n should be different from 1. And the same you can get, as before, this kind of proposal in which you have the super renormalizable theory. Then, also in this case, you have cosmological solutions. And cosmological solutions are related with the fact that you get, as you can see here, solutions which are standard Friedmann solution, like in this case, or de Sitter-like solution, like in this case. However, this gives rise to the form of the various fields, in particular the Gauss-Bonnet field, the non-local field related to the Gauss-Bonnet, and the Lagrange multiplier, which is entering into the action. It is interesting to see that also in this case, because this n is not an integer, this n is a real number. Also in this case, you can get that general relativity is in agreement with the existence of nether symmetry due to the fact that square G is a particular case of the approach. Then you can work out a cosmological solution. You can work out cosmological solution. You can have the standard counterpart of the Woodard and Deser terms, but in this case, the further terms is topological, because it's related with G. And also in this case, as you see, you get the various sections. It is interesting to see that nether symmetries seems to select the sort of power expansion of theories and theories where you have exponential terms. So it seems that there should be some relation between the terms which are good for renormalizations and the existence of these nether symmetries. And then you can work out theories considering the existence of these conserved quantities. In particular, what happens if you had by hand the Ricci scalar to this kind of theory? If you had by hand the Ricci scalar, also in this case, after a localization procedure, you can get Lagrangians of physical interest. Then it seems that at the end of this procedure, it seems that corrections related with the standard Hilbert-Einstein actions could be, in any case, related with the existence of some symmetry. And also in this case, there is just a table of possibilities. Also in this case, you can have various proposals related with the non-locality from one side and with the power of the Gauss-Bonnet terms and so on. So also in this case, the field phi is related with the non-locality. So in summary, what I'm saying is that the kind of non-locality can be in any case related with a sort of auxiliary field, and this auxiliary field has a geometrical interpretation as soon as you can interpret the non-locality. The final case is this one. The final case is a theory based on the fact, is an affine theory based on the fact that you can take into account torsion instead of curvature. According to the first proposal by the Einstein itself, that in 1925 proposed the fact that you can consider, instead of Levi-Civita connection, you can consider the Weissenbach connection, and the Weissenbach connection is connected with the tetrads. And in this case, you can work out this kind of theories, and this kind of theory is based essentially on three scalars. The three scalars are the torsion scalar that can give rise to the curvature scalar as soon as you are considering a boundary term B. So, in some sense, if you define this T in the Weissenbach connection, this R in the Levi-Civita connection, and you define a suitable term B, which comes out from the boundary term of the curvature of the torsion, you can connect the standard Levi-Civita approach with the Weissenbach approach, and then you can recast GR as a teleparallel theory. The localization procedure is exactly the same. You get as a standard the new scalar field. It is quite boring, but it is just a question of algebra, of mathematics. You get the Klein-Gordon equation related with these auxiliary fields that, I repeat, are just are nothing else but Lagrange multipliers for the theory. As you can see here, you have a Lagrange multiplier for the field T and another one for the field B. And then you can proceed exactly in the same way. You can give rise to the cosmological Lagrangian, and according to this cosmological Lagrangian, you have to define a suitable mini superspace. You have to consider the generator of the symmetries, and the generator of the symmetries give rise to the Noether symmetry that could be used for this kind of approach. Also, in this case, the existence of the generator provides a system of partial differential equation which specify the form of the cosmological Lagrangian. Also, in this case, you have solutions. Solutions are the various form of the gravitational Lagrangian, which are selected by the existence of the Noether symmetry. So the recipe is that you give me a Noether symmetry, and after all the procedure, I give you a particular class of theories which are related with that Noether symmetry. But the important point is that this kind of solutions are, in some sense, with the physical have a physical meaning due to the fact that Noether symmetries select physical theories. I would like just to stress this point because it is not just a tautology, but I would like just to point out the importance of symmetries, because symmetries seems really a selection criterion in order to find out physical theories. It's not just an aesthetic approach, but it could be, in some sense, also an operational approach which give you some physical content. Also, in this case, you can get cosmological solutions which are related with the various generators. As you can see here, in some sense, you can get solutions which are the standard solution of cosmology, which are power law solution, which are de Sitter-like solution, and so on. It is interesting to see that the parameter of this solution strictly are related with the symmetry. So this could be another important selection criterion, because why? Imagine that you are going to construct a cosmography. In the cosmography, it is fundamental how you select the derivatives of the scale factor. But in this case, the derivative of the scale factor and the scale factor himself are strictly related with the existence of the symmetry. In some sense, the cosmography could be related with this Noether symmetry approach in relation with this procedure. Okay, so after all these excursus, which is I'm going to conclude, we can try to search for this kind of approach also at astrophysical level. In particular, is it possible to see if spherically symmetric solution and some astrophysical considerations can be developed for these non-local terms. So the objective, we can select the form of this non-local action containing symmetries. we can perform a post-Newtonian limit for this. We can constrain the free parameters. In particular, there are several interesting astrophysical methods by which this kind of parameter and then this kind of length related with this with this non-locality could be selected, and then we can try to see if it is possible to find out some interesting result. In particular, we considered the Desert and Woodard action. We considered this action this time for spherical symmetry, and we take into account this kind of matrix, this class of matrix. We produce a point like Lagrangian, but please take care of the fact that this kind of Lagrangian is a point like Lagrangian, but for spherical symmetry. Is like when you are producing the Schwarzschild solution, considering the Lagrangians giving rise to the Christoffel symbols in some sense. And the nether symmetry select the form of this kind of Lagrangian. If we if we restrict the interval to this subspace, and you consider higher order corrections in your post-Newtonian derivation, these are the details that you can find out in the paper, immediately you see that in order to take care of these higher order terms, you need to take care to correction up to the sixth order. So you have to take care of this kind of potentials coming into your dynamics related in relation with the fields that you are taking into account. And then, this is the procedure, you can consider the corrections coming from this kind of approach. And then the order of potentials could be really relevant in order to select this kind of terms. So apart the mathematics of the details of mathematics that, as you can see, is quite cumbersome, the interesting point is that you can map the Keplerian orbit according to some interesting cases. In particular, we take into account the S2 stars around the galactic center, and we selected the possibility that it is possible to constrain possible characteristic length which are strictly related with the existence of this scalar field related with the non-locality. In particular, as you can see here, the two scalar fields can be related with these two kinds of length, one for the field phi and the other one for the field epsilon. It is interesting to see that according to the precision that the telescopes are now on the market, for example, I have in mind the Event Horizon Telescope or some related collaborations, ALMA and so on, very likely this kind of selection are at hand because they are of the order of some astronomic unit. So coming to the conclusion is that according to these non-localities, it's possible to produce ultraviolet and infrared cosmic evolution. From the nether symmetry, it is just a mathematical approach, but is it possible to select physically relevant models? And in particular, it is possible to derive exact cosmological solution. So this is from the point of view of dark energy. From the point of view of dark matter, is it possible to speculate according to the fact that this kind of non-local corrections could give rise to some interesting feature. For example, recently we published with my collaborator a paper on classical and quantum gravity in which we demonstrate that non-local gravity can give rise to further modes in gravitational waves from one side. And in particular, the experimental perspective is that some selections of the length, of given length, could be derived from the observation. That's all. Thank you for your attention.
Thank you very, very much, Salvatore, for a very interesting and comprehensive talk. that's our last talk for the session. We are slightly over time, but possibly we could take a question. Is there any question?
Okay, I see a couple of questions.
From
on the chat.
Yes, please.
There is one by Nicodem, which says that what about the Einstein-Cartan theory? This is the most natural modification and of the oldest of generativity. I completely agree that with the Nicodem, very likely the Einstein-Cartan is in the same research topic. Probably the Einstein-Cartan theory gives rise to further characteristic length, and they could be probed, in my opinion, with data. Yes, probably this is one of the very precursor of this kind of approach. And there is another one by Arun, and it seems that, yes, the dark energy problem, in my opinion, could be solved taking into account this non-local gravity, because non-local gravity, as you see, give rise to accelerated expansion for free, and this kind of accelerated expansion can be related with some field. But it is interesting to see that non-locality give rise to this kind of field, and we know what is the origin, the geometric origin of this kind of field. I think that the dark energy problem could be related with this approach. I hope to have answered the questions.
Okay, thank you very much for that. We're well past time. We thank you, Salvatore, for a very interesting talk, and all the speakers in this session. If your delegates have specific questions, please direct it by email or chat to the speakers concerned. And in about 10 minutes' time, there will be the next session for the mini talks. Sudan, is there anything you want to say?
Thank you very much.
No, all the information has been given by the chat.
Okay. All right. Okay, fine. We'll meet again shortly. Thank you. Bye.
South Africa has all of the features that travelers long for in a vacation destination. Fine weather, gorgeous scenery, great beaches, modern accommodations, and superb cuisine. The southern tip of Africa also offers an exotic array of once-in-a-lifetime adventures, from off-roading on a safari to diving with great white sharks. It's hard to name another holiday destination that offers as much variety. Here's a look at the best places to visit in South Africa. Number 10, Blyde River Canyon. Blyde River Canyon is the second largest canyon in Africa, after the Fish River Canyon, although it is much greener due to its lush subtropical foliage. Walking treks through the rich diversity of flora and fauna-filled canyon offer views of magnificent escarpments, waterfalls, and ancient geological phenomenon. Visitors have the opportunity to encounter all 5 of South Africa's primates here, as well as hippos and crocodiles near the wetlands of Swandini Dam. Number 9. Cape Winelands. The fertile valleys of the Cape Winelands are surrounded by majestic mountains, sleepy villages, fruitful orchards, and some of the lushest scenery in South Africa. Visitors can follow the wine routes of the Cape to visit the vineyards of the country's finest winemakers, whose sherries, ports, brandies, and intriguing whites and reds are world famous for their delicate flavors and savorable palatability. Number 8. Addo Elephant National Park. Located in the Eastern Cape region of South Africa, the Addo Elephant National Park is one of the country's largest parks. The park is famous for its elephant population that has a special brownish skin color due to the red soil. Amongst the elephants, other animals like ostriches, antelopes, and warthogs can be seen. As part of the park's expansion, a group of lions and a group of spotted hyenas have been introduced to the park as of 2004. Number 7. Hermanus. Located on the southern coast of Africa near the Garden Route, Hermanus is famous for its shore-based whale watching. The sheltered, shallow waters attract southern right whales that migrate to the region each year to mate and breed. A 6-mile-long cliffside walk with built-in telescopes and benches offers visitors plenty of opportunities to view these social animals as they raise their flukes in the sea breezes. Whale watching boat tours are available as well. Number 6. Durban. South Africa's second largest city, Durban, is located on the eastern coast. Durban's subtropical climate, scenic beaches, and close proximity to Johannesburg have made the coastal city a popular vacation destination for South Africans. The English colonial architecture that once dominated the city has been enlivened by a mix of Zulu murals, Islamic mosques, Hindu temples, and Christian churches. Number 5. Hluhluwe Umfolozi Game Reserve. As the only park under a formal conservation effort in KwaZulu-Natal, where you can see the Big Five: lions, elephants, leopards, buffalo, and rhinoceros, the Hluhluwe Umfolozi Game Reserve offers visitors wildlife viewing opportunities second to none. Wildlife enthusiasts may enjoy the vast expanses of native plants and native animals during guided walks, self-guided drives, or opt for a thrilling viewing experience by boat along the Hluhluwe Dam.
Hi, Matt. Praveen Kumar is here. Warren is Pankaj. Is here. Hamza.
Hi, Sudan. Okay. I suggest our first speaker, which is Praveen, tries to share his screen now.
Praveen Kumar, are you with us?
Yes, sir.
Please try to share your screen. Okay.
Okay, great. Okay.
It is visible?
Yes. It's fine.
So we're just missing one speaker, I think, at the moment. Is that right?
Yeah.
Yeah. Okay.
If
All right.
she doesn't show, it's fine.
Okay. Okay. So welcome everyone to this room one of the parallel sessions. So we're going to get started right now with our first speaker, which is Praveen Dankar, who's going to be telling us about entropy-corrected interacting holographic dark energy model with extended Chaplygin gas in higher dimension. Okay, so take it away.
Thank you. Good evening to one and all to be present here. I am Praveen Kumar Dhankar, associated with the Department of Mathematics, Rashtriya Sant Tukadoji Maharaj, Nagpur University. Jointly work with this Dr. N.A. Ramtekar and Dr. G.S. Khadekar with the topic of entropy-corrected interacting holographic dark energy model with extended Kaplan gas in high dimension. So abstract for this, in this work, we have discussed the progression of logarithmic corrected interacting holographic dark energy in high dimension. We calculate the equation of a state parameter with scale factor defined by power law and found it transient universe from quantized to Fenton era. Further, we define correspondence between entropy corrected holographic dark energy and extended Kaplan gas to reconstruct the potential and dynamics of the scalar field in the presence of entropy corrected holographic dark energy. So we consider Kaluza-Klein type FRW metric of the form which is written in equation 1, where A of t is a cosmic scale factor. Energy momentum tensor for perfect fluid given in equation 2, where rho is energy density and p its pressure. Energy Einstein field equation, which is written in equation 3, where rho mu is the Ricci tensor. For the line element 1, Einstein field equation 3 for the flat universe, which can be written in the form of equation 4 and 5, where h is the Hubble constant and dot denote time derivative. Rho is the sum of the densities of entropy corrected holographic dark energy and dark matter, where P is the pressure corresponding to ECH-dE. Energy conservation equation, which can be written in form of equation 6. So we rewrite equation 4 in form of equation 7. So in case of interacting dark energy model, the corresponding non-conservation equation for dark matter and dark energy, which can be written in equation 8 and 9, where Q is some interacting term. So here we have taken this interacting term as defined by Pablon and Jimdal 2015, which is the form of Q equal to 4b square h rho lambda and rho m. the interacting, the entropy corrected holographic dark energy for Kaluza-Klein universe is defined by Ray et al. 2015, which can be written in form of equation 10, where m is constant and mu and lambda are dimensionless constant of order of unity. For k equal to 0, that is for flat universe, L is expressed in terms of future event horizon of the universe, which is written in equation 11, where A of t is some scale factor of the universe and R of t is relevant to the future event horizon of the universe. So the derivative of L with respect to time takes the form in terms of equation 12, where we inserting equation 10 in equation 7. So we find the equation 13. Using equation 13 in equation 12, we get L dot in form of equation 14. On taking time derivative of equation 10, we get equation 15. So by putting the value of rho dot lambda and q in equation 10, we get omega lambda in form of equation 16. So for in IR cutoff, we consider L equal to H inverse. So equation 16 can be reduced in form of equation 17. So here we choose a scale factor of the form, which is earlier taken by Kumar and Joy et al. 2018, that is A of t equal to A naught t upon t naught alpha, where t naught is the present value of the scale factor and A naught is the present value of the scale factor and t naught is the present age of the universe, and alpha is the dimensionless positive parameter. The distillation parameter can be reduced in form of equation 19. From the above equation, it is clear that alpha greater than 1 result into q less than 0 and alpha less than 1 gives q greater than 0, which describe accelerating and decelerating phase of the universe. So by using equation 19 in equation 18, we get A of t in form of equation 20. So we consider Hubble parameter as written in equation 21. So by using A equal to A naught 1 plus Z inverse and H naught equal to 1 upon T naught 1 plus Q, we get Hubble parameter in terms of redshift, which is written in equation 22. Thus, where IR cutoff value of L in terms of redshift, which can be written in equation 23. So by using equation 23 into 10, we get entropy corrected holographic dark energy in terms of redshift, which can be written in equation 24. So by using equation 10 and 23 in equation 16, we get equation in terms of 25. So the equation 25 represents equation of parameter, which is earlier obtained, which is same as obtained by Sarif and Javed. So the behavior of equation of parameter omega lambda versus at redshift Z and the scale factor, which is plotted in equation, which is plotted in figure 1 and 2. So for the figure 1, it is found that omega lambda transient universe from quantum size omega lambda greater than -1 to phantom omega lambda, which is less than -1 era, quantum size era to phantom era. And equation figure 2 is the equation of parameter, equation of state parameter transient from phantom era to quantum size era. And further, it is observed that the current value of omega lambda in terms of A for different values of B square, where omega lambda equal to 0.5, it represents consensus error for B square equal to 0.3 and 0.4, and phantom error for B square equal to 0.5. So energy density and pressure in terms of time dependent and homogeneous scale factor phi having self-interacting potential V of phi is given in equation 26 and 27. So here we consider for two cases. So now for n equal to 1, if we assume A1 equal to A, then extended Kaplan gas equation of state reduced to modified Kaplan gas equation of state of the form which is written in equation 28. So by using equation 28 density evolution for extended Kaplan gas can be written in equation 29, where C is the constant of integration. So next we define correspondence between entropy corrected holographic dark energy and extended Kaplan gas model, and reconstruct the potential and dynamics of the scale factor in presence of entropy corrected holographic dark energy by equating energy density from equation 24 and 30, 29 should be 29. We get the C in terms of equation 30. So further we have omega, which is written in equation 31. So by replacing rho by rho lambda in equation 32, we get 31. So and equating equation 24, we get B, a value of V, which is written in equation 32. So by substituting values of values from equation 24 and 25 in 32, we get the value of B in terms of equation 33. So for n equal to 1, we obtain scale potential and kinetic energy in terms of equation 20, in terms of equation 27, 28, as can be written as equation 34 and 35. So by using equation 30 in 35 and 36, we obtain values of phi dot square and V of phi scale potential in terms of equation 36 and 37. So by putting the value of B, C and B, we obtain phi dot square in terms of equation 38 and V of phi scale potential in terms of equation 39. So then we integrate it and obtain the value of phi. Here, figure 3, it is the behavior of scale potential versus redshift, and figure 4, which is the behavior of scale potential versus redshift, right? So respectively, where figure 3 indicate increasing with increasing of b square, while figure 4 it described that decreasing with increasing interacting parameter. So when we consider case 2, n equal to 2 and zeta equal to 1 by 2, so equation extended Kaplan gas equation of state can be written in equation 41. So by using equation 41, energy density for this case can be written in equation 42, where C1 is the constant of integration and omega is the root of the following equation, which is written in form of equation 43. So on equating energy density and densities from equation 24 and 43, we get the value of C1, which is written in form of equation 44. So further we obtain the value of omega in terms of 45 by replacing omega by omega lambda in equation 46 and equating with equation 24, we get the value of B in terms of equation 46. By substituting the values from equation 24, 25 in equation 46, we get the value of B in terms of equation 47. So for N, one can obtain scale potential and kinetic energy in terms of equation 20 in form of equation 27 and 28, as can be written in terms of equation 48 and 49. So by using equation 43 in 49 and 50, we get phi dot square in terms of 50 and V of 5 in terms of equation 51. So on putting the value of C1 and B in the above, we get the equation which is the value of phi dot square in terms of equation 52. So on integrating it, we get the value of kinetic energy in terms of equation 53. So the expression obtained for scale potential and kinetic energy terms for this case are same as equation 40 and 41 obtained for n equal to 1 in previous case. For the values of scalar field and scale potential, it is clear that our model represent quantized dark energy model for n equal to 1 and n equal to 2, which is satisfied with the Sarif and Javed 2013. So for the conclusion, to obtain expression for the equation of state parameter, we consider power law of scale factor, which is consistent with the present observational data. The behavior of equation of state parameter shows omega lambda transient universe from quantum size omega lambda greater than -1 to phantom era omega lambda less than -1. From the graph, it is clear that equation of state parameter transient from phantom era to quantum size era for B square equal to -0.5 at z equal to 0.4 and remains in quantum size era for B square equal to 0.3 and 0.4. Further, we have discussed correspondence between interacting entropy corrected holographic dark energy and extended Kaplan gas, and reconstructed the potential of the scale factor and found that it is they are same for n equal to 1 and n equal to 2. So for the values of scale field and scale potential, it is clear that dark energy model under consideration represent quantized dark energy model. These are the references. Thank you.
Okay, thanks for that nice talk there. We've got time for a quick question. If anyone has any, you can raise your hands on the Zoom thing. Or you can write in the chat, I suppose. Okay, I'm not seeing any questions at the moment. Okay. So if anyone has any, oh, hang on, has anything appeared? Okay, Vijay Singh has a question. So we can go to that.
Yes, sir.
Okay.
Hello. Can you hear me?
Yes, sir. Yes, sir.
Praveen, I think you have taken a wrong sign in the Einstein field equation, or there is some correction in your slide. it is maybe a mistake on your paper or just a typos?
Yeah, actually, sir, it is a typo error for the equations. Like it is some typo error.
Can you show me the slide of that where Einstein field equation is mentioned there?
Einstein field equation, yes, sir. This one equation,
Einstein field equation, the previous one. Yeah, equation number 3. Because you have taken the signature minus plus plus plus. So I think in equation 3, right hand side should be negative.
Okay, let me check.
Yeah, please check it.
Yes.
Okay, thank you.
Okay, so I think we should move on now.
Thank you.
Praveen, if you could stop sharing your screen now.
So I stop. I think I stop my sharing.
Yeah. So our next speaker should be Warren, according to the program.
Yeah. Okay. Let me share.
Yes, I stopped, right?
Okay. Warren, if you can share your screen, please. Okay, great. So.
Okay, is it visible?
Yeah, that's visible. It's not. Okay, that's fine, I think. Okay, so our next speaker is Warren Naidu, who's going to be telling us about constraining dark energy and relativity structure with high cosmic micro background survey. Take it away, Warren.
Okay. Yeah. Hi, my name is Warren Naidu. I'm a PhD student at UKZN, and this work is being done as part of my PhD under the supervision of Professor Kavalin Mudli. So today I'll be talking a little bit about constraining dark energy and the growth of large-scale structure using the HYREX experiment, which is led by UKZN, and in combination with CMB surveys. So we know from observations that about 95% of the universe or the energy distribution is in the form of some mysterious exotic matter. So 70% of that is dark energy and about 30% is dark matter. So we know that dark energy is driving this accelerated expansion of the universe, but we don't know what's causing it or what models can constrain that. Large-scale structure surveys can provide a wealth of information on the cosmological paradigm. And we so H1 surveys is a promising new tool that will help us in the quest to unravel these mysteries, because H1 surveys can map larger volumes of the universe much quicker than conventional galaxy surveys. So in this talk, we'll just investigate the potential of HYREX to do H1 surveys and constrain cosmological parameters. Okay, so the CMB has already provided a wealth of information on the cosmological models. So as we can see, the CMB map shown in the figure on top, we see in the early universe, there's thermal fluctuations, so hot and cold spots. This shows that there is a density fluctuation in the early universe, which becomes the large-scale structure we see later on. So from the data set, we can get the statistics, and the statistics can help us constrain models. Okay, so what we use to constrain, for example, in the CMB maps is the 2-point function. So basically the 2-point function says if there is an overdensity at some region R, what is the probability that there is another overdensity at some point R prime? And if we do that, so in the Fourier space, we get the Fourier transform of the correlation function. We have the power spectrum. And we see in the lower half of the slide, the CMB power spectrum. So we can see that the blue curve is the theory, and that the Planck 2018 results match really closely with theory. And that's fascinating because slight deviations will give us different parameter constraints. For example, if we observe some deviation in the damping scale or in the amplitude of the fluctuations or the peaks at the location of the peaks, those correspond to different cosmological parameters. So the oscillation peaks are quite interesting. They are from the baryonic acoustic oscillations. So in the Fourier transform, they oscillate, but in the real space correlation function, they just is this preferred clustering scale. And where does that come from? So in the early universe, we have this overdensity, right? So if we have a fluid with not much space between the particles because the early universe was compact, so the photons just bounce off the electrons and protons. And so the fluid is coupled. And so we have the photon pressure that wants to go outward and the gravitational pressure pulling in the baryons. But over time, we also have a background expansion and the cosmic expansion. So over time, the spaces between the particles grow. And over time, we have the photons leaving this fluid, and that's how we get the CMB. So at this point, we say that the overdensities are frozen in because now we only have the gravitational potential. And this characteristic scale can be is known because it's determined by the sound speed of the fluid. So we can see in the graphical representation of this BAO rings that there is now this preferred clustering scale in the correlation function that corresponds to about 150 megaparsecs. So that can be used as a standard ruler. So much like the surveys of supernova were a standard candle, now we have a standard ruler which provides this constant scale in the universe to measure expansion. So galaxy surveys have also provided a lot of information on the large scale structure. So we can see from the SDSS galaxy survey, we have this clustering of the galaxies that traces the cosmic web. And we can get the statistics and we can see the correlation function. So we have that bump at about 100 H inverse megaparsecs, which is the baryonic acoustic oscillation. Okay, so here I just show how you can get better constraints by combining data sets. So we can see on the leftmost plot, so if we have the parameters of density for dark energy and matter, by combining the clustering measurements with supernova and CMB measurements, we get the combined data set, which is right in the middle, which is constrained much better than the individual parameters, or individual surveys rather. And we can see in some of the newer results from the DES and Galaxy surveys, so now they're showing constraints on sigma 8, which is the amplitude of fluctuation, and the matter density. So an interesting point here in the new plots is this tension between Planck and the newer plots. So is that a tension because Planck prefers different values seemingly? So that's where adding more data sets helps. So like H1, would it provide a new theory to the later universe compared to the early universe, or is it just a systematic in the lensing measurement seen here? We can also constrain dark energy models specifically. So F is the growth function. It's related to the omega M. So we can see on the left here, so a few models of this no slip gravity. So if we can constrain F well enough with short enough uncertainties, then we can really say which models do not fit the data set and which models the data set prefers. And on the right, we see a few F of R gravity models, and in blue is a brain world model compared to the lambda CDM model. Okay, so H1 intensity mapping is using the 21 centimeter line emission, which we get from the spin flip transition, to map the neutral hydrogen distribution of the universe. And we believe that traces the large scale structure. So we can then get the large scale structure and get like a CMB map, but now using neutral hydrogen. And then once we do this, we can, since this is a spectral line, we also have the redshift for free. And so that we get a 3D map of the universe. But one of the major challenges facing 21 centimeter intensity mapping experiments is that the foregrounds are quite bright. So we can see on this plot, on the rightmost plot here, the red lines show different combinations, different contributions from the foreground, which is much brighter than the blue, which is the cosmological signal. But the foregrounds are thought to be slowly varying in frequency direction, so they can be removed from the oscillating cosmological signal. Okay, so the Hyrax experiment, which is what we consider here, will be a 1024 dish 6 meter interferometer array operating in the 400 to 800 frequency megahertz band. So Prof. Kavlan-Moodley's talk on Wednesday would be a more in-depth coverage of the HYREX experiment. So here I'm just showing the proposed dish layout, and here we have a HYREX critter that lives in the Kruger site. So HYREX will measure the neutral hydrogen at the time of the universe when the expansion starts to dominate, so we can get dynamical dark energy constraints. Okay, so how do we model the H1 signal? So we say the H1 is a bias trace of the matter distribution. So we can just write that as some brightness temperature of the H1 times the bias times the matter density. But we also add in the correction for the RSD term, the redshift space distortion, because we measure in redshift space, and that induces some non-linearities into the signal. We can then compute the 2-point function for the 21 centimeter line. So here L and Y is just is equal to the K space by division of a volume factor, and K is the Fourier transform of the real space. But these 21 centimeter interferometer measurements will also have some associated noise, and that's given by a root mean squared. So it's dependent on the system temperature, the field of view, the total integration time, and the baseline density function. Okay, so what about cross-correlation science? So cross-correlation surveys can help improve the individual survey measurements because they can minimize uncorrelated systematics. So in fact, the first detection of H1 was made in cross-correlation of the Green Bank telescope and the Deep 2 optical survey, as can see in the Chang et al. 2010 paper. And HYREX will have good redshift overlap with next generation surveys such as photometric galaxy surveys like DES and LSST. So Dr. Momita Aich is leading up some work on LSST cross-correlation with HYREX. Spectroscopic galaxy surveys like DESI, Euclid, W1st, or Roman. And I've done some initial calculations on the W1st HYREX cross-correlations. And CMB surveys such as ACT, the South Pole Telescope, or Simons Observatory. So here we consider ACT CMB lensing cross-correlations. So CMB lensing traces the large-scale structure as well, because the CMB photons pass through the large-scale structure and is deflected by lensing till it reaches us. And we can model that in real space by saying some convergence of the lensing or some measurement of the lensing is just the integrated matter density with some weighting kernel, which depends on the cosmology. And we cross-correlate this field with the 21 centimeter field to get a cross-correlation signal. But we find that the cross-correlation signal vanishes after foreground removal. So the foreground is smoothly varying in frequency direction. So in K space, it's confined to low K spaces. So if we consider the cross-correlation signal as a function of K, which is a Fourier variable of the frequency, we can see it decreases as you remove K. And that is because in the kernel for the lensing in K space is mostly supported at low K parallel. And we can see that better in the signal to noise plot at the bottom. So for all the modes, we have a cross correlation signal to noise of about 10 at L of 500. But if you remove about 0.01 megaparsec inverse, which is the expected removal for HYREX or for foregrounds, then the entire signal is basically gone and becomes undetectable. But we can recover a signal using the bispectrum or the 3-point function. So what we do is we use this density modulation effect. So we take two 21 centimeter modes and we correlate with a background kappa mode. So this density modulation, so if we have a bright background that shows the kappa field that will trace the background, which is bright and overdense. And then if we have this dark shade, it's underdense. And this blue stars represent the 21 centimeter line. So the 21 centimeter is more clustered where the background is overdense and less clustered where the background is underdense. So that's a correlation that we are trying to pick up. And we find in the 3-point function that we get really good signal to noise recovery, especially compared to the 2-point function. So here I'm showing that in the 21 centimeter case, or the H1 case, in a single redshift bin out of 4 in the HYREX range, we have really good signal to noise. And for the bispectrum in 1 redshift bin as well. So we can convert this higher signal to noise into parameter constraints. And to do that, we use the Fisher matrix analysis, which is based on a likelihood function, which basically says that given some underlying model and some expected measurements, how well can you constrain the parameters of that model? And we compute our Fisher matrix with this equation is just equal to some mode volume factor. And then the derivatives of the total signals, so the signal plus the noise, with respect to the parameters summed over the modes. Okay, so here I'm showing the basic parameter constraints for the H1 signal. So here I'm showing the bispectrum, the 21 centimeter signal, and then the combination. So we can see that we get really high constraints below the percent level on most of these H1 parameters. And the most interesting thing is, for example, sigma 8 and F and with BH1. By combining the data sets, we break the degeneracy, because in general, they're not well constrained, but we can see the blue curve, they become really well constrained when you add the information. Okay, we can also get cosmological parameters and dark energy constraints from this by considering the Hubble distance and the angular diameter distance. And when we do that, I show the marginalized constraints on F sigma 8 and the dark energy parameters. Okay, so here we can see with the combined measurement, we can break the degeneracy of F sigma 8. So here we can get really good measurements and really tight measurements on the structure formation. And with adding in kappa as well, we can see the red contour is really small. So that's really good. So we can really differentiate between structure growth and dark energy models. And the dark energy equation of state parameters, so the combined, so the red figure of merit, which is the area of this ellipse, is about 900 plus, which is really good tight constraints on dark energy. In fact, the H1 alone is pretty competitive because the H1 alone is about 400, and that's comparable with SKA phase 1. So this provides an alternative measurement comparable to SKA on just the H1 alone. Okay, so to conclude, next generation experiments will provide much greater information on the nature of the universe. Combining these surveys can place even higher constraints on the cosmological model. We showed how HIRAX can be used in next generation experiments to provide competitive constraints on dark energy and structure growth parameters. So for some future work, we will look at now constraining more specific modified gravity models. We want to work with Prof. Roy Martins and Dr. Louis Pernon is on board and looking at that. We also will look at extending our parameter forecast to constrain neutrino mass and non-Gaussianity parameters, as well as scale-dependent biases. And we'll also look at extending the galaxy surveys to get more parametric constraints out of that. Yeah, so that's the end of my talk, and thank you.
Okay, thanks a lot, Warren. Do we have any questions for Warren? Feel free to raise your hand or type them in the chat window. Okay, we've got a question from Roy.
There we are.
Yeah, okay.
Hi, Warren. Thanks. It was a very nice talk. You've got a very exciting PhD project. I just wanted to ask, what was your maximum K-scale that you used in the bispectrum analysis? How far did you go towards nonlinearity in your choice of K?
Okay, yes, thanks for that question. Yeah, so so the K-scales are set by two parameters. Firstly, the length scale that our interferometry can reach, because that's cut off in K-space as well. But as you mentioned, we're mainly stopping at the nonlinear scale, so about 0.14 megaparsec inverse. So we're not going into the nonlinear scale, yeah, in K. I'm not sure if that answers the question.
Yeah, that's fine. I mean, you're going into the non-linear scale because you're doing second order perturbations, but you're not going non-perturbative. Yeah.
Yeah.
Okay.
Yeah, yeah.
And for the, do you combine the power spectrum with the bispectrum, or you're just using the bispectrum?
We're just using the bispectrum, but we combine them when I showed the parameter constraints. So we add the Fisher matrices.
Oh, okay. All right, thanks.
Okay, we've got time for one more question. Okay, if not, well, thanks again, Warren. You can stop sharing your screen now and we can move on to our next speaker. which is Pankaj Kumar. Pankaj, if you want to try sharing the screen now. And unmuting yourself, of course. Okay, we can see that. Thanks. Okay, so our next speaker is Pankaj Kumar. Okay, who's going to be telling us about inflation with logarithmic scalar field and Brans-Dicke theory. So take it away.
Thank you, sir. Am I audible?
I can hear you, yeah.
Thank you. First of all, I would like to express my sincere thanks to organizers for providing me an opportunity to present my work, and congratulations for organizing a very nice conference. Myself, Dr. Pankaj Kumar, Assistant Professor of Mathematics at Maharaja Garshan University, Himachal Pradesh, India. The topic of my presentation is inflation with logarithmic scalar field in Brans-Dicke theory. Outline of presentation: lessons of Brans-Dicke theory, logarithmic form of Brans-Dicke scalar field, solution of field equations, classical stability of the model, conclusion and references. Equation first represent the action for Brans-Dicke theory in Jordan frame. R represents a scalar G, the determinant of metric tensor G, meaning omega is the dimensionless, and phi the scale factor. We consider a homogeneous and isotropic flat Friedman-Robertson-Walker universe, which is given by line element 2. For the action first and metric 2, we can obtain the field equation given by equation number 3, equation number 4, and equation number 5. Where rho denotes the energy density and P denotes the pressure. Equation 5 is known as the wave equation or conservation equation of Brans-Dicke scalar field 5. One of the widely used form of Brans-Dicke scalar field phi is power law form, which is given by phi equals to phi naught a to the power n, where phi naught and n are positive constants. If we combine equation number 3, 4, and 5 and take this power law form of Brans-Dicke scalar field, then we obtain a constant value of distillation parameter given by equation number 6. So it is evident from the value of distillation parameter that it is a constant value. Therefore, the phase transition of the cosmic evolution cannot be achieved in the power law. This is the main drawback of power law form of Brans-Dicke scalar field. In a paper published in Astrophysics and Space Science 2017, we pointed out the problem, the constant distillation parameter problem, and proposed a logarithmic form of Brans-Dicke scalar field phi, which is given by equation number 7. Where phi naught, alpha, and beta are constants. Alpha always less than, also greater than 1, and beta greater than 0.
Sorry, Pankaj, can you by any chance raise your volume a bit or move you close to your mic or something like that? It's a little bit quiet. It's audible, but it's a little bit tricky.
Okay.
Yeah.
Now I am audible.
It's kind of similar. Can you crank up the volume a little bit if you could, please?
Okay. Now, sir, is okay?
Yeah, I think that's better, yeah.
Okay, thank you. A number of authors have discussed various aspects of cosmological evolution using the newly proposed logarithmic form of Brans-Dicke scalar field. Some of the authors who have worked on the logarithmic form of scalar field are Singh and Kumar, Aditya and Reddy, Sarif and Saab. All the papers on logarithmic form in transitive theory have considered one of available dark energy candidate to study the evolution of the universe. So here, we are not interested to consider dark energy in this study. We are interested to observe the consequences of logarithmic form without considering dark energy component. Distillation parameter, as we saw, this is a constant value for power law form. So this distillation parameter an important parameter to discuss the evolution of the universe. Using equation number 3, 4, 5, as we obtained for power law, we obtained a value of distillation parameter given by equation number 8. And we can observe it is a time dependent value of distillation parameter. Thus, we have obtained a time dependent value of distillation parameter, whereas a constant value was obtained using the power. We observe that at a equals to 0, q equals to 1, which is a positive value, showing decelerated expansion of the universe. Thus, the universe began with decelerated expansion. The terms written here, these three terms, goes to 0 as scale factor goes to infinity. Therefore, as a tends to infinity, q tends to 1. This means in late time evolution, we will observe a decelerated expansion also. Now here we have plotted the deceleration parameter q against the cosmic scale factor a, and we have three parameters alpha, beta, and omega, and we have plotted the graphs for all three parameters, considering the two as constant. Like in this figure, we are varying alpha, and beta and omega have been fixed. We have plotted this graph to observe the effects of the parameter on the deceleration parameter. We can see for the lowest value of alpha 1.1, we having the deceleration inflation or phase transition in the early time of the evolution of the universe. As we decrease the value of alpha, the inflation or phase transition move backward on the timeline. As we increase, as we can say for alpha equals to 1.4, it happens in late time or after the previous values. So alpha, for the small value of alpha, we observe it in very early time. So to explain the inflation in very early time, the small value of alpha is more suitable than the large value of alpha. This is the effect of the parameter alpha on the deceleration parameter, or we can say on the evolution of the universe according to our model. In similar way, in the next figure, we have fixed alpha and omega and varying the parameter beta. And here we observe a reverse effect as we observe in alpha. For higher values of the beta, we observe phase transition. So here we can say the large value of beta is more favorable to observe the inflationary era of the cosmic evolution. In the next figure, we have fixed alpha and beta and varying the value of omega. And here we observe that the large value of parameter omega is more stable to explain the inflationary era. As we decrease the value of omega, the phase transition forward on the timeline. That is scale factor increase as the value of omega decrease, the phase transition move forward. Here we can say the large value of omega is more suitable to explain the inflationary era. And we see in all the figures previously, the value of Q is negative, then it suddenly goes to, in starting the value of positive, then it changes suddenly to negative value, and then suddenly come to the positive value. Because we know inflation happens for a very, very small time. So the model is able to explain the inflationary era of the universe. Next, to analyze the stability of the model, the method of squared sound speed is used, which is given by equation number 9. Where the dot denotes the derivative with respect to cosmic time. The model is stable if Vs square greater than 0 and for Vs less than 0. The model approaches to instability. If our model is stable, the value of Vs square must be 0. We obtain the value of rho and P given by equation number 10 and 11. And differentiating with respect to time, we will get the value of rho dot and P dot, and we will get the value of Vs square. We have not written the values here. We study the classical stability of the model for radiation and matter-dominated universe separately. For radiation-dominated universe, we have plotted two graphs. First, we vary alpha, then we vary beta, and then we vary omega. But here, just we are showing the variation for alpha. To see the, to observe the effect of the parameter in very early time. In first figure, we have plotted for the very small value, very small range of the t to observe the effects in very early time. And we observe as we decrease the value of alpha, the instability of the model move backward on the timeline. As we saw in the deceleration parameter, there also the small value of alpha was favorable to explain the inflationary era. Here also the stability in radiation-dominated universe. For very small value of alpha, the instability move backward on the time. Here also a small value of alpha is suitable for stability of the model. The second figure has been plotted to check the overall behavior. The first figure was required because we can see very early time behavior or effects are not visible in this picture. That's why we plotted the graphs for a small value of t. Here also we observe that the small value of alpha is more suitable for the stability of the model. As we decrease the value of alpha, the instability move forward in the time. That's why we are able to achieve the stability during the radiation-dominated era. We have other parameters also, but we have not shown here. As we will increase the value of omega, we will see that the instability also move forward in late time and in very, very early time, it will move backward in that time. Therefore, a collection of parameters, stable collection of parameters, we may achieve stability of the model during the radiation dominated era. For matter dominated era, because very early time is not suitable for matter dominated era. Matter dominated era happened after the radiation dominated era. So there is no need to plot the graphs for very early time. So that's why we have not plotted. And here we can observe that as we increase the value of omega, the instability of the model move forward on the timeline. It means for sufficiently large value of omega, we can achieve the stability of the model during the matter dominated era. These are the conclusions of the model. We have shown that the logarithmic form of drastic scalar field may resolve the constant dissolution curve of parameter associated with the power law form. The constant dissolution parameter of power law form is a natural consequence in the original drastic theory. So here we are able to resolve the problem using the logarithmic form. We saw that the model is able to show inflation in very early time, but the model is not able to show the late time acceleration. The dark energy, because we are not adding the dark energy in our model here. So we are able to show inflation, but late time acceleration is not able to achieve. The model shows stability for radiation and matter dominated eras of cosmic evolution for suitable values of model parameters. The small values of the parameter alpha and the large value of the parameter omega are rotation and stability of the model. The parameter beta has a mixed type of effect on both inflation and stability. Because in some place beta, if we increase the beta, then it is suitable, and for some place, then we decrease the value of beta, it is suitable. So it has a mixed type of effect on both the inflation and stability of the model. These are some references. Thank you.
Okay. Thanks, Pankaj. We've got time for a question or two, perhaps. So if you can raise your hand or you can write your question in the chat. Okay, we've got a Vijay.
Hello.
Okay, go ahead.
I am audible?
Yeah.
Hello. Yeah. Did you? Yeah. My question is that did you also check the feasibility of the model in terms of basically energy condition, and in particular the weak energy condition?
No, we have not checked the energy conditions here. Our aim was to show that the power law form is not suitable to explain the phase transition of the universe. And using the power logarithmic form, we can explain the phase transition easily. And we check the stability of the model, and we show that the model is stable for suitable values of model parameters. It may be checked in our next work. We may consider this when we work on our next project.
Okay, we have time for one more question, if there is one. Okay, thanks, Pankaj. You can stop sharing your screen now. We can move on to our final talk of this session. Okay, which is Hamza Azri.
Hello, do you hear me?
Yes, we can hear you. You can share your screen now.
Okay, I'm doing so.
Okay.
Can you see it now?
Yeah, I can see that. Thanks.
Well, thank you.
Okay.
So,
our final speaker of this session is Hamza Azri, who's going to be telling us about non-adiabatic perturbations in affine inflation. Okay.
Okay, thank you very much, and thanks especially to those who are still here. It is the last talk, and I promise it will be very short. So it is about non-adiabatic perturbations in inflation in the context of different formulation of gravity. It is called purely affine gravity, and the work is done by or with collaboration with Dr. Saleh, I'll say here. So, excuse me, okay. So, as we know, one of the most important features of inflation is that the scalar field, which drives this inflation, produces the so-called cosmological perturbations, and these perturbations are mostly adiabatic, and every source of non-adiabaticity is suppressed by at superhorizon scales when this scale is of course less than AH, or say when the wavelength is longer than the half scale. And in the case of multiple fields, they can interact, of course, and they can produce a different kind of perturbations. We call them non-adiabatic or entropic perturbations, which can possibly not be suppressed at the superhorizon scales. And the consequence of this feature is that the perturbation, or the gauge invariant perturbation, is becomes dependent on time. It does evolve, and we can track this evolution from the so-called non-adiabatic pressure of the perturbation. So the theory of gravity that we are interested in here is called the affine gravity, or it is actually a different formulation of general relativity. And it is based on the fact that in general relativity, the fundamental field is the metric tensor, which can be considered only as of a secondary importance. We know very well that gravity, or the relativistic theory of gravity, is based on the fact that the gravitational phenomena is an aspect of the curvature of the space-time. Then what we need actually is a space-time connection, and not the metric, at least at the first stage. You can add to this the motivation that the standard model of particle physics or gauge fields in general, they can be described by connections. So in this framework, we will consider this theory of gravity, and we can summarize it like this. So you can always define the covariant derivations in terms of the connection. We will be interested only on the symmetric connection, and locally it vanishes. So it gives you the condition that the space-time is flat locally. And as we said before, the metric at this stage is not necessary. And the curvature of space-time is nothing but a measure of the failure of the commutativity when gamma is symmetric. And if it is not symmetric, then you have the notion of torsion. So multiple fields can be coupled to this theory of gravity. They can be coupled directly to the Ricci tensor, Ricci curvature. We say that the theory is we have a non-minimal coupling, and one of these, features of this kind of action is that we have to have a non-zero potential energy at the first place. So if you have like potentials which go single or go to zero, like the spontaneous symmetry breaking potentials, then you have to add always a non-zero cosmological constant to guarantee that these kind of actions are not singular. So another feature is that you can switch from minimal coupling to non-minimal coupling to minimal coupling, which is I mean a parallel feature for Einstein Jordan frame. Here by switching only to a new potential energy, just so that you can absorb this function which appears the interaction between scalar fields and the curvature. Of course, here in metric gravity, remember that we have always we have to have the so-called conformal transformation or Weyl transformation of the metric, so that you have all the theory or minimal coupled scalar fields with the curvature. So in this case, there are some issues, of course. There are debates on so-called frame issues or frame ambiguities in the literature, because these kind of transformations, they can lead to like changing of Hubble parameters. They affect the Hubble parameter when you switch to the other frame, because Hubble parameter is nothing but the scale factor, and it affects also the number of E-folds, etc. In this kind of actions, you do have only potential. You change only the potential. Of course, you will have like a non-canonical kinetic terms here, and the field space is not completely flat. In the case of single field, of course, you will have when you transform to the minimal coupling, you will have exactly dynamics which is equivalent to general relativity. So now we have like purely a fine picture of the action, and we go through the equation of motion. We generate this this metric tensor. We vary it with respect to the connection, and we get an equation like this type. So, and then we substitute with this scalar densities, also which or scalar or tensor density, sorry, so that the notion of or the concept of metric becomes here as we have in general relativity. So the connection we started with, which was arbitrary, now it becomes a Levi-Civita of this metric, and then you can construct the Einstein tensor, and you go ahead with the gravitational equations, etc. Interestingly, you have no terms which are like covariant derivative of the non-minimal coupling function, which can be considered as sources of an isotropic pressures. So this will be important, the new feature of I mean, the absence of this kind of terms. The equation for the scalar field, so-called the Klein-Gordon equation, can be obtained by variation with respect to the scalar field. And you get an equation of this kind, and you see there is no metric at all. Of course, we started with a metric-free action. But once you generate the metric, as we did in the last step, and you substitute now, and you get the Klein-Gordon equation, where the deviations are clear, deviations from general relativity or purely metrical theory. And then you can study the background evolution of this scalar field. I mean, the standard, of course, dynamics, and you go and choose just a time-dependent scalar field, and you get energy density, pressure, Hubble parameter, etc. And the dynamics of the scalar field, of course, will be characterized by this equation, which can be also derived from the continuity equation of the conservation law. So these are all the basic steps of the background evolution. So we have the perturbation now. We go through the scalar field, I mean, expanding the scalar field here. And we expand also the non-minimal coupling function up to first order. And then you expand also the metric, where you have like this perturbation scalar here of phi and psi. This is usually called the Newtonian gauge. And then you derive the equations of motion. So you have the evolution of these potential, gravitational potentials here in terms of the perturbations of the scalar field. This is, of course, the time equation of motion, of gravitational equation of motion. And this is the mixed, like, time and space. And this one, the last one, is like the space. So there is an interesting point, is that it equals 0. It means that these potentials, are called the Barnum potentials, they are equal in this case. However, in metric gravity, you should have like terms which are sourced by an isotropic energy or energy momentum tensor, which appears as derivative of the second derivative of the non-minimal coupling function. So the non-adiabatic pressure, its definition is like this. If you put just single scalar field, you will realize that it's completely 0. And for the multiple fields, of course, you go through the equation of motion that we derived already, and you derive this expression, where here delta rho is the perturbation of the energy density, and delta phi, of course, the perturbation of the scalar field. And you substitute some of this delta rho plus 3h dot. You substitute with the equation of motion that the equation of motion from the gravitational field, and you get the last expression like this. So K here is the momentum, the frequency, which appears when you expand in Fourier mode. And you see that these two terms are completely expressed. Terms like these, they can appear for a single field as well. They are completely suppressed at super horizon scales when K is smaller than AH. And then you end up with two quantities. So the first one is completely related to the multiple fields. And the second one, it's related to non-minimal coupling, because as you see here, derivative of the function f with respect to the scalar fields. So at super horizon scales, we have two remaining terms, which are sources of the entropy perturbations. So we summarize them here. We notice, of course, that for a single field, you put just here delta phi, and all these terms will disappear. This, of course, consistent with the single case or single field case. When you have two fields, of course, you can realize that it doesn't vanish. It doesn't vanish simply because this term is not 0, because this one is what we call this is the contribution of the non-adiabatic perturbation, because like you have different parts of the universe, they have different overdensities, but the fractions are the same because, are not the same like the single scalar field. That's why this one doesn't vanish. So the second source is related to the non-minimal coupling, and what is interesting here, when f is completely constant, then this is a minimal case. Then you have this guy will disappear completely. The second property is that when you have only single field, also this term disappears. And this is what makes the formulation or this framework different than the purely metric gravity, because there are in the metric gravity there are contributions from only non-minimal coupling, even when you have only single field. So of course there are issues about this when you go to the metric gravity. So as I said before, we have like sources of an isotropic pressure, and then in the case of single scalar field, as you can see here, then it doesn't vanish. So this means that there is a frame issue, because when you in metric gravity, when you go to Einstein frame, so the theory becomes completely equivalent to a single field coupled minimally to gravity, and we should not have any entropy production. So it means that the so-called adiabaticity is not invariant under changing of frames. It means that when you have like an adiabatic perturbation in one frame, let's say an Einstein frame, which is the case when you have only one single field, then when you go to the other frame, these perturbations become non-adiabatic. So this means that the curvature perturbations, it can evolve with time in the Jordan frame, and it does not in the Einstein frame. So this frame issue is not present in this formulation. So you have sources of you have no sources of anisotropic pressure, and then you, in the case of single field, you have zero entropy production. So it's like the case of standard general relativity without non-minimal coupling. And the notion of adiabaticity is frame independent. So this is the comparison between fine gravitation and metric gravity at this cosmological application of non-adiabaticity. So this is all what I have actually, and thank you very much.
Okay, thanks Hamza for that nice talk there. So we've got time for a few questions. So if people could raise their hand, or you can type it in the chat window if you'd like. Okay. Okay, if there are no questions, or if people think of questions afterwards, of course, you're welcome to contact our speakers directly. Yeah, so that's the final talk of our session. So I'd like to thank all of our speakers this afternoon again. Imagine people clapping. And yeah, we pick up tomorrow at 9 o'clock South African time. Unless Sudan has anything he wants to add, go for it.
Nope, only a few people have survived to this point. So other rooms have closed down. So we'll resume tomorrow with the plenaries and a similar program at the end. Thank you to all. Bye.
Okay, thanks everyone. Bye-bye.
Bye.